Yeah, hi everyone, welcome to PrepFusion. So in this video, we are going to study about MOSCAP, Metal Oxide Semiconductor Capacitor. Very important topic for your GATE examination, and people find it confusing, right? People struggle in this particular topic. So that's why I thought that I should bring the complete concept starting right from the zero to very advanced level. Whatever that can be asked from this particular topic, that will be covered in this particular video. What all are the prerequisites? So you need to study semiconductor physics, right? If you are getting into EDC, it doesn't mean that directly, sir, I can start from MOS. No, you need to have a basic idea of basic semiconductor physics, and very basic idea of PN junction would also work. Okay, even if you know PN junction under equilibrium, no biasing. Under equilibrium, if you have studied all these three videos, then you will be able to understand this particular video as well. All these three videos are uploaded on YouTube only, so you can study these videos and then you can start with MOSCAP. What do I expect from you? What is the expectation? Comments. Once you are done watching this video, comment down that how did you feel, and if you have already studied this topic, then what different did you find out? Like we focused more on formula or concept building, whatever that you feel like commenting down, that you need to comment down once you are done watching this particular video. So MOS capacitor completely will be covered here, and all these three videos are also covered which you need to watch. Sir, I'm directly coming for MOSCAP only. Sir, I have studied all these concepts from some other educator. It is also fine. Just you need to have a basic idea of basic semiconductor physics and a basic idea of PN junction under equilibrium. That's it. That would be more than enough. Okay then? Yeah. Thank you very much. Happy learning. So let's get started. It would be of 8 hours 42 minutes. Okay. Yeah. Thank you very much. Happy learning. Yeah. Also one more information. Notes are uploaded. Notes are uploaded on our Telegram group. Okay. So notes you will find as MOSCAP. As far as I remember, MOSCAP slides. And printable notes are also there. MOSCAP printable notes are also there. Okay, and let's take up a target. Let's take a target of 150 likes. Okay, let's take a target of 150 likes. Okay, then notes are also uploaded on our Telegram group. Yeah, thank you and happy learning. Hi everyone, welcome to PrepFusion. So in this video, we are starting our new chapter, that is MOSCAP, Metal Oxide Semiconductor Capacitor. Okay, so notice the word capacitor here. Sir, we already know about capacitor. In network analysis, we study capacitor. In analog electronics, we study capacitor. Sir, capacitor is everywhere. We already know about it. But the kind of capacitor that you used to study, that was parallel plate capacitor, right? We used to call it parallel plate capacitor. That means there was a metallic plate, then there was some dielectric, and then again there was a metallic plate. So that was metal. Now, what is oxide? Oxide is an insulator. So here, in between the space of metal, what used to be there? Some insulator. It could be air, it could be some oxide, it could be some other insulating material. So there used to be some insulating material. So that insulating material we are assuming to be oxide. Oxide is an insulator. So it could be silicon dioxide, SiO2 it could be, or any other oxide it could be. So whatever the material that we are using here, that would be oxide. So instead of calling it insulator, I will be calling oxide. Okay. So insulator is nothing but oxide. And then there was another metal. So the capacitor that we used to study, that was metal oxide metal capacitor, not metal oxide semiconductor capacitor. In this chapter, we need to study about metal oxide semiconductor capacitor, not metal oxide metal capacitor. But in this video, we are going to talk about MOM, metal oxide metal capacitor. Sir, we already know about it, sir. Why we are wasting time? No, you are not wasting time. Something new you will be learning. So you need to have some patience and you need to watch this video completely. Okay. So what kind of capacitor we have already studied? So that I have already written. We have studied about a parallel plate capacitor. So this used to be our capacitor that we have already studied. So there used to be a metallic plate. Another metallic plate would be there. And in between, there would be some dielectric present. And that dielectric I am assuming as oxide. So I am saying that oxide thickness is TOX. What I am saying? Oxide thickness is TOX. Basically metal, in between there is oxide, then again metal. So what is the separation between the metals? TOX only. What is the thickness of oxide? That is also TOX. Right? All good. So this kind of capacitor we used to study. Here what we used to do? If I give some particular supply, if I give it some supply, then what will happen? If I give it a supply, then what will happen? This side is connected to, this plate is connected to positive. So here positive charge you will be getting. Now on this particular plate you will be getting equal and opposite negative charge. Equal and opposite negative charge. I hope you know all these things. So here if you are getting plus Q, on the other plate you are getting minus Q. Right? So capacitance was given by, or I can say that the charge Q was proportional to the applied voltage V. If I am increasing this voltage, this charge Q will increase. If I decrease this voltage, this charge Q will decrease. Or better, I should write down the change in charge was proportional to the change in voltage. So your capacitance was dq by dV. And when you remove this proportionality constant, what do you get? You get a proportionality constant, that is capacitance. So capacitance was given by dq by dV. And for parallel plate capacitor, or you can call it metal oxide metal capacitor, this was a constant value. This was a fixed value. This fixed value came out to be epsilon of the dielectric that we are using. So dielectric constant of the dielectric that we are using, that is our oxide. So here I can put epsilon oxide. Cross section area of the plates divided by the separation between them, which is TOX. So this was a constant value. This was a constant value. Or I can say that my capacitance value was not a function of applied voltage. So whatever the voltage that you are applying, that will not define the value of capacitance. Why is that so? Because if I increase the voltage in the same amount, my charge will also increase. Let's just say with respect to 5 volt, I am getting 2 coulomb charge here. With respect to 5 volt, I am getting 2 coulomb charge. If I make it 10 volt, then how much charge I will get? 4 coulomb. So slope is always remaining same, no? Like 5 by 2 or 10 by 4. Or better, I should write down opposite. So with respect to 2 coulomb charge, you applied 5 volt. Now with respect to 4 coulomb charge, you need to apply 10 volt. So basically here the scenario was that by the amount of voltage that I am increasing, if I am doubling my voltage, then my charge is also getting doubled. If I triple it, my charge will also get 3 times. So dq was proportional to dV. That means dq by dV was constant, and that was your capacitance. So capacitance was not a function of voltage. Where? In metal oxide metal capacitor. But now I want to make a capacitor. Now what I want to do? I want to make a capacitor which is a function of voltage. What is my requirement? Now my requirement is that my capacitance should be a function of the applied voltage. This voltage I will call as Vg. Why I am calling this G? Like what is the meaning of this G? You will understand. Later on you will understand it. So your capacitance should be the function. Your capacitance should be the function of applied voltage. This is my requirement. This is my requirement. That means I want to control the capacitance value with respect to the applied voltage. Control. I want to control the capacitance value. Just as you see the word control, what will come into your mind? Semiconductor. So that's why I moved to metal oxide semiconductor capacitor. Usually we start the MOSCAP from this is metal, then this is oxide, then this is semiconductor. Why semiconductor we are using? What is our target here? The target is that I need to make a capacitance which is depending on the applied voltage. As of now, the capacitor that I used, it is not depending on the applied voltage. It is completely constant. Okay, epsilon OX, constant value, TOX, constant value, thickness, constant value, area, constant value. So it came out to be constant only. So how do you measure a capacitance value? So sir, you applied some voltage and you get some charge, Q by V. That will be your capacitance value. No, this is not how you measure the capacitance value. How do you measure the capacitance value? I am talking about the measurement. So for measurement, what do? First you give it some fixed supply. Let's just say I am giving it some Vg equals to 5 volt. Okay. So with respect to 5 volt, what will happen? There will be some charge and some negative charge here. Let's just say this charge was plus Q and this was minus Q. Now on this fixed 5 volt voltage, what I will do? I will apply a small signal. Let's just say I am applying a small AC signal 0.1 sin omega t. Now the total applied voltage is 5 plus 0.1 sin omega t. This is the voltage that you are applying across the capacitor. This is the voltage that you are applying across the capacitor. Across the capacitor, this voltage has been applied. So 0.1 sin omega t, it can take the value from minus 0.1 to plus 0.1. That means it can take the value from 4.9 to 5.1. Your applied voltage across the capacitor can take the values from 4.9 to 5.1 volt. Basically, the applied voltage is continuously changing now. Is that clear? What will be the waveform of applied voltage? This will be the waveform of applied voltage. Sometimes it can get 4.9, sorry, sometimes it can get 5.1 and sometimes it can get 4.9. So it will toggle, the values will toggle between 5.1 to 4.9. So let's just say with respect to 5.1, I was getting some Q1 charge here and minus Q1 charge here. And with respect to 4.9, I am getting some Q2 charge here and minus Q2 charge here. Then I will see with respect to the change in voltage. What is the change in voltage? 0.2 volt. How much change in charge I am getting? How much change in charge I am getting? Q2 minus Q1. That will be my capacitance value. Next time what I will do? Between 4.9 to 5 volt. As I say, this point is somewhat 5 volt. So I will say that when my voltage is changing from 4.9 to 5 volt, with respect to 5 volt, let's just say my charge was Q3. Here minus Q3. So when I am changing from 4.9 to 5 volt, so how much my voltage is changing? 0.1. How much my charge is changing? With respect to 4.9, you are having Q2. With respect to 5 volt, you are having Q3. So how much charge you are changing? Q3 minus Q2. Then you will measure this value and you will find out that in all that change, with respect to the change in voltage, the charge is changing proportionally. dq will be proportional to dV, and you will find out that the capacitance value is coming out to be a constant value. That means if I draw the graph of applied voltage, this applied voltage I am calling as, look, here I will put Vg only. Here I will put Vg only. That means my Vg was 5 volt. My Vg was 5 volt. Okay. On this 5 volt, what I did, I applied a small signal. Sometimes it went to 4.9, sometimes it went to 5.1. So in this particular range, I got a constant value of capacitance. In this particular range, I got a constant value of capacitance, which was this value. Then what I did, I changed the gate voltage here. I made it 2 volt. So I made it 2 volt. Then again the same thing will happen, 1.9, 2.1. Again here you will get a constant value of capacitance. Here also you will do the same thing. Sometimes you will apply Vg equals to 7 volt. Across 7 volt, 6.9, 7.1. Again you got a constant value, and that constant value came out to be epsilon Ox Tox into A. This I am talking about metal oxide metal capacitor. So this is how you measure the value of capacitance. Okay, it's not that sir I apply 5 volt, whatever the charge you get, so charge divided by voltage, that will be my capacitance value. That is true for metal oxide metal capacitor, but it might happen that sometimes your dq is depending on dV, or better I should write down here my capacitor is, here my capacitance value is constant, but sometimes it may happen that capacitance value is not constant. Then this Q by C formula would not work. We used to write down C equals to Q by V. This we write down, right? So this formula works only if this is constant. This is not a function of V. But what if this is a function of V? Then you need to do dq by dV, no? And for measuring dq by dV, what you need to do? Give a fixed supply which is 5 volt, and then superimpose a small signal, small AC signal over this. That means the value can go to 5.1 or 4.9. So between, when it is going from 4.9 to 5.1, what is the change in the charge you are getting? When it goes from 4.9 to 5, what is the change in charge it is getting? When it goes from 5 to 5.05, then what is the change in charge you are getting? Notice the change in charge, notice the change in voltage. You will find that dq by dV is always coming out to be constant for metal oxide metal capacitor. For MOM capacitor, it is coming out to be constant only. And after that, what I will do, I will change the supply. I will check it at 2 volt, I will check it at 7 volt, I will check it at minus 1 volt, I will check it at minus 3 volt. Everywhere I will check it, and every time I will get the same answer, which is this value. So this is my capacitance value, and this answer will come out to be epsilon Ox Tox multiply with area. Is that clear? Now can anyone think that why this is happening? Like why we are getting the constant value of the capacitance? Why this graph is constant? Why we are getting this kind of graph? Because what we are using metals, and metals have more than enough electrons or more than enough charge carriers. So if you apply any positive charge here, this switch should be closed. So if you apply any positive charge here, the metal will immediately give you negative charge. Immediately. Like I was having 5 volt, 5 volt, 5 volt, suddenly I applied 5.1. So suddenly here here the charge will be developed corresponding to 5.1 voltage. Let's just say with respect to 5.1 voltage, you are getting the charge Q1. So metal is having more than enough charge carriers. This positive charge, this positive plus Q1 charge will ask this metal to give him minus Q1 charge, and this metal will say, I am having more than enough charge carriers, immediately I can give you minus Q1 charge. Now from 5.1 to, let's just say suddenly I went to 10 volt. So what this metal will say? With respect to 10 volt, if you are having, let's just say Q4 charge here plus Q4 charge here, then I can give you minus Q4 charge immediately. That means with respect to the change on this metallic plate, the second metallic plate is responding immediately. I hope you are listening to every single word. Okay, with respect to the change in charge at metal 1, the metal 2 is responding immediately because both of the metals are having more than enough charge carriers. That's why the capacitance value is constant. That means the change in charge is proportional to the change in voltage. The change in charge is proportional to the change in voltage. Just as voltage changes, the charge also changes very immediately. Right? Just as this voltage changes. Let's just say if I change this voltage by 10 volt, then this charge will also change by 10 coulomb. Or I should not say 10 coulomb, in proportional manner it would change. Right? But it might happen that if you are going from 10 volt to 2 volt, with respect to 10 volt you are having 10 coulomb. When I went from 10 volt to 20 volt, let's just say I got 20 coulomb charge. Now if I go from 10 volt to 30 volt, here if I am getting 25 coulomb charge, then your capacitance value will not be constant. Why is that so? Because here you went doubled, or better I should say, voltage got doubled here, charge got doubled. Here voltage got doubled, but voltage got 1.5 times. From 20 to 30 volt if you go, then voltage will be 1.5 times, right? But here your charge did not become 1.5 times, because from 20 to 30 it should have gone, but if it is going to 25 coulomb, then there is some issue. Then your capacitance is not, then your charge developed is not proportional to the change in voltage. But for metal is having more than enough electrons, more than enough charge carriers. If you change any kind of charge on this particular plate, it will respond immediately. But semiconductor is different. Semiconductor, it is not necessary that semiconductor will have more than enough charge carriers. Is that clear to you? That's why we will use first plate metal, then oxide, and then we will use semiconductor. And in semiconductor, interesting things can happen. So we will study that, but we will study that in next chapter. As of now, I am building up the concept. I hope it is not reflecting you. Like people may get reflected, sir, what we are studying. We used to study MOSCAP in different manner. You used to study in different manner. Here you will study in different manner. Okay. Here I am directly not going to start MOSCAP. First, I will do the discussion of 2 to 2.5 hours that why we need MOS capacitor. So that discussion I will do, and then only I will start MOSCAP. Next lecture will be based on MOSCAP, and believe me, you guys will be 100% confident. Like you will see MOSCAP and you will be able to tell what will be the capacitance value. Everything you will be able to comment. It's just that you need to focus on this particular lecture in a good manner. Okay. So as of now, what is the conclusion we have made? That when I am using metal-oxide-metal plate, when I am using metal-oxide-metal capacitor, the change in charge is proportional to the change in supply or change in the voltage. That's why my capacitance value is constant, epsilon OX multiplied with area divided by TOX. This is the capacitance value I am getting. Okay. And why it is constant? Because metal is having enough charge carriers. Metal is having more than enough charge carriers. So whatever the change on one metal plate we are doing, the same change is happening in the other metal plate as well, very immediately. Okay, because of that the capacitance is coming out to be constant only. So this theory has been written here. In a metal oxide metal capacitor, both plates are metal. When you apply a voltage, the metal respond instantaneously by rearranging electron on its surface. Whatever positive charge you apply on one plate, equal and opposite negative charge immediately appears on the other plate. Because of this immediate response, the charge changes linearly with the applied voltage. dq by dv remains constant. As a result, the capacitance value stays fixed and it is determined by the geometry only. Sir, how this formula came, that you can study in network analysis or in AMFT. How this formula came, that I am not deriving. The derivation you can do. That will be epsilon x TOX multiplied with the area. So this is the capacitance value we get. Right? And you can see that since neither the dielectric constant nor the oxide thickness or you can call it separation between the capacitance value, right? Sorry, separation between the metallic plate. So what is written here? Neither the dielectric constant nor the physical separation changes with the bias. The capacitance does not vary with the applied voltage. That's why metal oxide capacitor cannot provide voltage dependent capacitance. Capacitance is not proportional to the applied voltage. This is for metal oxide metal capacitor. But what I need to do, I need to make a capacitor which is depending on the applied voltage. That is my metal oxide semiconductor capacitor. Okay, so remember this graph, this kind of graph we are getting in metal oxide metal capacitor. This is for metal oxide metal capacitor. In the end, we will see that for metal oxide semiconductor capacitor, we will get this kind of a plot. So there, with respect to the applied voltage, your capacitance value is changing. So this is our target. This is something that we need to study. So this is something that we are getting for metal oxide metal capacitor, MOM. So that is the reason we move to a MOS structure where the semiconductor allows voltage dependent capacitance to be obtained. How it is allowing, that we will see later on. Now let's see an important note. What is that note? The note is that it is coming from EMFT. So electric field inside a metal or inside a conductor will always be 0. Basically, if I bias it, this is my metal oxide metal capacitor only. This is your metal, this is your oxide, this is your metal. Here we used to show a plate, but this plate will have some thickness, no? So that thickness I am showing here. This is the thickness of the plate. This is the thickness of the plate. This is the thickness of the other plate, and this is the thickness of the oxide. Basically, this TOX will be much larger than this metal thickness. I am calling this thickness as TM. This is your metal thickness. So your metal thickness is much lower than the oxide thickness, but again some thickness would be there, right? So let's just say I am giving it some positive bias. Here I am applying some positive bias. Here I am applying some positive bias. So this plate will be positively charged. Now where that positive charge would go? So first thing is that whenever you give any positive charge, let's just say this is your metallic, this is the metallic bowl I am having. Metallic bowl. Okay, am I having some bowl? No. Let's just say this is made of metal. If I give it positive charge, where the positive charge will be stored? On its surface. It will not go inside. It will be on its surface only. Sir, why is that so? In EMFT, I have explained it. That why the charge remains only on the surface, why it doesn't go inside. So if you give it any charge, it will remain only on the surface. So on the surface only it will remain. Now in case of capacitor, where the charge will go? Someone can say that, sir, the charge can come here, or on this surface it can come, or sir, on the downward surface it can come, or sir, here it can come. Basically, this kind of plate, let's just say this is the plate. So it is having this surface as well, the downward surface as well, this particular surface as well, this particular surface as well, here as well, here as well. So where the charge would go? It is having six kind of surface. So in which of the surface the charge would go? So there is another point. The point says the electric field inside the metal is 0. Now if you are giving it positive charge, then you know that on the other plate negative charge would come. Here as well negative charge can come here, here, or here, or here. Now if I am assuming that on the upper plate, here positive charge is available, then what kind of electric field you will be getting? Electric field is always directed from positive charge to negative charge. If I am saying another mobile I would require, yeah. So these are the two metallic plates I am having, okay? Two metallic plate, inside there is a oxide. So when I gave it positive charge, the positive charge went here. On the upper surface it went. This is what I am saying. So if it is going on the upper surface, I am not caring about the downward surface. On the downward surface, let's just say anywhere some charge is present. Here positive charge, here negative charge. So electric field will be going from this particular point, from the upper point to the downward. That means inside the metal as well there will be some electric field, no? Can you see it? From the upper plate it is going downward. Downward till what point it goes, I don't care about it. But I know one thing, that if the charge is stored upward on this plate, then the electric field will go, I cannot break it, right? But you are understanding, right? It will go from the metal surface. Then inside the metal it will go, then it will come out from the other metal surface. That means if you are giving it positive charge, then the positive charge cannot be stored on the upper surface. It cannot be stored on the sideward surface. It has to be stored on the lowermost surface, so that there is no electric field inside the metal. Now from here, if electric field lines are getting out, then there is no issue, because these are not inside the metal, it is coming out of the metal. Inside the metal, electric field has to be 0. So whatever the positive charge you give, that positive charge will come right at the bottom surface. Okay, and this thing I will again and again will be using when we study about metal oxide semiconductor. There I will say I am giving it a positive charge, but positive charge will come here, not here. Okay, and at that time I will not answer that why in the metal the positive charge is coming on the lower surface, sir, not on the upper surface. Now what about the bottom surface? What about the bottom surface where the negative charge should come? If negative charge is coming on that downward surface, so from the upper side electric fields are coming. Now if negative charge is there on the downward surface, then what will happen? The electric field will penetrate inside the metal, but metal will not allow electric field to penetrate. That means the negative charge has to be there only on the upper surface only. Now in this condition, what will be the scenario? There will be surely electric field, but the whole electric field will be there inside the oxide. Complete electric field is there inside the oxide. There is no electric field inside the metal, nor on this metal. And this is the property of metal, that inside the metal there cannot be any electric field. And whatever the charge that you give, that will be stored on the surface, but on which surface, that is also clear to us. Why all the charge is coming on the downward surface for metal 1 and why all the charge is coming on the upper surface for the metal 2, is it clear to you or not? And whole electric field will be there inside the oxide only. If someone asks you what is the positive charge, how much charge is available on this particular plate, you will say 0 charge. If someone asks you how much charge is available on this particular surface, you will say 0 charge. The charge is there on this surface, the charge is there on this surface, and where is the electric field? Inside the metal, electric field is 0. Inside the metal, electric field is 0. Inside the oxide, we show the electric field by this particular sign, no? This is how I am showing electric field. But inside the oxide, electric field is non-zero. These are very important points. You are not going to find it out like anywhere, you are not going to find it out. But these points are important to understand MOS physics. Okay, when we move to metal oxide semiconductor capacitor, all these points will be used. In accumulation mode, Y capacitance is constant. In inversion mode, Y capacitance is constant. Why in the depletion mode only capacitance is variable? So instead of going into mathematics, I will explain intuitively that why your capacitance is constant in accumulation mode and inversion mode, and why it is varying in the depletion mode and the weak inversion mode. So all these points we will see, but as of now you need to understand whatever the point that I am telling. So on positive plate, all the positive charge will sit on the lower surface, the surface facing the dielectric or oxide you can call it. On the negative plate, all the negative charge will sit on the upper surface, the surface that is facing the dielectric. Outer surface carry no charge. Outer surface carry no charge. Outer surface carry no charge. Is that clear to you? So this is your parallel plate capacitor or metal oxide metal capacitor that we were studying. What all point we saw? That if I give it a positive voltage, positive charge stored here, negative charge would come up. Immediately it would come up because they are having more than enough electron and holes, or you can say more than enough charge carriers it is having. So whatever the change in charge you are applying on one plate, the change in charge on the second plate is reflected immediately. Capacitance is constant, that is coming out to be epsilon OX divided by TOX multiplied with the area. So this is the capacitance that we are getting. How do you measure a capacitance value? Sir, applied some voltage, get some charge? No. What you do? Apply some voltage and then some small signal voltage if you also will apply. Then some change in charge would be happening in both of the places. Right? Some change in charge will be taking place in both of the places. And what you need to do? You need to measure this change in charge with respect to change in voltage, and that will come out to be constant, and that is coming out to be epsilon OX divided by TOX multiplied with the area. And why it is coming out to be constant, that is clear to you, because whatever the change is happening in one plate, the second plate is responding immediately. The second plate responds immediately, right? This theory has been written here. So here you can see that your capacitance is not a function of applied voltage. That's why it is known as metal oxide metal capacitor. When it becomes a, what I require the capacitance to be a function of applied voltage. I require the capacitance to be a function of applied voltage. There I will be using MOS capacitor. Okay. And this very basic thing we show that if I am giving a charge, positive charge, that will come on the downward surface. Here it will come on the upward surface. Inside the metal there will be zero electric field, and the charge will be stored on the downward surface facing the dielectric, upper surface facing the dielectric, and inside the metal zero electric field would be there. So these 2 points are also very important. Now ideally we should start our MOS capacitor, but we will see some points, some important points. Those points you might have already studied in basic semiconductor physics, but we will revisit them and make some conclusion. All those conclusions you already know, but don't skip it. You can watch it in a quicker manner. You can watch it at 1.5x, 1.75x, 2x. You can watch it in quicker manner, but don't skip it. All these things you already know. Intrinsic semiconductor we are having with Ni value of 10 to the power 10 centimeter cube inverse. What I am doing? I am doping acceptor atoms of 10 to the power 17 centimeter cube inverse. That means my number of holes will be 10 to the power 17 and number of electrons will be 10 to the power 3. Why is that so? Because I remember mass action law, n into p equals to Ni square. Where will be my Fermi level? Sir, your Fermi level will be near to the valence band. This will be your Fermi level. What about this one, sir? Here, sir, your number of holes will be 10 to the power 11, number of electrons will be 10 to the power 9. Where will be your Fermi level? Sir, your Fermi level will be somewhere here, near to the valence band, but here doping is more, here doping is less, so this will be upper side. Sir, what about this one? Fermi level will be somewhere here. Sir, here your electron concentration is 10 to the power, or better write down hole concentration first and then electron concentration. So electron concentration will be 10 to the power 17, but hole concentration will be 10 to the power 3. Sir, what about this one? Electron concentration will be 10 to the power 11 and hole concentration will be 10 to the power 9. Okay, sir. And where will be your Fermi level? This will be your Fermi level. So we call this as Fermi level EF, and this is our intrinsic Fermi level EFI. Now see the conclusion one by one. See the conclusions one by one. So first conclusion, all these conclusions have been written, but they will make a very important role. What is the first conclusion? If the Fermi level is below the intrinsic Fermi level, then the holes are the majority carriers. If your Fermi level is below the intrinsic Fermi level, then holes are the majority carriers. 10 to the power 17, 10 to the power 11, that means holes are the majority carriers. Here, holes are the majority carriers, and here, electrons are the majority carriers. And if your Fermi level is above the intrinsic Fermi level, if your Fermi level is above the intrinsic Fermi level, then electrons are the majority charge carriers, electrons are the majority charge carriers. All these things I already know, right? But those conclusions will be helpful in the next lecture. A higher position of Fermi level indicates more free electrons. This is very important. So out of all these four scenarios, who is having maximum electrons? What I am talking about?
electrons, not charge carriers. What I am saying, which of the four scenarios is having maximum electron, not charge carriers. So this guy is having maximum electron. If I give the rating, then this guy will come at first for the electrons. This guy will come at second. This will come at third, and this will come at fourth. Say yes or no? Electrons, 10 to the power 3 least, 10 to the power 9, 10 to the power 11, and 10 to the power 17. So first rating, second, third, and fourth. Only talking about the electrons, not charge carriers. Someone would say that, sir, it is having higher charge carriers. But I am not talking about charge carriers. I am not talking about holes. I am only considering electrons. So higher position of Fermi level, this is highest, then this is at second, then this is at third, and this is at fourth. So higher position of Fermi level means more free electrons. So this has been written. A higher position of Fermi level indicates more free electron. Okay, and if the smaller gap is there between Fermi level and intrinsic Fermi level, that shows fewer charge carriers, or you can call it less doping. Basically, here the gap is less, no? Here the gap is less. So how many charge carriers you are having? So 10 to the power 11 plus 10 to the power 9, which will be nearly equals to 10 to the power 11 only. Here 10 to the power 11 plus 10 to the power 9, so charge carriers are 10 to the power 11 only. What about these guys? 10 to the power 17, 10 to the power 3, 10 to the power 17. 10 to the power 17 plus 10 to the power 3, 10 to the power 17. So this guy is having higher charge carriers. This guy is having higher charge carriers. But if the gap is small, that means it is showing less charge carriers. So if I ask you who is the maximum conductive, who is the most conductive, you will say, sir, this guy and this guy. Now someone will say that, sir, electron mobility is more, that's why n type is more conductive. Yeah, that is fine. But only looking at the charge carriers. If you don't know whether it is n type or p type, only looking at the charge carriers, who is the most conductive? This guy is the most conductive. This guy is the most conductive. And who is the least conductive? So this one and this one. Why is that so? Because gap is lesser. If the gap is lesser, that means you are moving towards the intrinsic only. And in the intrinsic, you know that conductivity is very less. In your intrinsic semiconductor, in your intrinsic silicon, the conductivity is very less. The conductivity was less. That's why we moved to n type or p type. That was the reason, right? Why we moved from intrinsic to these extrinsic semiconductor, which is n type and p type. Why we moved from here to here? To improve the conductivity. So if less space is there, that means less conductivity. If more space is there, more conductivity. And if someone asks you who is more metallic, what I am saying, who is more metallic? Metallic means who is more conductive. So who is towards like, if I say out of these four, two guys are metal, then whom I will call metal? This one and this one. This guy and this guy. Why so? Because they are having higher number of charge carriers. Basically, if I am saying that one of the semiconductor is moving towards metal, moving towards being metal, metal means higher conductivity. So which guys are having higher conductivity? These two guys are having higher conductivity. That means their gap between intrinsic Fermi level and the Fermi level is higher. This gap is higher. Okay, so all these points will be useful in the next lecture. There I will be directly writing down the things, and I will not be saying that from here, from where these things are coming up. As of now, it feels like that, sir, we already know it. Why you are wasting time? Why you are focusing so much on this? In the next lecture only, all these things will come up and you will be thinking, sir, how that happened? So at that time, I will not be telling you. Okay. So you see this conclusion. Let's verify these conclusions with p-n junction. Sir, p-n junction complete analysis we have studied. Let's do the analysis in a different manner. So this was your p-type semiconductor. This was your n-type semiconductor. Here doping of acceptor atom would be there. Here doping of donor atom would be there. So here Fermi level will be above. Here Fermi level will be less. Now I know that I need to join them. Okay. So just let me know one thing. Who is having more electrons? I am talking about electrons. Which guy is having more electrons? This guy is having more electrons. And this guy is having less electrons. So when you join them, what will happen? Electrons will flow. Here there is more electrons, here there are less electrons. So electrons will flow from here to here. So this particular side is losing the electrons. This particular side is losing the electrons because higher electrons, lower electrons will flow. So this particular side is losing the electrons. That means this side will become positive, and this particular side is taking the electrons. So this side will become negative. What will be the direction of electric field? From positive to negative. So in the depletion region, this is the direction of electric field. We used to call it built-in electric field. So electrons will flow till which point electrons will flow. So if electrons are getting out, that means electron concentration is going down. If electrons are getting out, that means electron concentration is going down. That means this Fermi level will go down. And here electrons are getting more. If electrons are getting more, that means Fermi level will go upward. More electrons shows if Fermi level, a higher position of Fermi level will indicate more free electrons. So here electrons are going out, that means free electrons are going down. That means free electrons are less. That means your Fermi level will go downward. Electrons are getting in here. Electrons from here is getting into this particular semiconductor. That means free electrons are increasing. If free electron increases, then Fermi level will go upward. There will be one point where both of the Fermi level will be inclining. And that point is known as equilibrium. We have understood the analysis of PN junction in a different manner. Here I am doing the analysis in a different manner. I hope you are understanding this point. Electrons are flowing. Electrons will reach here. This guy goes upward, this guy goes downward, and they will become flat. When they have become flat, at that point, this guy is having same number of electron, and this guy is also having same number of electron. There will be no electron flow. So this is the equilibrium condition that we have achieved, and this is the built-in electric field as well we have seen. So what is the direction of built-in electric field? You can see that, sir, this is the direction of built-in electric field. In the direction of electric field, slope in the conduction band, valence band, and intrinsic Fermi level will be positive. In the direction of electric field, slope is positive. In the direction of electric field, slope is positive. In the direction of electric field, slope is positive. Well and good. Okay. So one point, did you understand these points? Okay. I hope you have understood all these points. So let's keep the diagram as it is. In a different manner, we are doing the analysis. In the previous videos, when we study PN junction, what we did, holes will diffuse from here, electrons will diffuse from here, they will recombine each other, then electric field will be set up. So that analysis is also fine. Here, with respect to band diagram only, we are doing the analysis. The electrons, more electrons, lesser electrons, electrons will flow. Electrons will keep on flowing until the point both are having the same number of electrons. So here electrons are increasing, this guy is going upward, here electrons are decreasing, this guy is going downward, both will become flat. So this particular whole level, this whole band diagram came downward, this whole band diagram went upward, right? So this kind of scenario we got, this kind of electric field we were getting. And what is the direction of electric field? Since it was losing the electrons positive, it is gaining the electron negative. This is the direction of electric field. This is the direction of built-in electric field. Okay, more points we can see. What points we can see? Do you remember the carrier concentration diagram? Let's just say here the doping was 10 to the power 16. Here also the doping was 10 to the power 16. Okay. So here number of holes were 10 to the power 16. Here number of electrons were 10 to the power 16. So number of holes were 10 to the power 16. Here also 10 to the power 16. So what will be the number of electrons here? Sorry, this was number of electrons. What will be the number of holes here? 10 to the power 4. And here holes will be 10 to, sorry, electrons will be 10 to the power 4. So this was the concentration of holes. This was the concentration of electron. This was the concentration of electron. This was the concentration of hole. This was your n side at equilibrium. Holes in n side at equilibrium. Holes in p side at equilibrium. Electrons in p side at equilibrium. So this was the scenario. Inside the depletion region, what will happen? We have seen this plot that electron hole concentration is going down, electron concentration is going up. So let's just say at this particular point, the whole concentration has become 10 to the power 14. So what will be the electron concentration? 10 to the power 6. Because I know that n into p equals to ni square will always be applicable. So here 10 to the power 16, 10 to the power 4, that would become 10 to the power 20. 10 to the power 4, 10 to the power 6, that would also become 10 to the power 20. But here the charge carriers were 10 to the power 16 plus 10 to the power 4. So nearly it would be equals to 10 to the power 16. But now in this one, the charge carriers are 10 to the power 14 plus 10 to the power 6, nearly equals to 10 to the power 14, which is very less. 10 to the power 16 is much larger than 10 to the power 14. It is 100 times, right? So charge carriers have went much down. And can you verify it? Yes. The gap between intrinsic Fermi level and Fermi level. Now this has become one Fermi level only. I will call it Fermi level. EF and EFP are gone. I will simply call it Fermi level. So the gap between intrinsic Fermi level and the Fermi level is reducing. That means the number of charge carriers are decreasing. Fermi level is below the intrinsic Fermi level. In this particular region, let's divide it one more time. How will I divide it? Let's divide it one more time. What is this point? This is the point of junction. This is the point of junction. Both are the same point. This is the point of junction. This is the point of junction. So before this junction, or here, I am talking about this particular region. So in this particular region, what you can see, your intrinsic Fermi level is above than the actual Fermi level. Intrinsic Fermi level is above than the Fermi level. This guy is above than this guy. That means here, holes will be more. See this point. If Fermi level is above the intrinsic Fermi, this point. If your Fermi level is below the intrinsic Fermi level, if your Fermi level is below the intrinsic Fermi level, then the holes are the majority charge carriers. That means yes, holes are the majority charge carrier. Here holes is more than the electrons. But here what will be the scenario? Electrons will become 10 to the power 14, but holes will become 10 to the power 6. You can see here, your intrinsic Fermi level is below the Fermi level. So if your Fermi level is above the intrinsic Fermi level, if your Fermi level is above the intrinsic Fermi level, then electrons are the majority. Yes, electrons are the majority. But actually what is happening? This guy is going down, down, down. This guy is going up. Here it becomes up. Here it becomes down. At this particular point, can you let me know what will be the electron and hole concentration? At this particular point, at the junction, this is the point of junction. Sir, here electron and hole concentration would become equal and they will become equal to 10 to the power 10. That means at the junction, we have become intrinsic semiconductor. Is it same? Yes, sir. At the junction, the gap between Fermi level and the intrinsic Fermi level is 0. I am just verifying these points with respect to PN junction, nothing else. Sir, we were studying MOSCAP, why we are directly moving to PN junction and all these kind of things. In the next lecture, we are starting MOSCAP. As of now, we need to study some prerequisite and metal-oxide-metal capacitor. Okay. So if you want to study from here, then this is how you need to study. I cannot start MOSCAP, positive bias, you apply, this will happen, that will happen. No. Proper reasoning would be there, and in the next lecture, you will enjoy it a lot. But as of now, these kind of prerequisite you need to cover. So with respect to band diagram, we can verify all these points. Is that clear to you? And this point also you can verify. A smaller gap between the Fermi level and intrinsic Fermi level means fewer charge carriers. Here the gap is lesser than this gap. Here the gap is lesser than this gap. So gap is more charge carriers. Here more charge carriers were there, which I have shown in this particular diagram. More charge carriers, lesser charge carriers, more charge carriers. So if the gap is more charge carriers. Gap is more charge carriers. If gap is lesser, less charge carriers. And we used to call it depletion region. In depletion region, there are very less charge carriers, or we used to call it, this is like an insulator only. Right? Why so? Because there are lesser charge carriers. If less charge carriers means it's like an insulator only. So depletion region was like an insulator only. I used to say that this will provide very high impedance, and these guys will provide very less impedance because they are having more charge carriers. So this was like an insulator. So it's like a semiconductor oxide semiconductor scenario. Semiconductor oxide semiconductor. This kind of scenario it is. Right? So whatever we start, we always start from basic semiconductor physics only. What was this? This was basic semiconductor physics. Then this was our second chapter, PN junction. Right? So everything is related with the basic semiconductor physics only. You study the whole MOSCAP, it will be related with basic semiconductor physics only. That's why I say that in EDC, 50% is basic semiconductor physics and 50% is rest of the chapters. So if you have covered basic semiconductor physics in a good manner, then MOSCAP and everything will become a cakewalk for you. So we are just revising our basic semiconductor physics, but in a complete different manner we are studying it. Electrons flowing here, this became negative, this became positive, both became on the same level, and this kind of band diagram we are getting. And like this kind of bending is there, no? You can call it bending, right? You can call it bending. So this is known as bend bending. What it is? Bend bending. Bends are being bent. So what we call it? Bend bending. This scenario we call it bend bending. Bends are bending, no? So we call it bend bending. Okay, bend bending. So let's remove it. All the points we have verified. Okay. So some discrete points we are studying. One point we have studied, these points we studied, these 4 points we studied, and we verified it with this one. Now another point I need to verify, what is that? Effect of biasing on Fermi level. Only Fermi level I am going to draw. I don't know what kind of semiconductor it is, but I know that this is how my Fermi level would be there. Why is that so? This is how my Fermi level will look like. Why so? Because current is 0. No? You know that the slope in Fermi level is proportional to the current flowing. So if current is 0, that means Fermi level will be uniform. So this is how your Fermi level will look like. Here, what is the direction of current? Sir, this is the direction of current. So in the direction of current, the slope of Fermi level will be positive. So this is how the Fermi level will look like. So let me show it somewhat like this. So this is how the Fermi level will look like. Here, what is the current direction? This is the direction of current. So in the direction of current, Fermi level slope will be positive. So in the direction of current, Fermi level slope will be positive. Now can you verify one thing for me? What I can verify? Here positive bias will be applied and this side I can take negative. Here positive bias will be applied and this side I can take negative. So where positive is applied, that side has gone downward. This was the initial position, this side has gone downward. Where positive bias is applied, positive bias is applied, this side has gone downward. And where negative bias is applied, that side has gone upward. Negative bias, that side has gone upward. So positive bias, side goes downward, negative bias, side goes upward. This is something that we have written here. Just remember this point. I will be using this point somewhere. At that time I will not be explaining it because I have already explained. When a positive bias is applied to a region, the Fermi level shift downwards. When a negative bias is applied, Fermi level shift upward. Only we are talking about the Fermi level. I am not talking about conduction band, valence band or intrinsic Fermi level. I am only talking about this guy. Only talking about this guy. Okay. Now some definitions we need to define. So this is a new point that we are going to understand. So 3 points we are going to understand: work function, electron affinity and Fermi potential energy. So 3 terms are there. We are going to define it as of now. So first I am going to define it with respect to the band diagram. So first we will see with respect to the band diagram and then we will understand the physical meaning. Okay. So first we will see with respect to band diagram. So let's just say this is the semiconductor. In this semiconductor some electrons will be there, holes will be there. And this is your outer space. All this is your outer space. So in this semiconductor, electrons and holes will be occupying some particular energy state. In this semiconductor, electrons and holes will be occupying some energy states. Now in the outer space as well, there will be some energy. So energy of outer space I will be showing by E vacuum. This is the energy of outer space. Just let me know one thing. If you are confined in a room, let's just say you are closed in this room or you are outside, when you will have more energy? When I am outside, right? I can move here, there, everywhere I can move. So if you are outside, your energy is more. If you are inside, your energy is less. So these are the energy levels of a semiconductor. This is your semiconductor. All these are inside the semiconductor. Or better I should write down any material, because these terms are defined with respect to any material only. So this is your any material. Inside this material you are having conduction band, valence band, intrinsic Fermi level and your Fermi level as well. Although by this diagram you can verify it that it is a p-type semiconductor, right? This diagram is there for p-type semiconductor, but as of now I am considering as a general material. And outside environment is having an energy of E vacuum. So this will be like a reference energy level. Work function and electron affinity will be defined with respect to this E vacuum. So whatever the energy that is required to go from your Fermi level to vacuum energy level, this much energy is known as work function. So I will denote work function as Q phi. And whatever the energy that is required to go from conduction band to vacuum energy level, that is known as electron affinity. I will denote it by Q chi. What it is? Chi. And what it is? Phi. Can you tell what is phi and chi? Like what is the unit of phi and chi? What is the unit of phi and chi? Can anyone tell what will be the unit? This is your work function energy. Work function energy. And this is your electron affinity energy. So can anyone tell what will be the unit of phi and chi? Volt. Right? Phi and chi are voltage. So I will call phi as work function potential. I will call chi as electron affinity potential. Is that clear? If you multiply any potential with the charge, what you will get? Energy. So this is the energy. This is the energy. This is also energy. But phi and chi are potential. Phi is the work function potential. Chi is electron affinity potential. What is work function energy? Energy required to go from Fermi level to the vacuum energy level. And what is your electron affinity? Energy required to go from the conduction band to vacuum energy level. That is your electron affinity. There is something called Fermi potential energy as well. That is the gap between intrinsic Fermi level and Fermi level. This is the gap that is known as Q phi. Okay, so your Q phi is nothing but EFI minus EF. The gap between intrinsic Fermi level and Fermi level. It could be, I should put a mode here. Why I am putting mode? Because who knows, Fermi level can be above as well. So basically the gap between the Fermi level and the intrinsic Fermi level is known as Fermi potential energy. If Fermi potential energy is high, what does that mean? This gap is more. If this gap is more, what does that mean? Doping is more. If doping is more, what does that mean? More conductivity. So if gap is high, that shows higher doping. If gap is lesser, that shows lower doping. You don't need to mug it up, you will be able to understand. So Fermi potential energy, everything is clear about Fermi potential energy. What is your Fermi potential energy? Q phi f. Sorry guys, here it should be written Q phi f. Fermi potential, F shows for Fermi. So Fermi potential energy is the gap between the intrinsic Fermi level and the Fermi level. What is work function energy? Energy required to go from Fermi level to vacuum energy level. What is your electron affinity energy? Energy required to go from conduction band to vacuum energy level. Now what do you think what it is representing? What is the physical meaning of work function? So inside the semiconductor, if some electron is there, this electron could be free as well, this electron could be bound as well. So what amount of energy you need to give to this electron such that it will leave the semiconductor and will come to outer space? There is some electron that is present inside the semiconductor. So how much energy you need to give to that semiconductor? Sorry, how much energy you need to give to that particular electron such that it leaves the semiconductor and comes into the outer surface? Now the point is, sir, the electron could be present in valence band as well. Sir, the electron could be present in the conduction band as well. Sir, why you took from the Fermi level? So what did I tell you? The electron is present inside the semiconductor. Whether it is free or bound, I don't know. So electron could be present in valence band, electron could be present in conduction band. So what I need to do? I need to take a kind of average, no? And what is the average of conduction band and valence band? It is the Fermi level. What was your Fermi level? What was the definition of Fermi level? Fermi level was that energy level where the possibility of finding electron is 50%. That means 50% chances are there that electron is bound and 50% chances are there that electron is free. So this is the point which is like an average state of an electron. This is your average state of an electron. Are you able to understand what I am saying? What is the physical meaning of Fermi level? Like if I am saying that this semiconductor is having 10 electrons, I am not telling whether it is free or bound. It could be free as well, it could be bound as well. And I ask you, what is the position of that? What is the position of that particular electron? What you will say? Position is, this is the position of the electron that is present inside this semiconductor. Sir, I don't know whether it is free or bound. So what I will do? I will take an average energy level, and that will be my Fermi potential level or Fermi energy level. Is that clear? So what do you think? What is electron affinity? So electron affinity is defined with respect to a free electron. That I am pretty sure the electron is already free. That means already electron is having good enough energy. Now you give him some energy such that it leaves the semiconductor surface. that is known as electron affinity. When work function energy you define it with respect to the free electron as well, with respect to the bound electron as well. You don't know whether the electron is free or bound. So that's why when you take work function energy, it is defined from the Fermi level. When you take electron affinity energy, it is defined from the conduction band. A very, very interesting point. I will not say important, because in the examination it might not be used, but very interesting. That why do we define the Fermi energy level from the, why do we define work function energy from the Fermi level, and why do we define electron affinity from the conduction band? What is the reason behind that? So work functions tells you about all the electrons. It could be free as well, it could be bound as well. But electron affinity only tells about a free electron, because here free electron only will be present. I will not show it in the diagram, but in the conduction band you always know that free electron is present. But in the Fermi level there is 50% chances of free electron, 50% chance of free electron, and 50% chance of bound electron. But in the conduction band 100% free electron will be there. No, let's remove it. 100% free electron, and in the valence band 100% bound electron, or you can say 0% free electron. So Fermi level is like the average of both of them, 100% plus 0% divided by 2, 50%. So Fermi level is like an average of both of them. So when you define the work function energy, you define it with respect to bound electron as well and free electron as well. And when you define electron affinity energy, you define it for free electron only. Very, very interesting point. I hope you are enjoying this particular conclusion. And this was your material which I can show here. Okay. So we are not going into the physics. We are understanding by the band diagram. First we understood the meaning with respect to band diagram, and then we understood the meaning, then we understood the physical meaning. So everything is written here. What is electron affinity? Electron affinity is the energy needed to remove an electron from the material when the electron is already in its free moving state. Very important point. Free moving state inside the material. So it is the energy required for an electron to move from the lower state of conduction band to the vacuum energy level. From conduction band to the vacuum energy level. What about the work function? So work function is the energy needed to remove an electron from its Fermi level to the material. It is the energy required for an electron to move from okay, here it is not written. This theory could be better. Okay, so better theory you can write down here, that your work function is defined with respect to free electron as well and bound electron as well. Free electron plus bound electron. So here in the definition what I have written, it is the energy required for an electron to move from the Fermi level to the vacuum energy level. From the Fermi level to the vacuum energy level, that is known as your work function energy. Okay, very, very important. I would say, I would star mark it. They will be used somewhere. Okay. What is your Fermi potential energy? Fermi potential energy is the energy difference between the intrinsic Fermi level and the actual Fermi level of the semiconductor. Intrinsic Fermi level and the actual Fermi level of the semiconductor. It shows how strong the doping is. A larger Q phi f means stronger doping. Larger Q phi f. If Q phi f is larger, that means this gap will be larger. That means stronger doping would be there. Now, chi, phi and phi f are the potential corresponding to electron affinity, work function and Fermi potential energy. Is that clear to you? Chi, phi and phi f are the potential, and Q chi, Q phi and Q phi f are the energy. Well and good. Very simple thing. Very straightforward. Let's do the classification of material. Sir, we already know about the materials. Conductor, insulator and semiconductor. I told you in this chapter conductor will be shown by metal and insulator will be shown by oxide. So I am doing the classification based on metal, oxide and semiconductor. So in the metal you know that conduction band and valence band will be overlapping. This is the lower state of conduction band and this is the upper state of valence band. Both will be overlapping. So in the metal there is no point of showing conduction band or valence band. So in the metal I will always show only the Fermi level. Are you able to understand this point? Basically in the metal there will be more than enough electrons and holes, no? Right? Electron is rich. Metal is rich. In metal there are more than enough electrons and holes. There are more than enough charge carriers. Conduction band and valence band are overlapping. So there is no meaning of showing conduction band separate, valence band separate. Right? So in the metal when I show metal, this is the vacuum energy level. When I show metal, I will only show a Fermi level and nothing else. That's it. I will only show a Fermi level of metal. What about the oxide? What is the meaning of oxide? Oxide means the gap between the conduction band and valence band will be very much large. In the insulator, this is very large, right? The band gap is very large. You know that in the oxide or in the insulator, there is 0% chances of finding free electrons, right? There is 0% chances of finding free electrons. So here 0% chances are there and 100% bound electrons will be there. So when you show an insulator, you only show conduction band and valence band. There is no meaning of showing Fermi level. Are you able to understand what I am saying? Because there are no free electrons, no. The position of Fermi level, what does it tell? The position of Fermi level, what does it tell? The position of Fermi levels tell how much electrons we are having. Where we saw it? Here we saw it. The higher position of Fermi level indicates more electrons. Here there are no free electrons. So why should I show the Fermi level? I will only show conduction band and valence band. Conduction band and valence band. And both are very much far apart. Conduction band and valence band. In the semiconductor, you show conduction band as well, valence band as well, you show the Fermi level as well, and also you show intrinsic Fermi level as well. Because in the semiconductor, some electrons will be there in the conduction band, some electrons will be there in the valence band as well. So based on that, you take an average, that is your Fermi level, right? So when I show the semiconductor, I show conduction band as well, I show the valence band as well, I show the Fermi level as well, and I show the intrinsic Fermi level as well. So this is the whole conclusion of the discussion that we have done. So when I will be talking about metal, I will only show the Fermi level. When I will be talking about the oxide, I will show the conduction band and valence band and a larger gap between them. And when I talk about the semiconductor, I will show the conduction band as well, I will show the valence band as well, I will show the Fermi level as well, I will show the intrinsic Fermi level as well. Okay, if it is a intrinsic semiconductor, then EFI and EF will be having no gap. If it is a p-type semiconductor, then EF will be lower than the EFI. If it is an n-type semiconductor, then EF will be higher than EFI. Say yes or no. All good, all fine, right? So we are talking about metal oxide semiconductor. Now for metal, can you define work function energy? Yes. What is the work function energy? This is the work function energy for the metal. Work function energy of metal. Can you define electron affinity? Sir, there is no conduction band, there is no valence band. So you can say that, sir, work function energy is same as electron affinity, or basically you can say that electron affinity is not defined for the metal, or you can say work function is same as the electron affinity. Both are the same thing. Basically here only Fermi level I am showing, no, here only EF I am showing. So with respect to EF, energy required to get into vacuum, what that is known as? That energy is known as work function energy. So here also I can show work function energy. Yes sir, that will be the work function energy of a semiconductor. Work function energy, so Q phi silicon. Okay, always remember, I will always show the semiconductor by SI. Okay, always I will be showing the semiconductor by SI. Silicon, it could be n-type silicon, p-type silicon, it could be anything. It is not necessary that it is intrinsic only. I is not standing for intrinsic. Okay, this I doesn't mean intrinsic. I am showing silicon. Okay, that means I am talking about semiconductor. M means metal. Can I define the electron affinity as well? Yes sir. Q chi SI. Here can you define work function? No, there is no Fermi level. So what I will define? I will only define electron affinity. Q chi oxide. Is that clear? So this diagram is clear. So why we studied the classification, is that also clear to you? We studied the classification metal oxide semiconductor, right? In metal, conduction band and valence band are overlapping. So I will only show the Fermi level, because there is no meaning of conduction band and valence band here. A lot of free electrons are there. All the free electrons are present on the Fermi level only. So you can call it conduction band, you can call it valence band, you can call it Fermi level. So here everything is same. It is equals to conduction band only, it is equals to valence band only, or it is equals to Fermi level only. So only one level I show, that is the Fermi level. Talking about the oxide, I show conduction band and valence band, gap is much larger. And talking about the semiconductor, we show conduction band as well, valence band as well, Fermi level as well, and intrinsic Fermi level as well. Everything we show. We can define work function as well, we can define electron affinity as well. Here only electron affinity will be defined, and here your work function will be defined, or you can say that work function and electron affinity are same. All good? All fine? Just one more thing is there. What is that? Whenever you show a semiconductor, sorry, whenever you show an oxide, you always make two lines as well. Sir, what is the reason behind this? No good reason. Okay, there is no good reason that, sir, why do we show these two lines? It's just that this is your conduction band, this is your valence band. Just for showing it, we show it somewhat like this. Conduction band, valence band, and these are separated. Like basically we'll show it like a box when we talk about oxide. Because what we are going to make? We are going to make metal oxide metal or metal oxide semiconductor capacitor. So what will happen? Now these guys will come here. So just to show them separately, we put two lines more. So we will show oxide like a box. Like there is no good reason, there is no physics. It's just that we will show it like this. Metal, oxide, semiconductor, or here metal could also be there. So when they come together, just to show them separately that this was your metal, this was your oxide, and this was your semiconductor. Now if I join them, if I take this guy here and I take this guy here, so if I join them, then what will happen? Like I will be able to differentiate that this side is metal, then this side is oxide, and this side is semiconductor. So when we show the oxide, we show it in a box. No good reason, no physics involved. It's just that this is how we will be showing it. All good? Okay. So I hope you are understanding all the points that we are discussing. This was a work function we have discussed, and then we saw the classification metal oxide semiconductor. Metal we will show by the Fermi level only. Oxide we will show conduction band, valence band. There is no free electron, so no meaning of showing Fermi level. Semiconductor, conduction band, valence band, Fermi level as well, intrinsic Fermi level as well. And this is the vacuum energy level that is taken as a reference. That this is the energy level of the outer world. Okay. We are going to understand metal oxide metal capacitor now. Okay. But the point is both metals are same. Both of the metals are same. So as of now they are lying separately. Basically this is one metal, this is oxide, and this is semiconductor. You haven't joined them. They are lying separately. This is separate. Okay. This is in Jaipur, and metal width should be same, no? This is also metal. So this is in Jaipur, this is in Australia, and this is in America. Okay, this is in USA. So Jaipur, USA, and Australia. All these things are separate. Metal, oxide, metal. What I need to do? I need to join them. So first let's make them separately. This is our metal. You will be having some work function Q phi m. Here also there will be some work function. Both work function will be same. Q phi m. Q phi m. And this is your electron affinity of oxide. Now they are separately. They are separate. And I told you always we will show the semiconductor somewhat like this. We will show the semiconductor like this in a box. Not semiconductor, sorry guys. We will show the oxide in a box. We will show the oxide in a box. Or you can say insulator will be shown in a box. So when I join them together, will there be any electron flow? In the oxide, there are 0 electrons. Don't care about it. Electron flow can happen from metal to metal. But will there be any electron flow? Whatever the number of electrons this guy is having, this guy is also having the same number of electrons. Both of the metals are having same number of electrons. So will there be any electron flow? Absolutely not. So no electron flow, nothing will change. Basically, they will be joined. Simply they will be joined. Like nothing changed. Here, no things got changed. Previously, they were separate, metal, oxide, metal. Now I have joined them. So let's show it by green. Let's show it by yellow color only. So I will fill the yellow color here. I will fill the yellow color. So they were lying separately. Okay. Previously, they were lying separately. When I joined them, nothing happened. No electron flow, nothing. So no Fermi level change, nothing changed here. Everything is as it is. Everything is ditto as it is. And one more thing I would like to tell. These are the device properties. Q phi m, Q chi. So basically, I will write down here only that forgetting about this guy, I am only talking about the work function and electron affinity. They are the device property. They will not change. Okay? They never change. They never change. These are the device property, no? So they never change. Is that clear to you? So this work function will not change. It will never change. Even though if this guy was having more electron, this guy was having lesser electron, no matter whatever the condition is, work functions will never change. This vacuum energy level can be shifted upward or downward, but work function will never ever change. Are you able to understand what I am saying? Like let's just say if this guy goes upward or this guy comes downward, whatever happens, but the gap between the vacuum energy level and the gap between the vacuum energy level and the Fermi level will always remain the same. We will understand this point. Don't care about it. But as of now, you know that this Q phi m and this Q phi m is same. We will understand this point. Don't worry much about it. Okay. Don't worry much about it. We will understand that particular point. But as of now, what you will say? That this Q phi m is same. Nothing got changed here. Nothing got changed. Right? But what if both metals were having different work function? So now we are understanding metal 1 oxide, metal 2 capacitor. Now when you join them, things will happen. What things will happen? This guy is upper. Fermi level of this metal is upper than the Fermi level of this metal. What does that mean? This is having more electrons. So electrons will flow from here to here. Right? So this guy is losing some electrons. That means this guy will become positive. And this guy is getting some electrons. This guy will become negative. Because of that, there will be some internal field that will be developed. But just tell me one thing. Can there be any field inside the metal? No. Inside this metal? No. So the whole electric field will be there inside the oxide. So EOX I will be telling. Are you able to understand what is happening? This guy will lose the electron and electrons will be piled up here. Because this is having more electrons, this is having less electron. When they are, now what I am going to do? I am going to join them. So when they are being joined, what will happen? Electrons will flow from here to here. This side will become positive, this side will become negative. Until what point electrons will flow? Until they become at the same Fermi level. Because you know that at the equilibrium, am I giving any bias? Am I applying any bias? No, I am not applying any bias. All these electron flow is happening on its own because metals are different, no? So in the network analysis, whatever the kind of capacitor you used to study, that was this capacitor. No electron flow, nothing. Like without even applying any bias, I did not give any voltage. This was separate, this was separate, this was separate. I am joining them together. No voltage I am giving. Just as you are joining them, electrons are flowing from this side to this side because here there are more electrons, here there are lesser electrons. Electrons will flow till what point they will flow? Until they become at the same level. So this side will go downward because it is losing the electron and this side will go upward. because it is gaining the electron and they will become at a same level. This guy is going downward, downward, downward. At one point they will become at the same level. Because of that, there has been some electric field that has been developed inside the oxide. If electric field has been developed, then there will be some slope in the conduction band. In the direction of electric field, the slope will be positive. So what kind of slope you will get? This kind of slope you will get. So let me show what will happen, what kind of diagram we will get. So first I am talking about oxide. So if I talk about the oxide, this kind of diagram we will get. This is your oxide. This is your EC. This is your EV. What about the Fermi levels? So Fermi levels have become at the same point. Fermi levels have become at the same point. So this is my EF at the same point I need to make. So they have become at the same point. This is your EF M1. This is your EF M2. I told you one thing. What did I tell you? That these guys will never change. Look, this is the diagram. The diagram is complete. From here you can tell that, sir, there is some oxide electric field has been developed here. This is the direction of that oxide field. So this is your diagram at equilibrium. So there is some slope in the conduction band and valence band of oxide. Along with that, we can show the vacuum energy level as well. So, sir, vacuum energy level will be made somewhat like this. No, it will not be made like this. Why is that so? Because I told you one thing, this gap Q phi m, that has to be remained same. So let's just say if I am saying that this particular gap is Q phi m. This particular gap is Q phi m. Then here the gap has to be more, no? This is Q phi m1. Q phi m1. So you can see here that Q phi m2 is more than Q phi m1. So Q phi m2 has to be more. That means here the vacuum energy level has to be on the upper side. This has to be the vacuum energy level. Is that clear to you? Although it is not that important in the examination, they will not make the vacuum energy level, but sometimes they can confuse you. Till this point, whenever the diagram has come, this diagram has come. They never made the vacuum energy level. But you should also know that vacuum energy level may be shifted, but these guys will never change. Q phi m, Q phi m2, they will never change. Along with that, what all things will not change? Electron affinity will also not change. So if there is some slope here, that means the same kind of slope would be there. Are you able to understand? Like now I can make the diagram in much better manner. What I will do? Now point has been understood by everyone. The point says that till this point it is fine, then this slope and then this diagram. So this will be your vacuum energy level. From now onwards I will not make the vacuum energy level. As of now I am making the energy level just to give you satisfaction that your work function here and your work function here, they are not changing. Work function is not changing. Electron affinity is also not changing. That is also same only. All the points you can take, all the points, at all the points electron affinity is still the same. This height is still the same. So electron affinity is also not changing. Right? This Q chi, this is also not changing. The vacuum energy level may be made like this. So from now onwards you will not make the vacuum energy level. Okay? Because you have understood that whatever the slope in conduction band, I can see the same slope in vacuum energy level will also be there, and after that I can simply make the diagram like this. So no need to make the vacuum energy level from now onwards. I will only make these guys, EFM, EFM and oxide. Is that clear to you? Okay. So what really happened here? Electrons flow from here and going towards the metal 2. That means metal 1 has become positive and metal 2 has become negative. So metal 1, this was your metal 1 and this is your metal 2. So metal 1 has become positive and metal 2 has become negative without even applying any external bias. Without any external bias. Without any external bias. just because of work function difference. Work function difference. Right? Is that clear to you? This Fermi level was above, this Fermi level was below. Electrons flow from here, this became positive. So this particular metal side became positive, this particular metal side became negative, this was positive, this was negative, without any external bias, just because of the work function difference. This is happening. Right? Sir, when we study network analysis, we did not used to see this kind of scenario because you used to use same metal. If you are using same metal, then metal in between oxide and then semiconductor, no charge would be there, zero charge, because nothing happened. No electron flow was there, no electron flow here, no electron flow, no electron flow. If no electron flow, that means no positive charge, no negative charge, that's it. So this kind of capacitor we used to study. But if I am using different kind of metals, electron flow could be there, positive negative charge could be built up, and without even applying some external bias, you are getting some positive charge here, negative charge here. Because of that, there is some band bending. So can I say what is happening here? There is some band bending is taking place. Now, before using this particular capacitor for any operation, like I need this capacitor for some operation. Let's just say I apply 5 volt across this capacitor. This capacitor I am using, I apply 5 volt. I applied 5 volt. So actually you applied 5 volt, but this capacitor, let's just say because of this work function difference, this capacitor got charged for 1 volt. This capacitor got charged for 1 volt because of that work function difference. Right? So already it was having 1 volt. You applied 5 volt, it will serve the purpose of 6 volt. Like you cannot say, sir, this is 5 volt, so this will become a 5 plus 1, 6 volt. So you will say that, sir, KVL is not valid. KVL is not valid. How you can say 5 volt, 6 volt here? This is what I am saying. Basically, if you need to make it work for the operation of 5 volt, then you only need to apply 4 volt because 1 volt charge it is already having. Some charge it is already having. Are you able to understand this point? What I am saying? I want to work it on the operation of 5 volt. So I need to give the charge equivalent to 4 volt only. So whenever you use a capacitor where metal is different, these two metals are different, first you will get the flat bands. What is the meaning of flat band? That means this band bending should not be there. Why this bending is there? Why there is a slope in conduction band? Because of the built-in electric field, right? So I need to kill this particular electric field. So what I need to do? I need to kill this electric field. There is an electric field in this direction. If I apply from my end, if I apply an electric field in this direction, then what will happen? Both of the electric field will cancel out each other and total electric field will become 0. So to get the flat band, what is the meaning of flat band? No slope in EC, EV or EFI. This is the meaning of flat band. So if I need to get the flat band, already this is charged to some potential. What I need to do? I need to apply some negative charge across it. Say yes or no. So I am showing the positive battery. I am showing the positive battery and I am saying that I am applying a positive battery of Vg volt. Positive battery of Vg volt. But I know that this Vg has to be negative. Say yes or no. Because already this plate is having positive charge, this plate is having negative charge. What I will do? I will apply some negative charge here. Both we will develop positive charge here and both negative and positive charge will cancel out each other. How much positive charge I need to apply? Can anyone think of it? Sir, because of this electric field, first thing is that, sir, why you made this slope constant? So inside the electric field, the slope will be constant. We will see it. Inside the electric field, slope will be constant. We will see it. In the next lecture, we will see it. Okay. So that's why I did not show it somewhat like this. I showed the slope like this only. Why it is not going like this? Sir, why the slope did not go like this? Sir, why the slope did not go like this? Slope went like this only. Why is that so? Because electric field is constant. Why it is constant? We will see that. Just tell me one thing. How much is this difference? How much is this difference? This difference is Q VOX. Can anyone tell what is Q VOX equals to? Sir, Q VOX is equals to Q phi M2 minus Q phi M1. Forget about this vacuum energy level. Just think, no, this guy is going downward, this guy is going downward, and this guy is going upward. One guy going downward, one guy going upward. Both became at same place. If I say this guy is not moving upward, if I say only this guy is going downward, if this only this metal is going downward, this Fermi level is going downward, then how much down it needs to go? This much down it needs to go, no? And what is this much distance? This much distance is nothing but Q phi M2 minus Q phi M1. So what is this much distance? So as much as this has gone down, this has gone up. So the slope is the same. Like this length is the same only. No, I hope you are able to understand. This you need to visualize. In PN junction as well, we have done this particular thing. This Fermi level goes downward, this goes upward. So this node is shifting downward, and this node is shifting upward. Right? This is going upward, so this node is shifting upward. This node is going downward, this node is going downward. So this node has went upward, this node has went downward. So there is some gap. Q VOX gap is there. How much is that? How much is that gap? Q VOX gap is equals to Q phi M2 minus Q phi M1. I need to write down the positive value. This is more, this is less. So this gap is Q phi M2 minus Q phi M1. So can anyone tell how much voltage would have been developed here? What will be the value of VOX? Sir, VOX would be Q get cancelled out. Sir, phi M2 minus phi M1. So the voltage that would have been developed here, that was phi M2 minus phi M1. So to kill this particular voltage, how much VG I need to apply? Here it was phi M2 minus phi M1. To kill this particular voltage, I need to apply phi M1 minus phi M2. Opposite of that, or I can say, here I can write down that my VOX developed was, what was developed? Phi M2 minus phi M1. And what I need to apply? Negative of phi M2 minus phi M1. That means I need to apply phi M1 minus phi M2. This much I need to apply. Is that clear to you? So I can write down VG is nothing but phi M1 M2. What will be this value? This value will be negative only. This value will come out to be negative only. Because phi M1 is lesser than phi M2. So here I need to apply negative potential, here I need to apply positive potential. I hope it is clear. As much as this has gone downward, as much as this has gone upward. So this node is going upward, this node is coming downward. So this Q VOX is nothing but equals to Q phi M2 minus Q phi M1. So here positive potential that has been developed, that is nothing but phi M2 minus phi M1. Because phi is the potential, Q phi is the energy. So I need to apply the negative one, phi M1 minus phi M2 I need to apply. With respect to this question, it will be more clear. So think about it and solve it. I hope you will be able to solve. Very easy question it is, not tough. Think about it and try solving it. You will be able to solve it. This is actually a very, very important point. In MOSCAP as well, the same thing will come into action. At that time, I will simply write down the formula because you will be able to understand all the theory on your own. Okay, so we are building up the theory for the next lecture. So solve this question, you will be able to solve it. Okay, so let me take a break. I will come back after drinking some water. So two kind of metal we are using, metal 1, metal 2. Both are having different work function. What will happen? From one particular metal, electron flow will take place. So you draw the diagram. First you draw the vacuum energy level. This is your vacuum energy level. Inside there will be oxide, that I don't care. There will be metal 1 and metal 2. Metal 1 and metal 2. Metal 1 is having 4.20 and metal 2 is having 5 electron volt. That means this gap will be lesser. And this gap will be more. Right? Okay. So who is having more electrons? This guy is having more electrons because this is upward. This is EF1 This is EFM2. So electrons will flow from here to here. So this guy has become positive and this has become negative. So in between there will be oxide that I did not know, that I did not make. So here there will be some electric field will be building up, right? So can I write down what will be your VOX? Sir, VOX will be nothing but 5 volt minus 4.2 volt. That will be 0.8 electron volt. Or better, I should write down what will be your QVOX. QVOX. That would be, sir, Q5M2 minus Q5M1. Sir, 5 electron volt minus 4.2 electron volt. That would be my QVOX or EVOX I can write down. Because here Q has become electron, no? So this and this will get cancelled out. So VOX has become 0.8 volt. So this was my metal 1. Metal 1. In between there was a oxide. And this was your metal 2. This was your metal 1. This was your metal 2. Okay, so this side has become positive and this side has become negative. So how much voltage have been developed? 0.8 volt. So if I make the capacitor will look somewhat like this. This is your metal 1. This is your metal 2. This is 0.8 volt. Right. First question, what they are asking? At equilibrium, what is the magnitude of charge per unit area? Charge per unit area they are asking. Induced on each plate. So on metal 1, how much charge would be there? Can you find out the charge? What will be the charge? Charge will be voltage divided by the capacitance. Oh, sorry. Q equals to CV. Capacitance multiplied with the voltage. Is that clear to you? Charge I need to find. No. Metal 1 will be positively charged. Metal 2 will be negatively charged. So what is the potential that has been developed? That I already know. What will be your capacitance? Per unit area you need to find. What is the value of capacitance? Sir, capacitance is epsilon A divided by thickness. This distance is thickness only, no? TUX. So capacitance per unit area, that would be this one. So this I can do, or simply I could have put one thing here, epsilon OX area divided by TUX multiply with the voltage. So Q by A, that would be epsilon OX divided by TUX multiply with the voltage. So this is your charge per unit area. That is coming out to be epsilon OX TUX multiply with the voltage. What is epsilon OX? Relative permittivity is given as 3.9. What is oxide thickness given? Oxide thickness is 10 nanometer. So this is 3.9 into 8.85 into 10 to the power minus 14 into how much voltage has been developed? 0.8. Now this is interesting. TOX equals to 10 nanometer. 10 nanometer can be written as 10 to the power minus 8 meter, and it can be written as 10 to the power 6 minus 6 centimeter. Say yes or no? So I will always put all the calculation in centimeter. So everything is going in centimeter. This also I put in centimeter. Voltage is voltage only. So this also I will put in centimeter only. So 10 to the power minus 6 I will put here. So what answer you are getting? And to the power minus 8 would be there, no? So 3.9 into 8.85 into 0.8. So 27.6 into 10 to the power minus 8 coulomb per centimeter square. So this much charge have been there. So on metal plate 1, the charge is plus 27.6 into 10 to the power minus 8 coulomb per centimeter square. On metal plate 2, the charge is minus 27.6 into 10 to the power minus 8 coulomb per centimeter square. Is that clear? Now what they are asking? In the second question, what they are asking? What voltage should be applied to metal 2 with respect to metal 1? To metal 2 with respect to metal 1. So what is our condition? Can anyone make here? The condition is, sir, this one. This is our metal 1 and this is our metal 2. But sir, applied voltage is 0.8 volt. Not applied voltage, sorry. This is the voltage that we are getting. What I need to do, sir, if I need to get the flat band, what I need to do? Sir, I need to apply minus 0.8 volt here. I need to apply minus 0.8 volt here. But your answer would be minus 0.8 or plus 0.8. Think about it. Voltage applied on the metal 2 with respect to metal 1. So on metal 2, on metal 1 you are having positive charge and on metal 2 you are having negative charge. So on metal 2 what you need to give? You need to give the positive charge, no? Are you able to understand this point? So metal 2 would be connected with the positive terminal, metal 1 will be connected with the negative terminal. So metal 2 is positive, metal 2 is more positive than the metal 1. Is that clear? So answer will be 0.8 volt here. So with respect to what they are asking, that is our matter of concern. Is that clear to you or not? So our flat band voltage, where I am saying with respect to metal 2 to metal 1, that would be plus 0.8 volt. So formula and all we will not mug up. We will go by this diagram in very quicker manner. We will be able to draw the diagram. You would see that this is having higher work function. That means this side will become positive, this side will become negative. This diagram I will make. With respect to this diagram, I will be able to know that I need to apply 0.8 volt, but metal 2 will be positive, metal 1 will be negative. So what they are asking, voltage, what voltage should be applied to metal 2 with respect to metal 1? To metal 2 with respect to metal 1. So that would be plus 0.8 volt. Is that clear to you or not? Okay. So that's a very important point that we have seen. Along with that, we can make the band diagram as well. So what we are doing, band diagram. So basically we are drawing the band diagrams. So first we will draw the band diagram before achieving the flat band. So before achieving the flat band, what will be the condition? This side will become positive, this side will become negative. That means in the oxide, there will be some slope like this. In the oxide, there will be some slope like this. And Fermi levels will be at the same position. This will be the Fermi level positions. Okay. Before achieving flat band. If I need to achieve flat bands, then what will happen? Before achieving flat band, what is the condition? This side has become positive, this side has become negative. So there is an electric field that has been set up here. This is your EC only, this is your EV, this is your EF M1, this is your EF M2. If I need to achieve the flat band, what I will do? This side I will connect to negative and this side I will connect to positive to achieve the flat band. To achieve flat band. That means metal 1 is connected to negative and metal 2 is connected to positive. If something is connected to negative, the Fermi level goes upward. So what will happen? Flat band will be achieved. Flat band will be achieved. Flat band here will be achieved. This will become EC, this will become EV. So this will be the condition. Flat bands are achieved. EC, EV, flat bands are achieved. But where you have applied negative, this side will go upward. Is that clear to you? this side will go upward and this side will come downward. Where you apply positive, that side comes downward. Where I have seen it, sir? Sir, you have seen it here. Positive side Fermi level goes downward. Negative side Fermi level goes upward. Negative side Fermi level goes upward. So wherever you have applied positive, that side comes downward. So I need to show more downward here. I will show it somewhat like this. So this side comes downward where I have applied positive. So this side comes downward where I applied positive, and this side goes upward like this. Okay, well and good. So this is after achieving flat band. Look, it doesn't mean that current is flowing here. Like you will say that sir, this guy has come up, this guy has gone upward, and this guy has come downward. So current is flowing. No, these guys are still flat. This is also 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 flat. So this is the meaning of flat band. Current is still not flowing. If current was flowing, let's just say in the metal, if some current is flowing, and let's just say the current is flowing in this direction. So there will be Fermi level. It will be made like this. If current is flowing in this direction, then Fermi level will be made like this. This is how the Fermi level will be made. Current is not flowing. In the capacitor, current is not flowing. No. Are you able to understand this point? If I am connecting this battery, then minus 0.8 volt will be exposed here. It doesn't mean the current is flowing. No, current is not flowing. Current is still 0. Is that clear to you? So here, if I say what is the current? What is the current here? Current is still 0. What is the current here? Current is still 0. And surely in the oxide, current is still 0. In our whole chapter, current will always be 0. There will never be a current flow. In the whole chapter, in whole MOSCAP, we will never talk about the current. Current will never flow. Inside the capacitor, current can never flow, no? So current flow, we will never talk about it. Always these guys will be flat. Although they can be shifted upward or downward, because positive bias, if you apply, they goes downward. If you apply negative bias, they goes upward. So positive, negative, they can go upward, they can go downward, but they will never have a slope. In this whole chapter, the slope of Fermi level will always be 0. It will always be 0. And what it will show? It shows 0 current. Current will always be 0. Now, a very interesting doubt I will ask you. Okay? And you guys need to answer on your own. Just think about it. Those who have studied network analysis in a good manner, they will be able to think about it. So, what is my question? My question is, across the capacitor, I say that if you apply positive bias, then what will happen, sir? Here positive charge will come. And if you apply the negative bias, here sir, negative charge will come. Okay? Right? This is what you say. Here negative charge is coming. On this side, negative charge is coming. What does that mean? How negative charge would have come? How negative charge comes? If electron goes inside you, if electron is going inside you, then only negative charge would come, no? And if electron is flowing out of you, then positive charge would come. If you want to become positive, what does that mean? You need to flow out the electrons. What will happen? You will become positive. If you want to become negative, that means you need to take the electrons. You will become negative. So that means if you are saying that on this particular plate, some positive charge have come. On this particular plate, some negative charge have come. That means some electron would have flown out, some electron would have got in. Right? That means electrons are flowing. Here, some electrons are flowing. If electrons are flowing, what does that mean? In this direction, if electron is flowing, then there will be some current as well. In this direction, if electron is flowing, there is some current as well. If this current is there, then this current will also be there. Then this current will also be there. Then if this current is there, then this current will also be there. Then this current will also be there. So from the battery, there has to be a current. Basically, if I am saying that initially I was having no voltage, no charge, nothing. When I connected some battery, some charge came here. If some charge have come, if something has happened on the metal plate, that means surely current has flown. Where is that current? We say no, like if I ask you what is the current at 0 plus, what will be your answer? Sir, 0 ampere. right? Because sir, voltage is constant, I equals to C dVc by dt. Sir, voltage is constant, so this will become 0, so current is 0. But there is a impulsive current. Current at 0 plus is 0, but current at 0 is not 0. There will be a impulsive current of CV delta T. Here I am not going to explain the whole point. In network analysis, we have understood this point. Always there will be an impulsive current. The current at the steady state is 0. But if you are saying that, sir, some positive charge have come here, some negative charge have come here, sir, some electrons have flown, that means current was there, but that was impulsive for 0 second. That means just as you connected the battery, very large current was flowing, and because of that, some positive charge and negative charge have come. After that, the current was gone. Just as you connected the battery, the current flew, gave the positive negative charge, and then went away. So this current is the unsung hero. Came, gave something, went away. So current was there, but only for 0 second, that you did not even notice. There was some player in your team who contributed a lot, but you never even noticed that. The current is the same thing. Current was there. Current flow took place. Sir, how that current took place in the air? Let's just say here I am using air. There is nothing in between. Still, sir, current was flowing in the air. Yes, that point we understood in EMFT. So those who have studied EMFT, network analysis, analog electronics in a good manner, then they would know that how the current was flowing in the air because of that displacement current. Displacement current, conduction current, all the points we have discussed, right? In a very, very deep. Capacitor is very deep, like electron is nothing but capacitor only. VLSI is capacitor. So all the analysis, if someone asks you anything about the capacitor, you should be able to tell. Forget about the student, 99% of the GATE educators will not be able to tell about the capacitor if I ask them one good question. Because someone says that we teach analog, someone says that we teach EDC, someone says that we teach network, someone says that we teach EMFT. No one studies all the subject. As an educator or as a student, when we say we are electronic student, we are into electronics, that means we need to have knowledge of all the subject. Okay, it doesn't mean one subject, two subject. When you go into the industry, let's just say I become an analog engineer, it doesn't mean that only the knowledge of analog is required. EMFT can be used anytime, communication can be used anytime, EDC can be used anytime. So this discussion, like this is not the matter of discussion for EDC. But I'm just telling you one thing, like if some student is thinking that, sir, how this positive charge came, how this negative charge came, because of the impulsive current, then another doubt would be that, sir, how one plate was there, another plate was there, in between there was a air. Sir, how this current flow? Current flow because there was an electric field. Because of the electric field, because of the changing electric field, there was a displacement current. So all these points you will study in EMFT. And because of that, current was also flowing inside the air as well, in the wire as well, but that current was there only for 0 second. And because of that 0 second current, because of that current in 0 second, here positive charge came, here negative charge came. Okay. I should not write down I0, I should write down IT equals to CV delta T. This would be the correct statement. So if someone like think that, sir, how the charge came into action, so this is how the charge came into action. Although this is not a matter of concern for this particular lecture, but I hope you are able to understand this particular thing as well, that the current was there, but only for 0 second. After that, the current was 0. So here if someone asks you at steady state, what is the current? Sir, 0 ampere. Was the current always 0? No. There was an impulsive current as well. Okay, so all this discussion we have done. Flat band also we have understood here. For achieving the flat band, after achieving the flat band, this will be the diagram, because here I am applying negative bias, here I am applying positive bias. So all these diagram we are making at the steady state. At steady state, current is 0. Current is 0, current is 0. Here also current is 0. So at steady state, current is 0. No slope, nothing. No slope in the Fermi level. So current is 0. It's just that here I have applied negative, here I apply positive. So positive means coming downward, negative means going upward. Flat band also we have achieved. Okay. Few more points we need to see from the EMFT only. So boundary condition we need to see. And then we need to talk about metal-oxide-metal semiconductor capacitor. Okay. And then we will see the parallel series combination of capacitor. Hardly 10-20 minutes of discussion is left in this lecture. So let me take a break, because it's been 2 hours since I am directly recording. I did not even take any break. So I will take some break. Then we will discuss these very small concept of boundary condition and this metal-oxide-metal semiconductor capacitor and series combination of capacitor. And then we will end the lecture. In the next lecture, we will move to MOSCAP. So all these band diagrams and everything, whatever we are discussing here, the same kind of thing we are going to discuss in MOSCAP as well. But this metal-oxide-metal capacitor is also very important. because people know that, even the professor who are setting up the question paper, they also know that everyone is studying MOSCAP, but they don't know why MOSCAP came into action. So who knows, they frame a question on metal oxide metal capacitor only. Previously we used to study PN junction, right? But no one used to study N plus N junction. In GATE 2017, for the first time N plus N junction came into action. So PN junction requirement started from here, no? So MOSCAP requirement started from MOM. So we need to study this one as well, then we move here. Is that clear to you? Okay. So we will study MOM, then we will move to MOS. It will be a cakewalk. Okay. So let me take a break and then I will come back. We will discuss these simple points. That is boundary condition. Very simple it is. So let me take a break and I will come back. Yeah, hi everyone, welcome back. So we have understood about metal oxide, metal semiconductor, all the basic point, whatever we need to understand, that we have understood. So all these points will help us in the next lecture for MOSCAP. Now this is also one of the point which will help us in the next lecture. What is this point? This particular concept is known as boundary condition, which we study in EMFT, but here it will be used. First thing is that, sir, what is the meaning of boundary? Boundary means separation. Basically, you studied about metal oxide metal semiconductor, right? This was metal, this was oxide, and this is metal. Let us say I am standing here. When I move from here to here, what will happen? First I will see, sir, oxide, 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 and suddenly, sir, metal. When I came here, what did I see? Metal. So from oxide to metal you are moving. So this is known as boundary. So boundary is not like a physical barrier. It's not a physical barrier. Just that when your material is changing, here your material was oxide, here your material is metal. Is that clear to you? So this is the meaning of boundary. So what I am saying, let us say this is x equals to 0. So for x less than 0, you are having a material 1 which is having relative permittivity of epsilon R1. And for x greater than 0, you are having material 2 which is having relative permittivity of epsilon R2. Okay, so this is the scenario. Now, in material 1, let's just say there is an electric field. So whatever the direction of electric field, very, very important point. Whatever the direction of electric field you are getting in material 2, after the boundary, the same direction of electric field you will get in material 2 as well. So at the boundary interface, the direction of electric field is consistent. Sir, what about the magnitude? So relation for the magnitude is, let's just say here the electric field is E1 and here the electric field is E2. So direction of E1 and direction of E2 would be same. So I can write in this manner, E1 cap would be equals to E2 cap. Cap is just showing the direction. Okay, so direction of E field will be same. What about the magnitude, sir? So magnitude relation will be followed by this. Epsilon R1 E1 would be equals to epsilon R2 E2. So this epsilon R1 E1 is known as flux. This is known as electric flux density. So statement is given by, at the boundary electric flux density is constant. But that statement you don't need to remember. What you need to remember, the direction of electric field will be same. Along with that, what about the magnitude? Sir, epsilon R1 E1 multiply of both of them would be equals to epsilon R2 E2. That's it. Okay. So this is something that you need to remember. So these 2 points will you be able to remember? Direction of E field would be same. Magnitude epsilon R1 E1 would be equals to epsilon R2 E2. So this has been written here. The perpendicular component, and what do you mean by perpendicular component? So this is the boundary, this is perpendicular, right? So these are the perpendicular component. So perpendicular component of electric field maintains the same direction. Perpendicular component of electric field maintains the same direction as it crosses from one material to the other material. From one material to another material. Okay, all good. Another point we are going to see, what we are seeing now, metal oxide metal semiconductor. So basically first layer is metal, then I am having oxide, then I am having metal, and then I am having semiconductor, or any kind of material it can have. Not only semiconductor, any kind of material we can have. So let's just say this I am keeping as ground, and here I am applying some positive voltage. Here I have applied some positive voltage. Negative voltage also I can apply. Some positive voltage I am applying here. Now what this positive voltage will do? Positive voltage will say that with respect to this positive voltage, I am developing some Q charge or some Q1 charge. So what do I require? I require minus Q1 charge. So this guy is saying that I require minus Q1 charge. So here there are two guys, metal and semiconductor. What metal will say? Metal will say that, sir, I am having more than enough charge carriers. You require minus q1 charge, I will give you minus q1 charge. He will say no need to look at the semiconductor or any other material, whatever the material you are having. What metal will say, this guy will say that, sir, I need plus q1 charge. This metal will say, I will provide you minus q1 charge. No need to do anything with the semiconductor. So nothing is happening inside the semiconductor. If this particular layer is grounded, so if this is zero potential, then this will also become zero potential only. Is that understandable to you? Like nothing is happening inside the semiconductor, semiconductor remains as it is. Metal, oxide, metal, and then semiconductor we are having. Because metal is having a property that, sir, whatever the charge you require, I am able to give you. If you require plus q1, I will give you minus q1 very immediately. No need to look at the semiconductor. If you require plus q2, I will give you minus q2 very immediately. No need to look at the semiconductor. What does that mean? That means your metal, oxide, metal, semiconductor, capacitor is nothing but metal, oxide, metal, capacitor only. And what will be its value? So that value can be given as epsilon ox multiplied with the area divided by tux. So here also you are having a constant capacitance only. Is that clear to you or not? So if I draw Vg versus, if I call this potential as Vg, so if I draw Vg versus capacitance plot, if I draw Vg versus capacitance plot, so here also the equivalent capacitance, whatever the equivalent capacitance that we are getting, that is also constant. And this capacitance we are calling as COX. And COX is epsilon OX multiplied with a TOX. Okay. And we can, like sometimes we will talk about what is the unit of this capacitance here? Farad. Okay. Yeah, Farad की spelling क्या होती है? Unit of this capacitance is Farad. I guess this is the spelling. Farad. Okay. So sometimes we will be talking about capacitance per unit area. Capacitance per unit area. What that would be? Epsilon OX divided by TOX. What will be its unit? Farad per centimeter square. Because in EDC I told you everything we deal in centimeter. So Farad per centimeter square. Well and good. Sometimes we will talk about capacitance per unit area. Because our major matter of concern is epsilon OX and TOX only, not the cross section area. Cross section area for the oxide, for the metal, for the semiconductor, for everyone it would be same. So a lot of time in the examination you would see that you would find out the capacitance per unit area, not the complete capacitance. Okay. So here also the same thing we are getting, but important point is the metal, oxide, metal, semiconductor capacitance behave as metal, oxide, metal capacitor only. Because whatever the change in charge that you are applying here, the same number of electrons or whatever the positive charge, negative charge you require, metal will be able to provide that. That means electric field lines will be somewhat like this only. Electric field lines would be somewhat like this. That's it. The metal will say that I will not let you penetrate through me. Not like this. I will not let you penetrate through me. Whatever the positive charge you require, I am able to provide you the same amount of negative charge. No need to look at the semiconductor. So no impact of semiconductor is there. Absolutely no impact of this semiconductor. So if 0 voltage were there, effectively this point has become 0 voltage. Because what is this semiconductor? Let's just say it is p-type semiconductor or n-type semiconductor. It will be electrically neutral, right? If it is p-type, if it is n-type, then it would be somewhat like this. If it is p-type, then it is like this. Or if it is intrinsic as well, that means no positive or negative charge would be there. That means it will be effectively electrically neutral. Positive, negative cancelling out each other. Positive, negative cancelling out each other. So it will be electrically neutral. That means if this is the 0 volt, then this would also be a 0 volt only. So effectively 0 volt have reached here. Is that clear to you? Everything is absolutely understandable. Say yes or no. Okay. So this is your metal, oxide, metal, semiconductor capacitor, which behaves as metal, oxide, metal capacitor only. And you know that in metal, oxide, metal capacitor, we get a constant capacitor, that is epsilon OX divided by TOX multiplied with the area. And this will be very, very important for you when we study the next lecture. In MOSCAP, we will get this condition a lot of time. There I will say it is working as a metal, oxide, metal, semiconductor capacitor. And then I will say MOMS capacitor is equals to MOM capacitor. And the capacitance value is this one. So in the next lecture, it will be useful. This thing you already know. Series combination of capacitor. How I can write it down? C1 C2 upon C1 plus C2. I hope you know this thing from basic network theory. Just one more thing I would like to tell you, that this equivalent capacitor would always be lesser than C1. and it would always be lesser than C2 as well. Basically, this value will always be lesser than C1, it will always be lesser than C2. This much network analysis, I hope you know it. Is that clear to you? Right? Basically, how do you get this 1 by CAB? 1 by CAB is nothing but 1 by C1 plus 1 by C2. Right? So CAB comes out to be C1 C2 upon C1 plus C2. If this C2 was infinity, then CAB would be equals to C1. If this C2 was infinity, that means this part would be 0, so CAB would be equals to C1. If this C1 was infinity, then CAB would be equals to C2. But both are there. That means CAB would be less than C1, CAB would be less than C2 as well. The parallel combination of anything, whatever the resultant that you get, that would be lesser. You can take any value. Let's just say C1 is 3 and C2 is 2. So do the parallel combination. 3 into 2 divided by 3 plus 2. What that would be? 5. So 6 by 5. What that would be? 1.2. So 1.2 is less than 2 and 3 as well. So verified as well. Okay. Very simple thing. Now what if between two metallic plates, here there is some boundary. Before this boundary, let's just say for D1 distance, we are having a material having relative permittivity of epsilon R1. And for D2 distance, we are having a material having relative permittivity of epsilon R2. So what will be its equivalent capacitor? So equivalent capacitance would look somewhat like this. So it's like two capacitor, no? Again, it's like two capacitor only. I can denote it like two capacitors. This is point A, this is point B, this is like capacitor C1, this is like capacitor C2. So capacitor C1 would be epsilon R1, epsilon naught A divided by D1, and C2 would be epsilon R2, epsilon naught A divided by D2. So your CAB would be C1 C2 upon C1 plus C2, right? This is also basic network analysis. I hope you know this much of thing. If you don't know it, then we have understood here. So this is our capacitor C1, which is having distance of D1 here and relative permittivity of epsilon R1. What about this one? This is having distance of D2 and having relative permittivity of epsilon R2. Okay, so C1 C2 upon C1 plus C2, CAB we are getting. C1 is epsilon R1 epsilon naught multiply with A divided by D1. C2 is epsilon R2 epsilon naught multiply with A divided by D2. So CAB is C1 C2 upon C1 plus C2. I hope that is understandable, and this is the end of this lecture. So what we understood in this lecture, main concept that we understood was, one concept was of flat band voltage. This is also very important. This concept will again come back in metal oxide metal semiconductor. At that time I will not be talking much about it. Okay, I will directly say the electrons will flow from here to here. This will become positive, this will become negative, electric field would be set up. Here we were using metal, oxide and metal. So electric field was set up only in the oxide. But what if I use metal oxide semiconductor? Inside the metal there has to be zero electric field. What I am saying, inside the metal there has to be zero electric field. Inside the metal there has to be zero electric field. But inside the semiconductor electric field can be there. So semiconductor will drive some electric field, and that electric field will be helpful for us to get a voltage dependent capacitance value. Okay, so we will see that in the next lecture. I hope you are able to understand why I picked why I started from metal oxide metal semiconductor. Those who are studying it for the second time, they would realize that what kind of depth we have seen here. Okay, so their whole memory about the MOSCAP would have been refreshed till now. You would have everything refreshed in your mind that yeah, this is how we used to study MOSCAP. All the reasoning would be clear. Next lecture you will study and everything would be crystal clear to you. All good? All fine? So let's meet in the next lecture. Thank you very much. Yeah, hi everyone, welcome back. So in the last video we were studying about metal oxide metal capacitor. In this video we need to start our chapter, that is metal oxide semiconductor capacitor. So first layer will be metal, second layer oxide, third layer will be semiconductor. So MOS capacitor we need to study. Okay, so let's do some nomenclature. Nomenclature we are doing. So this particular node is known as gate. So gate is directly connected to metal. Okay, so that is known as gate, and this particular node is known as body. So body is directly connected to the semiconductor. Okay, so the node which is directly connected to the metal, that is known as gate, and the node which is directly connected to the semiconductor, that is known as body. Is that clear? You will be able to remember that, gate and body, right? Why do we call it gate? It will be clear in when we study MOSFET. Okay, when we study MOSFET, it will be clear why the name gate was given. Okay, and this is known as body. Now this is your oxide semiconductor interface, no? Like this particular line. I am talking about this particular line. This particular line is your oxide and semiconductor interface. So sometimes I will be calling this line as surface. So surface could be anything. This could be surface, this could be surface, or anything could be surface. But when we use the word surface, that means I am talking about oxide semiconductor interface. That means when they are joining, at the point where they are joining, that is known as oxide semiconductor interface, or you call it surface. Okay. Semiconductor, here it is known as substrate. Let's just say I am using p-type semiconductor, so I will call it p substrate. P substrate. The word that is used, the word that we use, that is substrate. Okay, p substrate or n substrate. So here I will just write down substrate. It could be p or n, whatever it is. P/n substrate. Either I will be using p-type semiconductor, or I will be using n-type semiconductor, whatever I use. The most of the theory we will study with respect to p-type semiconductor, so let's use it p substrate. We will study about n substrate as well, but the analysis will be ditto same. Ditto, exactly the same analysis we will see. So let's call it p substrate as of now. Now, whatever the phenomena that would take place near the surface only. Near the surface, what is the meaning of surface? Surface means oxide semiconductor interface. So whatever the phenomena that would happen near the surface only. So this particular part, I will call this particular part as bulk. So this much of part, I will be calling this much of part as bulk. Okay. So if you leave the surface, some place near the surface, if you leave, whatever the rest of the part that you get, that particular part is known as bulk. So is the nomenclature clear? Metal oxide semiconductor, the node which is connected to metal, that is gate. The node which is connected to semiconductor, that is body. Same oxide and semiconductor interface is known as surface. If you leave the surface, whatever the part that is remaining, that is known as bulk. And semiconductor here would be given a better name, that is substrate, p substrate or n substrate. Is that clear? All fine. Can I draw the energy band diagram of metal? Yes. Can I draw the energy band diagram of oxide? Yes. Can I draw the energy band diagram of semiconductor? Yes. So when they are separate, metal is separate, oxide is separate, semiconductor is separate, I have drawn the energy band diagram of metal, I have drawn the energy band diagram of oxide, and I have drawn the energy band diagram of semiconductor. We already know about all these band diagrams. In the last lecture we have studied it, right? Now, who is having above Fermi level? This is having above Fermi level, and this Fermi level is below. So Fermi level of metal is above, or Fermi level of metal is at higher position than the Fermi level of a semiconductor. What I am using? I am using p-type semiconductor. So what will happen? Sir, here there are more electrons. If there are more electrons, then what will happen? The electrons will flow from here to here, right? So if electrons are flowing from here to here, what does that mean? This particular part will become positive and this particular part will become negative. That means there will be one electric field set up in this direction. Now let me know one more thing. In this p-type semiconductor, what you are having? You are having holes as well and you are having electrons as well. Let's just say the doping was 10 to the power 16. That means you are having 10 to the power 16 holes and you are having 10 to the power 4 electrons. Now if electrons are flowing from here to here, what will happen? Electrons will increase. In the p-type semiconductor, electrons will increase. But you know that the semiconductor is at, or you can say the material, whatever metal oxide semiconductor we are using, that is at equilibrium. We are not applying any external bias, we are doing nothing, no current is flowing. So things are at equilibrium. That means N into P equals to Ni square will always be valid. Mass action law will always be valid. So I am saying that electron concentration is increasing. Let's just say electron concentration got increased and it has become 10 to the power 5. That means hole concentration will go down. It would become 10 to the power 15. So if this is the gap when your electron concentration is 10 to the power 16. So this was your gap, what we used to call it? Q phi F. Fermi potential. Fermi potential energy, you can say. So near the surface, when you join them, near the surface, what will happen? Sir, hole concentration will go down because electrons are coming. Since electrons are coming, hole concentration is going down. Is there any current flow? No. That means this Fermi level cannot change. So let's join them. What we are doing? We are joining them. So when we join them, how I am joining it? So let's check that. So this is our oxide. This is our oxide. Okay. This particular area will be of metal. This is our oxide, and this will be our semiconductor. So when you join them, this EFP will not change. Nothing will happen with EFP. Only one thing would happen. What that would happen? Sir, this side would go downward because it is losing the electron, and this side would go upward because it is gaining the electron. More electron means going upward. This particular side will go downward, and they will keep on moving until they become at the same level. So they will become at the same level. This is your EFM. This is your EFP. They have come at the same level. But there will not be any bending in the Fermi level because there is zero current. I told you in the whole chapter, these Fermi levels will never bend because current is zero. Now you know one thing, that electrons are flowing from metal to the semiconductor, and they will flow near the surface only, no? Like it's not that, sir, electrons like first where they would come. Let's just say this is your this is your oxide, this is your semiconductor, and this is your metal. So from metal, electrons are going in and they are being padded up here. So electrons are being padding up near the surface, or you can say near the oxide semiconductor surface. That means here, near to this point, near this point, the whole concentration has gone down and electron concentration has gone up. Whole concentration has gone down. What is the meaning of whole concentration going down? The difference between the intrinsic Fermi level and this particular Fermi level will be less. Is that clear to you what I am saying? If electrons are flowing from metal to the semiconductor, then electron concentration is increasing, hole concentration is decreasing near the surface. Hole concentration is decreasing. That means the intrinsic Fermi level will become closer to the p-type Fermi level. So here your intrinsic Fermi level will become closer. Is that clear to you? And in the bulk, like everything would happen near the surface only. But in the bulk, this will not happen. It will happen near the surface only. In the bulk, it will not happen. Is that clear to you? Other phenomena is also understandable. How you can understand? Sir, this would be the electric field direction. Electric field direction is this one, right? So if this is the direction of electric field, now electric field can be set up inside the semiconductor as well, because semiconductor can drive electric field. Metal will not be able to drive electric field, but semiconductor will be able to drive the electric field. So electric field will take place inside the semiconductor as well. What will be the direction of that electric field? I told you at the boundary, direction of electric field remains same. So inside the oxide, if this is the direction of electric field, what I am saying, inside the oxide, if this is the direction of electric field, then after the oxide, in the semiconductor, this will be the direction of electric field. Say yes or no? So if this is the direction of electric field, then the slope of conduction band or slope of intrinsic Fermi level or the slope of valence band will be like this. The slope will be like this. So this is the slope of intrinsic Fermi level I have made. The same slope, the ditto same kind of structure you will get for conduction band as well. And the ditto same kind of structure you will get for the valence band as well, because I told you one thing, the phase of conduction band, valence band and intrinsic Fermi level is same, right? We have studied this particular scenario. What I have said, the conduction band, intrinsic Fermi level and the valence band would look similar. So by the electric field as well, you are able to understand that this is your electric field. Sir, why you do not make it linear? This is not linear, okay? It is having some curvature. So surely we will see it, why it is not linear. Okay, we will surely see it, because one thing you already know, that the slope in the conduction band or in the valence band or in the intrinsic Fermi level shows the electric field, right? So you would get to know that electric field is not constant, it is a function of x. So if it is a function of x, then this will also be a function of x. So this is how it is going. Okay, so it is not linear, that you will understand. But inside the oxide, the electric field will be linear. All these points you will understand. Okay, What is the direction of electric field? Sir, this is the direction of electric field. So this is how the electric field would look like. Similar thing would happen downward as well. So how we can show it? So this is your conduction band. This is your valence band. Okay. Is that clear? Understandable? So this diagram is clear to you or not? Again, let me repeat all the points that I can tell. Electrons will flow from metal to semiconductor because of the work function difference. This is having lesser work function, this is having more work function, or you can say, sir, here Fermi level is above, here Fermi level is below. So more electrons, lesser electrons will flow, this side will become positive, this side will become negative. That means electric field will be set up. Sir, when we were studying metal oxide metal semiconductor, at that time you said that, sir, inside the metal there will be zero electric field, but sir, inside the semiconductor there can be electric field. Boundary condition I have studied, if inside the oxide this is the direction of electric field, then inside the semiconductor this will be the direction of electric field. Same direction would be there. That means inside the oxide this will be the slope, inside the oxide this will be the slope, and here this will be the slope. Same kind of slope would be there. The magnitude is same, that is not necessary. I did not say that magnitude would be same, but at least direction is same, right? So this is your, which color I should use? I can use this color. So this is your electric field inside the oxide, and here we are getting electric field in the semiconductor. Okay, well and good. And another region, like another way to explain is this, that sir, electrons are coming from here to here. What does that mean? Sir, electrons are getting more here, that means holes are getting lesser. Electrons are getting more, holes are getting lesser. That means the gap between the Fermi level and the intrinsic Fermi level should be less. That means this gap should be lesser than this gap, and which is happening as well, right? The gap here should be lesser than this gap. Why is that so? Because less gap will show less doping. Have we seen this point? Yes, sir. Conduction band, valence band, intrinsic Fermi level, and Fermi level, right? Intrinsic Fermi level, this Fermi level can be above, and this is your conduction band, right? So if this gap is lesser, that means less doping. If this gap is more, that means more doping. In the last lecture we have studied this. I hope you remember all 4 diagrams, because those diagrams will be again and again used here. Less gap, more doping. Sorry, less gap, less doping. More gap, more doping. So here, if I say my electron concentration was 10 to the power 16. So now here my electron concentration would have become some 10 to the power 15. Not much changes would be there, but surely some changes would be there. Now there are 2 scenarios. One is bending in this guy. So can I call this bending as QVOX? Right? Because of this electric field, some oxide voltage will be developed, QVOX, that voltage. And here also there is a bending. So can I call this bending as Q phi S, Q phi surface? This is what I am saying. Let me explain it. What is the meaning of Q phi surface? Metal is there, oxide is there, and then semiconductor is there. So metal is losing the electrons, that means this will become positive. And this guy is taking the electrons, that means this side will become negative. Right? So there will be some potential that would be developed here. If I make that dotted line, so there will be some potential that will be developed inside the semiconductor, and that potential I am calling as phi S. I am not calling it phi SI. What would be the meaning of phi SI? Phi SI would show the potential of semiconductor, but I am saying that this much potential is phi S. If someone asks me what is this potential, like from this point to this point, what is the potential. So that potential will be different than phi s, right? This would be somewhat lesser than phi s. Are you able to understand this point? When I am saying phi s, that means I am measuring the potential from this particular side to till whatever the side there is some potential. Like basically, if I am saying that here nothing is happening, that means here zero potential would be there, this side is grounded, zero potential, zero potential, zero potential, only some potential will start developing here. If I am saying that, sir, these many bands are flat, nothing interesting happen, EC, EFI, EFP, EV, whatever the previous scenario was there, the same scenario is here as well. That means there is nothing, no voltage developed. The voltage that has developed in this much region only, in this much area only. So voltage have developed in this much area. So when I am saying phi s, what is the meaning of phi s? That means, sir, you are starting from the surface till the whole semiconductor. So that's why I am not writing phi si. Do you understand the difference between phi s and phi si? Phi si could be potential between any 2 points. But when I say phi s, S stands for surface here. So my phi s would be surface potential. Is that understandable to you? And what is the meaning of phi s? Surface potential. Surface potential means you are starting from the surface till the whole semiconductor. So either you go from here to here or you go from here to till the end of the semiconductor. Both are the same thing. What I am saying, if you go from here to here, whatever the potential you measure, or you go from here to here, whatever the potential you measure, that would be phi s only. Is that understandable to you? So let me make it more clear that what is the scenario here. At a negative, 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 negative will be built up. Okay. So if I measure the potential between these two guys, this potential will also be phi s, or if you measure the potential between these two guys, this potential will also be phi s only. Okay. So when I am writing down Q phi s, you should be able to understand the meaning of this. Q phi s means the potential from the surface to the whole semiconductor. And without applying any external bias, you are getting positive charge here, and here you are getting negative charge. That means the concept of flat band will come into action, right? So how much flat band you need to apply, that we will see. Now, what do you think, what would be your QVOX plus Q phi s equivalent to? QVOX plus Q phi s would be equivalent to what? Sir, that would be equivalent to Q. This guy went downward, this guy went upward. So that would be equivalent to, sir, Q. Since this value is larger, I need to write down the positive value. This would be a positive potential, this would also be a positive potential. So I need to write down the positive value. So, sir, this energy minus this energy. So Q phi si, Q phi si minus Q phi m. So when you solve it, what you get? Vox plus phi s. Vox plus what is phi s? Phi s is the surface potential, right? Phi si minus phi m. Actually, phi si is the work function potential here. So here what I was saying that, sir, between 2 points, like if I take this point and this point, whatever the potential that I can denote, that I cannot denote by phi si, because phi si is already given to Fermi potential. So here I need to give some different name, right? I hope you are not getting confused with the phi si that I explained and that I am explaining here. So phi si and phi s both are different things. Phi s means surface potential measured from the surface of metal oxide, from the surface till the whole semiconductor. Start from the surface, go till the end of semiconductor. Sir, if this is 0, this will also be 0 only. Why is that so? Because nothing exciting is happening here. This will be completely electrically neutral. So if this is 0, this will also be 0. So phi s is the potential that has been developed here. This much potential has been developed here. Is that understandable to you? Okay. And what is phi si? Phi si is your work function potential. Okay. Work function potential. And between any two random point, you can find out the potential. If I ask you to find out the potential between these two guys, what will be the answer? 0 volt. Why is that so? Because no band bending took place here. No potential was developing here. If this was 0, then this was also 0. So if you take any 2 points, between these 2 points, if I ask you what is the potential, that would be 0 volt. If I take this point and this point, if I ask you what is the potential, that would be 0 volt. So take any 2 points and ask the potential, that would be 0 volt only. But here the potential has started developing. So if I take these 2 points and ask you what is the potential, sir, it would be somewhat lesser than 5s, that I can tell you. Is that clear? All good, all fine. And how did I write down Q Vox plus Q phi x equals to Q phi si minus Q phi m? It should be clear to you from the last lecture. How did I write it down? Because as much this guy has come down or this guy has gone upward, difference of these two guys is appearing as the energy difference here plus the energy difference here. We have seen the same kind of analysis in PN junction as well, in metal oxide metal semiconductor as well, and now we are seeing it in metal oxide semiconductor as well. I hope you are able to understand this particular analysis, that whatever the changes that happened, that changes have appeared in two parts. One part is this one and another part is this one. So Q Vox plus Q phi s. Okay. That would be Q phi si minus Q phi m. Okay, yeah, fine. Getting the flat bands, I am not teaching you any theory. You should be able to solve this particular question. Without any theory, I guess you will be able to answer this particular question. How much voltage you need to apply to get the flat bands? Can anyone tell? Sir, the voltage that I need to apply from metal to semiconductor. What they are asking? From that, find the flat band voltage, the gate voltage required. Gate voltage required means what they are asking? They are asking the gate voltage required. This is your gate. So they are asking Vg with respect to body only. They are asking Vg with respect to body. So by default, always I will take body as ground only. So what they are asking? Metal to body voltage they are asking. So what would be that voltage that they are asking? Can anyone tell what would be that voltage? This guy has become positive, this guy has become negative. That means I need to apply negative voltage here to kill this electric field. The electric field has been set up in this direction. To kill this particular electric field, what I need to do? I need to apply negative potential here, because this negative potential will induce positive potential here and the opposite electric field will be set up here and they will cancel out each other. Right? So negative potential, how much negative potential? Equal to Q phi m minus Q phi si. So what will be the answer here? Q phi m minus phi si, but I am talking about the potential, so Q will be gone. So phi m minus phi si. So sometimes it is written as phi m si as well. So people directly remember it, phi m si. Look, even if this guy was downward and this guy was upward, then also the answer would have been phi m si only. What I am saying, this is the condition that this is downward and this is upward. This is your EFP and this is your EFM. So what would happen? Electrons will flow from here to here. Although practically, sir, it will not be possible. How a p-type semiconductor can have more number of electrons than the metal? P-type semiconductor is having more number of electrons than the metal. Is it possible? Hypothetically, we are making it possible. Okay, 99.99% chances are there that this condition will be asked in the examination. But who knows theoretically if they have framed that p-type semiconductor is having more number of electrons than the metal. So what will happen? Electrons will flow from here to here. This side will become positive, this side will become negative. Electric field direction will be this much. What really happened? Metal has become negative. Then there is oxide and semiconductor has become positive. So what voltage you will apply? You keep this as ground. What voltage you will apply? Sir, some positive voltage I will apply. How much positive voltage you will apply? That I am calling as flat band. How much positive voltage you will apply? Sir, higher gap minus the lower gap. Positive voltage, no? Here what I need to apply? Here I need to apply the negative voltage. If I need to apply the negative voltage, what I did? Lower gap minus the higher gap. Here I need to apply negative voltage, right? Is that understandable to you? I need to apply negative voltage. That's why I did lower gap minus higher gap, because you know that, sir, phi m is lesser than phi si. Phi si is more, phi m is lesser. So lesser minus more, what that would be? Negative. So phi m minus phi si, I have done. What I am getting? Phi m si. So here also I will get the same thing. What I need to do? I need to apply the positive voltage. Positive voltage means higher minus lower. What is higher? Phi m. What is lower? Si. So what answer I am getting? Phi m si. Here I was having p-type substrate. Even if it was n-type substrate, answer would always be the same. So this phi m si you can simply keep in your mind that first I will take the metal work function, then I will take the silicon work function, and I will subtract them no matter whatever their value is. Or if you want to be more confident in the examination, then draw the energy band diagram. Drawing the energy band diagram, you would understand from where the electrons are flowing out. Here electrons are getting in, this side will become positive, this side will become negative. That means I need to apply the opposite voltage. Here I will apply negative, here I will apply positive. So negative I need to apply, that means lower minus higher I need to do. Or if this kind of band diagram is there, that means electron will flow opposite. This side will become positive, this side will become negative. Now on the metal I am applying some voltage. On the metal when I am applying some voltage, metal is already negative. I need to make it positive. So what I will do, I will apply positive voltage. Positive voltage means higher minus lower. All the time answer would come out to be phi m si only. Okay. So this is like a generalized formula. We will write down the generalized formula as well, but as of now we are understanding with respect to concept. And I can remove these guys as well. I can simply write down n into p equals to ni square will always be valid, which here also is always valid. Okay, here electron concentration was 10 to the power 4, but here electron concentration has increased. That has become 10 to the power 5. Although this much change will not be there practically, right? Because of the work function difference, this much change will not be there, or it can be there as well. So our target is to find out the work function energy of p-type semiconductor. So what all things I am having? I am having Na value, I am having Eg value, I am having electron affinity value. All these values I am having. Ni value I am having. Metal work function is given. Phi m is given. Q phi m is given actually. This is your Q phi m, which is given as 4.1 electron volt. So from here, phi m would be 4.1 volt. Okay. What we need to find out? We need to find out phi si. Semiconductor work function we need to find out. So let's do something. Vacuum energy level. Conduction band, valence band, EFI, and this would be your EFP, right? What they have given? They have given electron affinity, right? Electron affinity they have given, which is 4.05 electron volt. So this gap they have given 4.05 electron volt, right? In which gap I am interested in? I am interested in this gap. I am interested in this gap, right? Do I already know this gap? Do I already know this gap? EFI minus EC minus EFI. Do I already know this gap? Yes, sir. What is this gap? Sir, total band gap is given as 1.12. Total band gap is given as 1.12 divided by 2. Electron volt, let's mention it in electron volt. So what I will be getting? 0.56 electron volt. So this gap is also you are comfortable. That is, sir, 0.56 electron volt. Is that understandable to you? So, sir, you already know this gap as well. This gap is nothing but 0.56 electron volt. Let's make the better diagram here. Now I need to care about only this much of gap. If I am able to get this gap, then my job is done. I will simply add all of them and I will get my silicon work function potential. So what I need to find out? EFI minus EFP. Do you remember the formula for this one? What it is given as? Sir, this is given as Fermi potential. I told you this we call Fermi potential. In the last lecture only I told you about it, right? What we call it? Fermi potential. So here I have already shown, so let's not make this diagram bad. Okay, so this is known as Fermi potential. So if I am able to find out my Fermi potential, my job is done. In the examination, what they can do, they can simply mention your Fermi potential is this much. So you should be able to know what is Fermi potential. So Fermi potential energy, since I multiply with Q, so that would be equals to, so KT ln Na by Ni. From basic semiconductor physics, I remember this much. I hope you remember this much.
So from here, phi f I can find out, that would be 0.0259 ln Na by Ni. Na value is given, Ni value is given, 5 into 10 power 16 divided by Ni, which is 1.5 into 10 power 10. Say yes or no. Right? Okay. So let's do the calculation. So 0.389 volt, or better here if I write down 0.389 electron volt. So what will be your work function energy? So that would be 4.05 plus 0.56 plus 0.389 plus 0.56 plus 4.05, 4.99. It is coming out to be 4.99 volt. कैलकुलेशन में तो so phi m is coming out to be 4.1 volt, and this is coming out to be 4.99 volt. Nearly it is 5 volt only. So nearly I can write down as 5 volt only. Let me check back the calculation. 4.05, 0.56. This is coming out to be Na by Ni, 5 by 10 to the power 6. It would be correct only. I have done the calculation correct. So this is coming out to be 5 volt. So what will be your flat band? So for flat band, I have told you, you can directly remember this formula, phi msi. So 4.1 was already given for metal. For metal it was given, that was 4.1 minus 5. So your flat band is minus 0.9 volt. Okay, fine. So this we have find out, and we have find out the semiconductor function as well, and we need to draw the energy band diagram. That means what we are doing, if you can understand, metal oxide semiconductor, this was your metal oxide semiconductor. So on the metal we are applying negative bias, and this is grounded. So basically you can say that with respect, here I am applying negative bias, or you can say if this is negative, this would be positive. Are you able to understand my point? To get the flat bands, on the gate we are applying the negative bias. That means metal is fed with the negative bias. If metal is fed with the negative bias, what will happen? Fermi level of metal will go upward. If I apply negative bias, I hope you remember this one, Fermi level will be like this. If you apply the positive bias, Fermi level goes downward. If you apply the negative bias, Fermi level goes upward. So Fermi level of the metal will go upward. So I will get the flat bands everywhere. I will get the flat band in the oxide. This is my oxide. Look, I hope this is not troubling you. Okay, but here in Rajasthan, ठंड बहुत ज़्यादा है यार. Okay, high amount of winter is there, and I don't care of my health. This is the worst thing about me. So a lot of bad things are there. This is not the only bad thing. Okay, a lot of bad things are there, but I don't care about my health. This is one of the bad thing. Yeah. So if you are applying negative bias at the gate, then what will happen? Fermi level will go upward, and this Fermi level remains at his own place. You can say that this remains at his own place. Okay, because you are saying that this is connected to ground, so you can say that this remains at his own place, but the other guy is going upward. So if I say this guy remains at his own place, and now all the bands will be flat. All the bands will be flat, because whatever the initial charge that was developed, this positive negative charge was developed, that has been cancelled out because of this negative and positive charge. So no charge is there, everything has been cancelled out. So all the bands will be flat. All the bands will be flat. So this would be your this was your EFI, this was your EC. Now these two will be in the same place, nothing like that, right? I'm randomly making it. This is your EC and this is your EV. Okay, this is your EC of semiconductor, this is your EV of semiconductor. Okay, and this was your EFI. And flat bands we have got. Can anyone tell what will be this particular value? This will be, sir, V flat band. Say yes or no. QV flat band, better I should write down QV flat band because we are talking about the energy. So this will be, sir, nothing but QV flat band, or you can call it Q phi MSI or SIM because I am writing down the positive value, no? So SIM I am putting. What is the meaning of SIM? Because I know that, sir, Q phi SI was more and this was lesser. So positive value I am putting. Here I am just showing that this gap is positive. So minus Q VFB also I can write down. Because VFB is negative, no? Flat band voltage is negative. So better I should write down minus QFB, minus Q VFB. Basically, at flat bands, after achieving flat band, after achieving flat bands, if I am putting the gap between EFM and EFP, that would be equals to Q VFB that I applied, but the negative value of that, or you can call it, sir, phi SI minus phi M. But if I am talking about the energy, I need to multiply with Q as well. So Q phi SI minus Q phi M. Q phi SI minus phi M. So this is the scenario. Is that understandable to you? Basically, whatever the bias you give, because of that bias only this has went upward, no? Because of this negative bias only this has went upward. So how much gap this, how much this has gone upward? Previously they were same. Here they were same. Here they were at same level. Now you have applied some bias. Because of the bias, this guy has went upward. So how much this has went upward? Equal to the bias that you have applied. Equal to the bias that I have applied. Here what I have applied? V flat band I have applied, which is negative. So equal to the bias that I have applied, this has went upward. And this remains at his own place. All good? All fine? Okay. So this is the flat band condition we have mentioned and we have solved the numerical as well. I hope you find it out in an easy manner only. Otherwise, MOSCAP becomes very difficult, but we have understood metal oxide metal capacitor. Based on that, we are able to understand everything here. Just one more new thing was there, that even inside the semiconductor, this time electric field will be existing. Right? So electric field is not being cancelled out here. Basically, here also some negative charge would be there, no? So electric field is actually going inside the semiconductor. So electric field is actually going inside the semiconductor, inside the semiconductor, inside the semiconductor, inside the semiconductor. So electric field is actually going inside the semiconductor. Okay. So this electric field is going inside the semiconductor as well. Right. So from now onwards, whatever the discussion we will do it with respect to ideal MOSCAP. Now, what is the meaning of ideal MOSCAP, sir? Ideal MOS capacitor means this Fermi level of metal and Fermi level of any semiconductor that you are using, whether it is p-type or n-type, both will be at the same level. If both are at the same level and I join them, will there be any electron flow? Whatever the number of electrons you are having here, the same number of electrons you are having in p-type semiconductor as well. That means there will be no electron flow and they will be directly joined. They will be joined like this. That's it. Nothing got changed. So this is known as your ideal MOSCAP, or you can call it zero flat band condition. Zero flat band voltage is required. So for getting zero flat band voltage, this condition we have already understood, that if your metal work function and your silicon work function or your semiconductor work function are equal, then no electron flow will take place, no electron flow, no electric field, nothing happened. So this scenario, what is the meaning of this scenario? No fixed charge trapped inside the oxide. We will study it. Okay, study later. Surely we will study it, but later on. Study later on. Okay, probably in the next lecture or in this lecture, we will surely study it. What is the meaning of trapped charges inside the oxide? So when you fabricate MOSCAP, no, when I fabricate metal oxide semiconductor, during the fabrication, what will happen? Some charges will be trapped here. So because of these trapped charges, what will happen? These positive charge will induce some negative charge here. And because of the negative charge, what will happen?
band bending will take place. Negative charge means the electron concentration has gone down. Positive charge have repel the holes. Basically, one more thing I would like to tell here. In this scenario, here positive charge is developed. So actually holes are being repelled here. Positive charge is developed, that means holes are being repelled. Now this is your p-type substrate. What is the meaning of p-type substrate? This is the meaning of p-type substrate. If holes are being repelled, that means itself it will become negative, no? So all this scenario we will discuss, have some patience. But as of now, we have discussed all this particular thing. So there will be some more topics. That topic would be no fixed charges should be trapped inside the oxide. So we will study about the flat band again. The flat band will again come into action. So one scenario is this one. Another scenario would be there. That scenario would say that some fixed positive or negative charges are trapped inside the oxide. Because of this positive and negative charges, something would happen with these bands and band bending will take place, and we need to stop that band bending. So again, to stop that band bending, what I need to do, I need to apply some potential at the gate. Okay, so we will study that, but as of now, you just remember this point, that there is no fixed charge inside the oxide. Basically, the flat band voltage is 0. This is our condition, that here our flat band voltage is 0. No voltage I need to apply, no initial charging, discharging would be there, nothing is there. Initially, there is, everything is at flat band. Initially, everything is at flat band. Okay, initially, everything is at flat band because their electron work function, metal work function and semiconductor work function are equal. If they are equal, no electron flow, nothing, everything is flat. Q phi M metal, Q phi Si I can show here. Okay. Now I will start giving some supply at the gate terminal. What I will do, I will start giving some supply at the gate terminal and body I will keep grounded. So first what I am doing, I am giving negative supply at the gate. So what I will write down here, negative supply at the gate, that means Vg less than 0. Now what is 0? 0 is flat band only, no? So can I write it down Vg less than flat band voltage? Is that understandable to you? That our first target, whenever we give any bias, our first target is to get the flat bands. If any device is there, first target is band should be flat. Even if there was PN junction, even in the PN junction as well, flat bands were there when they were not in the junction. Right? P was there, N was there, they were separate. When we joined them together, then some band bending took place. Right? So that was PN junction. Here in MOSCAP, some band bending is taking place. Some band bending is taking place. This kind of band bending is taking place. So first target is to get the flat bands, but what we are assuming? We are assuming which condition? This condition. That means already, even at 0 flat band voltage, already we have achieved the flat bands like this. But if flat band was non-zero as well, then can I write it down in this manner, that Vg is less than V flat band voltage? Because 0 is flat band only, no? 0 is nothing but flat band. If you are not able to understand this particular scenario, leave it. Just you need to understand that we are applying the negative bias now. What we are doing? We are applying negative bias. So this guy is connected to negative. This is already grounded. Let's just say this was some 5 volt. So this is 0. This would be minus 5 volt. So what I am doing? I am applying minus 5 volt here. Because of minus 5 volt, what will happen? Negative, 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 negative. Now what this negative will do? Negative will say holes go away. Because negative charge will repel the positive charge. So what it will say? Sorry. It will not repel. Sorry guys. It will attract. Sorry guys. Sorry. Big blunder. So it will attract the holes. Because negative charge, this is negative charge and these are holes. So negative charge will attract the holes. So negative charge will say holes come to me, come to me, come to me. So a lot of holes. This hole will go here, this hole will go here, this hole will go here, this hole will go here. This hole will also go upward, this hole will also go upward, this hole will also go upward. All these holes will go upward. So here a lot of holes will come into action. A lot of holes. Already holes were very high, 10 to the power 16. Here they have gone in a very huge amount. That means a lot of holes we have accumulated here. What we have done? We have accumulated a lot of holes in this very thin region, in this very thin plate, in a very minute layer. We have accumulated a lot of holes because of this negative charge. Negative charge said, holes come to me. A lot of holes went upward, right? But you might think that, sir, this guy will lose its hole, this guy will lose its hole, this guy will lose its hole. No, it will not happen. Battery will supply the holes. No? Battery can supply the holes, right? So no one will be losing the holes. Like, whole system will be electrically neutral. Whatever the positive charge that is here, the same whatever the negative charge is here, the same amount of positive charge will be here. Now, whatever these guys that are losing their holes, those holes will be supplied by the battery. Let's just say this hole has went upward. If this hole has went upward, then you might think that, sir, this guy is losing its hole. No, that will be supplied by the battery. So current is zero. How battery is supplying the holes? That answer I have already given. Current is zero, but at the steady state, there was an impulsive current. Because of that impulsive current, holes have got into it. Okay. So just as I apply a negative bias, this negative bias, this minus Q1 charge, what it will say? That I need positive charge. I need positive charge. Then holes will say, we will provide you the positive charge. So holes are coming upward, upward, upward. A lot of holes have been set up, or a lot of holes have been accumulated in a very thin layer. Now, very, very important point is coming up. This thin layer will behave almost like a metal only, no? Why almost like a metal? Because, sir, a lot of charge carriers have come into action. If this was 10 to the power 16, let's just say this has become 10 to the power 19 or 10 to the power 18. This 10 to the power 16 was already very high. This was also more than enough to call it a metal. This is also very high. Now what you have done, sir, a lot of holes have come into action. Because of that, it is nearly behaving like a metal. So from this negative terminal, from here, electric field lines will go out. So electric field lines will go out, go out, go out. Now electric field lines will say that I want to get inside the semiconductor. But what this layer will say? This layer will say, I am behaving like a metal only. So you cannot penetrate me. Very, very important point I am telling. From the negative layer, from the metal, electric field lines have gotten out. Now these electric field lines will get into the semiconductor. They will say that I will penetrate. But they will say, this particular layer will say, whatever the charge you require, whatever this minus Q1 charge you require, I will be giving you plus Q1 charge. I will be giving you plus Q1 charge. You don't need to go to the semiconductor. I am more than enough. I am behaving like a metal. Whatever the positive charge you require, that I can give you. Because I am already P type. So here, whatever the change that I put here, this guy will provide me the same amount of change charge. Because this layer is very strongly metallic. So electric field will never penetrate inside the semiconductor. A very minute amount of electric field will be there till this thin layer only. What I am saying, let's just say this layer is of 3 nanometer. Our semiconductor length is 1 micrometer. Let's just say semiconductor length is 1 micrometer. So this layer will be very, very thin. 3 nanometer thin layer would be there. So electric field would have penetrated in the semiconductor from 0 length to 3 nanometer length. So till 3 nanometer length only the electric field will penetrate. After that it will not go to the semiconductor at all. So started from here, penetrated till this point. Started from here, penetrated till this point. Started from here, penetrated till this point. So isn't it working like a metal oxide metal semiconductor capacitor? Say yes or no. Sir, metal oxide metal semiconductor capacitor, sir, that is equals to MOSCAP only. So sir, our oxide thickness I can use as TOX. So sir, our capacitance will come out to be epsilon OX A TOX. Again capacitance is constant if I am applying negative bias. People usually mug up that if you apply negative bias, capacitance would be constant. Why it would be constant? Or they will say that, sir, there is no depletion width made. If depletion width is not made, that's why capacitance is constant. That's absolutely baseless explanation. The explanation is, whatever the change in charge that you are doing at the metal, this particular layer is enough to provide you the equal amount of charge that you are changing at the metal, because this particular layer is showing very high metallic behavior. Also, this is your p-type semiconductor only. So if you require positive charge, p-type semiconductor will say, I am more than enough. This particular layer will say, we are more than enough. We can provide you as much positive charge you ask. So if I am applying negative bias, I will expect positive charge here. These guys will say, we will provide you positive charge. You don't need to go inside me. You stay at the surface only. So you will penetrate only a very small layer. For example, I am putting 3 nanometer. Is that understandable to you or not? Okay, so let's write down in a better manner so that notes should look good. So this line is fine, this line is also fine. Let's remove this one, and here I will write down that I am able to provide you charge change. So it's like a metal oxide metal semiconductor, and that is equals to metal oxide metal cap only. Answer would be the same. Okay, so next slide is about the Venn diagram. So can you try making Venn diagram on your own? Try making it. You know the electric field. If you know the electric field, then can you show the band bending inside the oxide layer? This is your oxide, no? So this diagram is under equilibrium. Under equilibrium, that means what I am assuming? I am assuming the flat bands without even applying any flat band voltage. I am getting the flat bands. EFM and EFP are at the same level. No electron flow took place. Flat band condition I am having. So this is my equilibrium condition. Now what I am doing? I am applying negative bias at the gate. Here what you are doing? Negative bias you are applying. And here what you are developing? If you are applying negative bias, here a lot of holes have been developed. So electric field direction is this that we have already seen. This is the direction of electric field. Right? So inside the oxide, what is the direction of electric field? Sir, inside the oxide, direction of electric field is this. Right? You have applied a negative bias. If you apply a negative bias, what happens? Fermi level goes upward. Sir, will there be any bending in the Fermi level? Absolutely not, because current is still 0. So this guy has went upward, EFM. Sir, will there be any electric field inside the metal? Absolutely not. There is one electric field here. That electric field is UX. Now, sir, for very minute thickness, there will be electric field inside the semiconductor. For very minute thickness. First thing is there any current, sir? No current is there. That means EFP will be as it is. Well, let's show it a bit upward. Here we can show. Sir, EFP will be as it is. Right? What about conduction band? What about intrinsic Fermi level? And what about valence band? So you know that, sir, whatever the direction of electric field you are getting here, for a very minute region, for only 3 nanometer, some electric field will be penetrated here as well. So whatever the electric field direction we are getting here, the same electric field direction we will be getting here as well. That means, sorry guys, whole explanation went wrong. The direction of electric field is opposite, no? So I hope you guys did not mind it. The direction of electric field is opposite. From the positive charge to negative charge. Rest all things are fine, only the direction is opposite. From positive to negative, positive to negative, positive to negative. So that's a blunder from my end. This is the direction of a field. Okay, so the direction of field will start a bit inside from semiconductor, right? This will say that electric field lines will come into me. From where they will start? They will start from here. From which point? From this particular point. From this particular point till here. From this particular point till here. From this particular point till here. So inside the semiconductor for 3 nanometer, what is the direction of electric field? Sir, opposite direction. Whatever that you have shown here, you have matched it up, sir, opposite direction. Because electric field direction is always from the positive charge to the negative charge. Sir, opposite direction. This you have completely matched up. But this you have done fine. That what you have done. So negative charge you have put, so Fermi level goes upward. It's just that, sir, direction you have completely matched up. So make it correct. So I am making it correct for you. This is the direction of electric field inside the oxide. Okay. And EFP I can make a bit downward now. This is my EFP. Now inside the semiconductor as well, for a very minute region there will be electric field. For 3 nanometer region only. For 3 nanometer region only there will be an electric field. So what is the direction of electric field? This is the direction of electric field. That means slope should be somewhat like this, because this is the direction of electric field. In the direction of electric field, the slope should be positive. Or what could be the other way? Other way could be, sir, here we are getting a lot of holes. That means hole concentration has went upward. This was 10 to the power 16, this has become 10 to the power 18. That means, sir, at the surface, hole concentration has went upward. Hole concentration has went upward. Sir, here, this was my intrinsic Fermi level. Sir, this was my intrinsic Fermi level. This was the gap. But sir, near the surface, what has happened? Sir, near the surface, hole concentration has went up. More holes are there. That means the gap will increase. Say yes or no. This gap will increase. You agree to this point? Let's see more points. So whatever the slope that we see here, the same kind of slope we will get in our conduction band as well. Right? Because phase of conduction band, phase of valence band and phase of intrinsic Fermi level will be the same only. So here also I can show it in a better manner. This is how I can show it. Well and good. Okay, so this gap was Q phi f. Can anyone tell what will be this gap? So this gap could be written as QV of x. Can anyone tell this is the line? No? So I can make this line here. This is the line, right? So I'm just extending this line here. What I'm doing, I'm just extending this line, extension of this line. So if someone asks me, what is the gap between these 2 points? What is this gap? What is this gap? This gap is nothing but QVG. How it is QVG? Because whatever the bias that you have applied, because of this bias only this guy has went upward, no? Right? What will be this gap? This gap will be Q phi s. Surface potential. If there is electric field, if there is some electric field, then there will be this minute surface potential as well, no, between these 2 points, Q phi s. So if theoretically if you see that sir, you are applying Vg here, this much Vg you have applied. From the metal, look, let me show it here. So starting from the metal till this particular point. So the whole potential that you have applied, whole potential is Vg. Whole potential that you have applied, that is Vg. Because you know that if sir this is 0, this is also 0. Right? If this is 0, this is also 0 because this is neutral only. So if this is 0, this is also 0. So whole potential Vg I applied across this, but this much potential or this much potential, both are same thing, right? So this is Vg. Now, some potential is dropped across the oxide, which is Vux, and some potential is dropped in this particular layer, that is phi s. So Vg is equals to Vux plus phi s. Right? Understandable? So this is your Q phi s, or this much is your Q phi s. So this QVg is equivalent to QVux plus Q phi x, or I can write down Vg potential is equals to Vux plus phi s. Sir, if this gap is more, what is the meaning of this more gap? That means whole concentration has gone up. If gap is more, whole concentration is more. Because this gap is lesser, which is showing less whole concentration, or whatever the whole concentration. Here whole concentration is 10 to the power 16. Now who knows, in this particular region the whole concentration has become 10 to the power 18 centimeter cube inverse. And from where band bending is starting? In this much region band bending is there, no? So this region is 3 nanometer. This 3 nanometer that I have put, it is not a fixed value. Only random value I am taking, 3 nanometer. Any random value I am taking, just to show you that this length, this particular length is actually very small. This 3 nanometer in a very small region. In a very small region, holes have been piled up. And these holes are showing a metallic behavior. And because of this metallic behavior, what is happening? It is working as a metal-oxide-metal semiconductor capacitor, which is equals to MOSCAP only. And MOSCAP will provide you the value, fixed value, epsilon OX, TOX, multiply with A. And these are the band diagrams we have got. More things we can see. Charge plots we can make. So this side is metal, this side is oxide, and this side is semiconductor. So on the metal, negative charge is piled up. Here negative charge is piled up. So that will also come on a very thin layer, no? Like, do you remember this structure? This was your metal. I told you I will give it a negative supply. So negative supply will come here. That means this is a very, very, very thin layer. 0 nanometer. If it is 3 nanometer, this is 0 nanometer. The negative charge is coming on 0 nanometer because you know that electric field will be not going inside the semiconductor at all. Sorry, electric field will not be going inside the metal at all. That means it is at the surface only. 0 nanometer. So I will be showing it with very, very minute width. 0 nanometer width. Negative charge I am having. So negative charge should be shown. This is your charge density plot. So negative charge should be shown on the negative side. So negative, 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 negative. 0 width. If this is 0 width, then 3 nanometer width I can show somewhat like this. Although these widths are actually very, very small. And inside the oxide there is 0 charge. Inside the oxide there is 0 charge. Inside the oxide there is 0 charge. And inside the semiconductor there is holes. Holes are present. What is the meaning of holes? Holes means positive charge only. So here there is positive charge, but for a very minute length, which is 3 nanometer. Okay. When you integrate this, what you get? Electric field. Do you remember the integration?
right? So let's keep it here. So just we need to integrate. So this integration I need to do. So it will be simply a straight line only, no? Like, have you done the integration of this particular thing? Yes, sir. The integration would be somewhat like this. But this width is actually very small. That means this line will be nearly long line only. Are you able to understand this point? If I am making this width very small, that means slope will increase here. So this width is nearly 0 only. So slope will be nearly infinity. Integration. Maths. This is the integration. What will be the integration of this particular thing? Sir, this will be the integration. What will be the integration of this particular thing? Sir, this will be the integration. The integration will be like this, or it will be like this, sir. So this is how we are doing it. And then there is zero charge. If you integrate 0, what you will get? Constant. And then there is this much of charge, right? So you integrate this, this is what you will get. But you integrate this and this is what you will get. But this line is wrong. This line is wrong. Why it is wrong? Can anyone think? This particular line that I have made, that is wrong. Integration will be like this only. But the line will not start from here. Then sir, from where the line will start? Line will start somewhat like this. And then after that everything is 0. So this is how the integration would go. Why the line is starting from here? Because you need to do the integration and then divide by epsilon as well. So now I am getting into semiconductor. So epsilon of semiconductor, epsilon Si, epsilon of oxide is epsilon Ox. So here I was dividing by epsilon Ox, right? Here I was dividing by epsilon Ox, and here I will divide by epsilon Si, and epsilon Si is surely more than epsilon Ox. Okay, I think shows somewhat like this. Okay, ratio is nearly 3. Okay, nearly it is 3 times. Nearly it is 3 times. Okay, is that clear? So you are dividing by something more. Like inside the semiconductor, if you are writing, that means you are putting epsilon Si. That means you are dividing by something more. And from here only this formula came. No, electric field inside the oxide multiply with EOX would be equals to electric field inside the silicon epsilon Si. But I am not caring about the electric field inside the silicon. I am only caring about the electric field at the surface. This is your surface. This is your surface. I am only caring about the electric field at the surface. So I am putting it as ES. So your electric field at the surface will be electric field inside the oxide epsilon OX divided by ESI. So epsilon OX, what is the ratio of EOX divided by ESI? That would be EOX divided by ESI, that would be 1 by 3. So this would be 1 by 3. So if this electric field is EOX, this is your ES, which is EOX by 3. So that's why here the field is EOX, but here the field will become lesser. And this is the boundary condition also we have studied. From the boundary condition you can see, and from this formula you can see. This formula says that you need to divide by the epsilon. So first I was dividing by epsilon OX. So here I was dividing by epsilon OX, but now I am dividing by epsilon Si. Is that clear to you? So this plot is clear to you. And now is it clear that inside the oxide the electric field is uniform? That's why the slope was constant. But here the slope is not constant because this kind of waveform you are getting. Linear waveform you are getting. That means electric field is changing with respect to x, although this distance is very small. This distance is nothing but 3 nanometer. This distance is nothing but 3 nanometer. Practical value I am taking. Sorry, not practical value, any random value I am taking. There is nothing certainty here. So 3 nanometer I have to here, 3 nanometer also I have to here. So in this 3 nanometer, here there is more electric field, and then electric field becomes 0. By this diagram as well you can verify it. Electric field is there inside the oxide till 3 nanometer electric field is there, but after that everything is 0. Or you can simply integrate it. In signal system you will understand the integration, very simple integration. This will go like this, and then EOX, because 0 is there, so whatever the value it is having here, the same value will be attained. And then electric field, you thought that integration would go somewhat like this.
No, integration will not go like this. The value will be decreased a bit because you will divide by epsilon Si. Is that clear to you? So this is the waveform of electric field. What will be the waveform of potential? Think about it, have some patience and draw this waveform on your own. V of x is integration of electric field and then negative sign. What will be the integration of this particular field? The integration would be somewhat like this. So in this manner, and then in this manner. Integration is nothing but the area. Integration is nothing but the area. So negative area, then more negative area. Always here area is increasing only. So how will you integrate? 0, 0, 0. Then area is increasing. So area increases in linear manner. Then area increases in what manner? Square manner. And then area becomes constant. Like if I am standing here, I ask you what is the area of this one. Like if I am standing here, that means I have integrated from minus infinity to this point. That means I have to calculate all the area. So this area plus this area, what that would be? Integration and then this side. I hope you know basics of signal system. This is nothing but integration only. Simple integration. So this will be the integration you will be getting, but there is a negative sign. So this is how you will show it. Okay. So someone can make the diagram like this. That sir, diagram would go somewhat like this. So this length is 3 nanometer. Can anyone tell what is this value? This value is 0 volt. Why is that so? Here you are applying 0 volt, no? So at the 3 nanometer as well, you will get 0 volt only. So this value is actually 0 volt. And at the gate, what you are applying? Negative potential. Minus Vg. At the gate, what I am applying? Minus Vg. So this is your gate. This is your metal. So this is your gate. So this value is minus Vg. And this value is 0 volt. So waveform nature will be like this only. What we used to do, first we used to integrate and then we used to take the mirror image. So here I have taken the mirror image. Right? If I integrate it like this, then I take the mirror image. Then what I will get? This kind of waveform I will get. So forget about this. This kind of waveform I will get. So this will be my nature of waveform. But this particular guy is 0 volt and this particular guy is minus Vg. So what I can do, I can shift it downward, no? Because I am showing the magnitude. Actually, this is my 0. And what will be my negative? Negative would be somewhere here. Are you able to understand this point? So nature I have got, the nature would be like this, sir. But how will I make the waveform to make it look better? Sir, this is how I should make the waveform. Because I know that, sir, at gate I am having minus Vg. Right? Then it would go somewhat like this. Then a bit of potential for 3 nanometer will be developed here. For 3 nanometer, I can show a curvature for 3 nanometer. And then it becomes 0. This is 3 nanometer. This is your complete TOX. And this is your metallic side only. So I have shown the waveform like this. So can you tell what is this? So this value is Vg only. And what is this point? This point is minus Vg. Can anyone tell, sir, how much is this potential? Sir, this potential is nothing but Vox. And can anyone tell how much is this potential? Sir, it is nothing but surface potential. So from here what you can see, you can see that, sir, Vg is nothing but Vox plus surface potential. I know you are finding it tough, like it is not that easy, but again, if you are putting full concentration, then you will be able to understand. If you are not putting full concentration, I cannot do anything. Right? Integration I have done. Then I need to take the negative sign as well. So if you do the integration, sir, this kind of waveform you will get. Take the negative sign. This is how you will get it. So directly, sir, I should make it. Yes, this is the nature you are getting. Constant, increasing slope, square manner, and then constant. Constant, increasing slope, square manner, and then constant. But I know that, sir, this potential is 0 and this potential is minus Vg. So better I should make it downward, because these values will show positive and these values will show negative. So better I am making it downward. So better I have made it downward. Is that clear? Okay. So Vg equals to Vox plus phi s. So this is your Vox, this is your phi s. Is that clear? Well and good. This phi s is actually very small. Vg would be nearly equals to Vox, right? Because this is nearly behaving as complete metallic plate. Again, it is purely not metal, but complete nearly it is metal only. So it is nearly behaving as a metallic plate. So what you would see that this phi s is actually very, very small, but surely some phi s would be there. Surely some phi s would be there. Vg equals to Vos plus phi s. Again, we have proved here, and I hope these diagrams are clear to you. Okay. Negative charge, positive charge, integrated it. So this is very, very finite sheet. Since it is negative, so this kind of waveform I will be getting. Then Eox value I am getting here, and then this is what I am getting here. These are the relation. This is how I would get the waveform. So when I integrate this, I know that I will be getting a linear waveform like this. But the linear waveform will not be starting from here. It will be starting from somewhat downward. Why is that so? Because Eox epsilon x equals to Es epsilon Si. Why Es? Because I am interested in the potential at the surface. That's why I put Es here. So Es Eox epsilon x epsilon Eox divided by 3 I am getting. And then all the scenario I have got, right? Now, interesting point we are going to see carrier concentration at the surface. Here, what was my carrier concentration? I am saying here my carrier concentration was equal to the doping. This was your electron, this was your hole concentration, and this was your electron concentration. Now, someone asks you, what is your electron or hole concentration at the surface? Because you know that, sir, what has happened here, electron concentration has gone up 10 to the power 18, but this was a hypothetical value, mathematical formula. So can you think of deriving it? What is this? Q phi f. And what is this much of gap? Like how much this has went upward? Sir, this is nothing but Q phi s. So what is this much of gap? This much of gap is nothing but Q phi f plus phi s. Is that clear to you? So, like, hold on, like, have some patience and think about it. How did I write down this equation? One equation I'm going to write down. So, Q phi f plus phi s equals to KT ln. Something I will write down here, but have some patience. What will be your Q phi f? Q phi f. Can you tell Q phi f? Yes, sir. KT ln whole concentration here divided by Ni. So can I write down KT ln whole concentration at the surface divided by Ni? What is your PS? PS is nothing but whole concentration at surface. Is that clear to you or not? So from here what I can get? Q phi s equals to Q phi f goes here. So KT ln PS by Ni minus Q phi f. So what is your Q phi f? KT ln PS by Ni minus what is Q phi s? That is KT ln Na by Ni. So Q phi s equals to KT ln PS by Ni multiply with Ni by Na. So PS by Na. So if you solve it, what you are getting? PS equals to Na into e to the power Q phi s by KT. So this is the value of PS I am getting. Whole concentration at the surface. Can I tell what will be my electron concentration at the surface? So that would be Ni squared divided by PS.
That's it. Do you need to mug it up? You can remember this formula if you want to. If you don't want to remember it, then simply you will make the diagram. Within 2 lines, you will be able to derive it. Hole concentration is increasing. Look, gap between the intrinsic Fermi level and the Fermi level will always remain kT hole concentration divided by Ni. So here, what is the gap between intrinsic Fermi level and the Fermi level? What is the gap? That gap is Q phi s plus phi f. Is that clear to you? The gap has increased, that means hole concentration has increased. If you are following it up, then you are able to understand. Otherwise, MOSCAP is difficult. I cannot do anything. I cannot simplify it more. This is the simplest possible explanation here. Believe me guys, you can study from anywhere. Either they will skip these points or they will make it complex. Like what I could have done, I could have skipped this waveform. No, you will never find these waveform in any of the notes. Student will always be confused that, sir, why don't we make all these waveform for accumulation mode? One thing I forgot to tell, this is known as accumulation mode because holes are being accumulated here. No, holes are being accumulated near the surface. That's why we call it accumulation mode. And next time, I can guarantee you, next time when they frame the question from accumulation mode, they will ask you these waveforms. 100%. Because people don't make these waveforms for accumulation mode. They will start from depletion. They will make it for inversion. But they will never make it for the accumulation mode. For accumulation mode as well, they are important. Okay? Because this phi s is actually very small. But even if it is very small, here what I am saying, even if it is very small, then exponentially it can change the value of a hole concentration. We will solve a numerical as well. Is that clear to you? Exponential Q phi s by kT. Even if phi s is 0.1, this 0.1 is also very high. 0.1 divided by 0.026. Take the exponential, you would see very high value you will get. Some 10 to the power 3 value you will get. So already it was 10 to the power 16. 10 to the power 16 multiplied with 10 to the power 3. What it will become? 10 to the power 19. So very minute phi s would be there, but that minute phi s is also more than enough. Most of the potential will be dropped across the oxide only. Why it will be dropped across the oxide? Everything we have seen here, right? Because this layer is very small. This layer is actually very small. EOX will also be larger. Like if this is TOX, this is your TOX, right? This is the thickness. This is your oxide thickness. So can anyone tell what will be the value of VOX? VOX will be nothing but EOX into TOX, right? What will be this VOX? What will be this VOX? What will be this value? EOX multiplied with TOX. Very simple. Electric field is constant. What is V? E dot dx. This is uniform. E can come outside. EOX. Integration you need to take for dx. What is integration of dx? That is TOX. So EOX into TOX. So what is the VOX value? VOX will be EOX into TOX. VOX is nothing but EOX into TOX. So what will be your phi s? Vg minus EOX into TOX. Right? Here what we have find out? We have find out the hole concentration and the electron concentration. So here hole concentration is increasing. That means electron concentration is going down, which is pretty obvious because N into P equals to Ni square will always be valid. So can you make the concentration plot? This is your metal, this is your oxide, and this is your semiconductor. Only in the semiconductor I will make the concentration plot. So in the bulk, deep inside the semiconductor, this was my hole concentration, which was Na or capital Na, and this was my electron concentration, which was Ni square by Na. But what really happened? When I applied negative bias here hole concentration has went up. Hole concentration has went up. If hole concentration has went up, then electron concentration has to go down. So at the surface, what you are getting? PS. Here what you are getting? NS. So what will be my value of PS? That would be Na e to the power Q phi s by kT. And if I need to find out NS, that would be Ni square by PS. Like I have seen very rough derivation for this particular formula. People say like this approximation you need to take, this modeling you need to take. Forget about those derivation. Very straightforward derivation is there. What this gap would represent? This gap would represent the amount of doping. But here doping is not changing because of the negative bias. Holes are being pulled away. So here whole concentration I am putting, and here any concentration I have put. This is the answer we have got. This is the answer we have got. Okay. Always n into p equals to ni square will always be maintained. Along with that, ns into ps into is equals to ni square. This will also be always maintained. Okay. Capacitance value. How do you measure the capacitance? You fix it some bias. What we are drawing? We are drawing the capacitance value for accumulation mode. Accumulation mode. And this is our P substrate. What we are applying here? Minus 5 volt. And what is this? 0.1 sine omega t. So this minus 5 volt here, minus here, hole. Okay. So electric field will be set up in this direction. Right, electric field will be set up in this direction, and you know that, sir, this will become like a metallic plate only. So because of this small signal, whatever the change in charge that is happening here, whatever the change in charge that is happening here, the same change in charge will happen here as well. So what will be your capacitance value? Capacitance value in accumulation mode, that would be equals to COX, or I can write down epsilon OX TOX area. What is TOX? This is your TOX. Epsilon OX, permittivity of this guy. So epsilon OX divided by TOX, multiply with the area. This is your capacitance of accumulation mode. Okay. If I draw the graph, capacitance with respect to gate voltage. So till what point? When you are getting the accumulation mode, until you are applying gate voltage less than 0. So till this point, you get this value. This is the value which is COX. I will put it as COX, that is epsilon OX multiply with area divided by TOX. COX is epsilon OX area divided by TOX. Okay, until you are applying the negative bias. Is that clear? Okay. Why is that so? Why it is happening? Because a lot of holes have been accumulated. This is behaving like a pure metallic behavior. Because of this pure metallic behavior, electric field lines are not penetrating through the semiconductor. These electric field lines are getting out here. This width is actually very small, nearly equals to 3 nanometer. So very small width is there. So it is behaving like a metal oxide metal. Here I can write down, it is behaving like a metal oxide metal semiconductor cap, which is equals to metal oxide metal cap only, and that is COX. So this is about our accumulation mode. I hope we have understood everything. Now we need to solve this numerical. So you can try solving it on your own. Okay, I need to take a break. Okay, so try solving it on your own. What they are asking: electron concentration and hole concentration at the oxide semiconductor interface, or you can call it surface as well. I would say it is important. It is important. Applied bias is given. Minus 2 volt have been applied. Oxide thickness is given 10 nanometer. Ni value is given So somewhere you can use the NA value as well. EOX is also given. Electric field inside the oxide, that is also given. So if EOX is given, TOX is given, can you find out VOX? Yes, sir. What that would be? Yeah, this 10 nanometer is interesting. What you can write down 10 nanometer as? So 10 nanometer is nothing but 10 to the power minus 8 meter, right? And 10 to the power minus 8 meter could be written as 10 to the power minus 6 centimeter. Take care that every calculation I will do in centimeter. So VOX is equals to EOX into TOX. E is the electric field. So let's write down, better we should write down in this manner. So EOX into TOX, that would be 1.9 volt. That is your VOX. So what is your VG? VG is minus 2 volt, right? So can anyone tell, sir, what will be the value of phi s here? Can anyone tell what will be the value of phi s? Minus 3.9. Because, sir, what I have seen, VG equals to VOX plus phi s, right? Surface potential. Sir, VG is given as minus 2. Sir, VOX we have got 1.9. Phi s. Sir, phi s is coming out to be minus 3.9 volt. If you are doing this calculation, that means you are not taking care at all. You are not listening to me at all. If you are doing this calculation, electric field is negative, no? But I don't need to care so much of electric field is negative. So minus 1.9 into 10 to the power 6, and this will be multiplied here. So this will become minus 1.9 actually. But I don't need to care so much about all these values. Concept should be clear. Minus 2 I am applying. Then minus 2 I am applying here, right, at the metal. So 2 volt will be distributed. 1.9 has been distributed across VOX. So 0.1 will be distributed across the surface. So phi s will come out to be minus 0.1 volt. Right? It should be clear, like no formula, nothing. VG I applied, minus 2 I applied with respect to ground or with respect to body. This formula, this diagram should be clicking in my mind. Minus 2 I applied here, 1.9 has been distributed here, 0.1 will be reaching here, that's it. If you have applied minus 2, then this would be the direction. No, here some value will be dropped, right? Or I could have shown it opposite as well. In what manner I could have shown it? That, sir, downward is connected to positive, this side is connected to positive, this side is connected to negative. So across the VOX, this much have been dropped, and across surface, this much have been dropped. So VG equals to VOX plus phi s only. So if VG is negative, then all these guys are negative as well. So this phi s, you can say it is coming out to be minus 0.1 volt. Now if I apply the formula, what I need to find out? Hole concentration. Hole concentration at the surface. The formula that I got. What formula I got here? This formula, Na e to the power q phi s by kt. So will I put the negative value here? If you put the negative value, then hole concentration will be lesser. If you put the negative value, I need to put the positive value here. No. Is that understandable to you? Like this much basics are you able to use? 2 volt you applied. Forget about minus sign. 2 volt you applied. 1.9 went into oxide. 0.1 came as surface potential. So 0.1 is my surface potential. Understandable? So because of that 0.1 voltage, hole concentration has gone up. So here what I will put, positive or negative? Or shall I reframe the formula? In the formula what I will do, I will put a mod sign here. Phi s will be negative only. No, that is very much understandable. In this diagram as well you can see. This will be negative only. This guy is negative, this guy is negative, this guy is also negative. All guys are negative. But it doesn't mean that, sir, here you will put negative. In this formula I am not going to put negative. I will put positive only. Even by mistake, if I have put minus 0.1 here, I will be able to understand, because what is the value of Na that is given? 5 into 10 to the power 16 e to the power. If I put by mistake, if I put 0.1, then divided by 0.026. If I have put a negative sign here, I would know that, sir, this value will come out to be some 10 to the power minus 2, 10 to the power minus 3, whatever it is. Let's just say it came out to be 10 to the power minus 3. That means whole concentration has gone down.
This much knowledge I need to have. If I am applying minus 2 volt, that means holes will be attracted. So it should go higher. It should go upward. So here I need to use the positive sign. This much knowledge you need to have. So don't get confused with mode or anything like that. I will derive the formula, but basic sense should be there. What is the basic sense? 2 volt you are applying, 1.9 is eaten up in the oxide, 0.1 is reaching at the surface. So because of that 0.1 voltage, hole concentration is going upward. How it is going upward? Whatever that was there previously, 5 into 10 power 6, sorry, 5 into 10 power 16, e to the power surface potential divided by 0.026. In that manner, it will be easy to remember the formula. Let's see what answer we are getting. 0.1 divided by 0.0259 I am doing. Then exponential I am taking. So here what I am doing, let me do it again. 0.1 divided by 0.026 or 0.259. Then you take the exponential. So here I am putting 0.259. Then I am putting the exponential 4.75. Now into 5 also I need to do. So 2.73 into 10 power 80. So your whole concentration at the surface. Arey bhai, no space. This is the whole concentration at the surface you are getting. Whole concentration at the surface. So what will be your electron concentration at the surface? So that would be Ni square by whole concentration at the surface. What is Ni square? 1.5 into 10 to the power 10 whole square divided by 2.37 into 10 to the power 18. So it is coming out to be 94.7 centimeter cube inverse. I can just check it as well. Yeah, so it is coming out to be this much. So this is your electron concentration. This is your electron concentration. So this is the answer for hole concentration and this is the answer for electron concentration. I hope it was not very tough for you to understand. Minus 2 volt I was applying at the gate. Because of that minus 2 volt, minus 1.9 was dropped across the oxide and minus 0.1 was dropped across the surface. So e to the power 0.1 divided by 0.0259. This is something that we will be getting in the increase of hole concentration. Okay, how did I find that how much is dropped across the oxide? Electric field inside the oxide was given. I simply multiply it with the oxide thickness. I got the oxide voltage. Then rest of the part would be dropped across the surface only. So that I have written here. I got the hole concentration. I got the electron concentration. It is important. These kind of questions have not been asked yet, and that's why it is not there in any of the notes. If you have studied from somewhere else, you would see that, sir, they never talk about electron and hole concentration. They talk about potential, they talk about electric field, but electron and hole concentration, they don't talk about it. Even if they do, then very rough formula they write down. So surely it is coming in future. Okay. In Niemann as well, questions are given on electron and hole concentration. So surface potential is our matter of concern. If I am able to find out the surface potential, my job is done. Well and good. Okay. Next, what I will do, I will apply the positive bias now. Here what I will do, I will apply the positive bias. What this positive bias will do? It will repel the holes. Holes will be repelled and electrons will be attracted. Holes will be repelled, electrons will be attracted. What will happen? That we will see after a break. You also drink some water. I will also drink some water, and then we will see. We will apply a low positive bias. Low positive bias. So let's see what happens here. Okay then? Yeah. I will come back after a break. Yeah, welcome back. So now we are going to apply low positive bias at the gate. Okay. So positive bias we are applying, but that's a low value. Sir, what is the meaning of low value here? Some low value V1. Like surely our voltage that we are going to apply, this is our VG. So surely your VG would be greater than 0, but it would be lesser than V1. Sir, how much is V1? That you don't know. We can see that, but as of now, you will just consider that low positive bias we have applied. Low positive bias we have applied. Okay. So in place of writing 0, what I can write down? In place of 0, I can write down flat band. So we are applying voltage greater than flat band and less than some particular value V1. Okay. Or you can say it is greater than 0, less than V1. 0 and flat band both are the same thing. Right. So when you are applying positive voltage at the gate, what will happen? At the sheet, positive charge would come. Now what this positive charge will say? It will say to holes go away, because positive charge will reflect the holes. So it will tell holes to go away. So this hole will go downward, this hole will go downward. So it is telling the holes to go away. Right. Now you might be thinking that, sir, holes are going downward. That means here at the layer a lot of holes will be piled up. No, this will not happen. Why so? Because battery will provide the electrons. So basically the thing is electrical neutrality will be maintained. Holes are going downward. That means electrons are coming and they will be nullifying these holes. So what is actually happening? That this hole will go downward, then this hole will go downward. In that manner, holes will keep on going downward. So what will happen? These guys are losing their holes. Who are losing their holes? These guys are losing their holes. Is that understandable to you? Because these holes are going downward, and if they are going downward, and then from the battery electrons are coming up and they are recombining those holes. So in that manner, what you are getting here? You are getting a depletion layer. Can you see this kind of depletion layer here? Along with that, if holes are getting lesser here, then electrons has to increase. Why so? Because, sir, n into p equals to ni square will always be maintained. So let's just say I am saying that here my hole concentration was 10 to the power 16. Because of this positive bias, holes went downward, electron got recombined here. So here the hole concentration has gone down to 10 to the power 14. So how much will be your electron concentration? That has to be 10 to the power 6, considering that ni equals to 10 to the power 10. So ni by default I am taking 10 to the power 10. Okay. So here if your holes were 10 to the power 16, your electrons were 10 to the power 4. Now here if the holes have become 10 to the power 14, so electrons have become 10 to the power 6. And now you know that why this will be called as depletion region. Because what is the total number of charge carriers here? Approximately equals to 10 to the power 14. What is the total number of charge carriers here? Approximately equals to 10 to the power 16. 10 to the power 16 is much larger than 10 to the power 14. That's why we will say that this particular region is depleted of charge carriers. Is that understandable to you? Okay. Well and good. So this is known as depletion region, and it will have some width. This width I am calling as XD. Now just think about it. If I increase the voltage, then what will happen? If I increase the voltage, then what will happen? This positive charge will say, as of now it is saying that I need Q1 charge. So with respect to Q1 charge, this depletion layer is providing you minus Q1 charge. Say yes or no? He was saying that here plus Q1 charge have been maintained. So plus Q1 charge will say that I need minus Q1 charge. So as of now it is providing minus Q1 charge. Now what if I increase the voltage a bit? Sorry, what if I increase the voltage a bit? That means some charge will be increased here. Previously, let's just say it was 5 coulomb. Now it has become 6 coulomb. So with respect to 6 coulomb, these negative ions will provide the negative charge. What does that mean? Depletion width has to increase. Say yes or no? Here, who are the major guys who are providing the charge? These guys. This is providing the charge. These guys are giving you minus Q1 charge. If you say I need minus Q1 plus dQ1 charge, that means what will happen? Depletion width has to increase. So after that, what will happen? More positive, that means more holes will be lost. More holes will be lost, and then depletion width will increase. So in that manner, now this will be the new depletion width. Depletion width will be increased. This will be the new depletion width. So if you are increasing the voltage, more and more positive charge is required. Because of that, more and more depletion width we are getting. Is there any metallic plate? No. Why so? Because, sir, hole concentration very less, electron concentration very less. Sir, effectively 10 to the power 14 concentration you are having. Sir, this much low concentration you are having. Is it like a metal plate? Absolutely not. So it is like a metal oxide semiconductor. Metal oxide semiconductor. And now if the electric field is coming, electric field will come from the positive charge. If it comes, it will penetrate through the semiconductor. It will penetrate through the semiconductor completely. It will penetrate through the semiconductor completely. So what do you see here? as I change the voltage, let's remove this, let's remove this, let's remove this one as well. So as I increase Vg, depletion width will increase. Now how this is helpful for us? So let's try drawing it. Let's try drawing the equivalent. This particular node is gate. Which node is gate? This node is gate. Sir, after that there is a metal connected. Then sir, for some distance, for TOX distance, this is my TOX. Then sir, for TOX distance there is a oxide. For TOX distance there is oxide. Right? Then for XD distance there is a depletion layer. And after that neutral region is there. After that zero body bias is there. This is the zero body bias. This is your body. Now you know that sir, whatever this I will connect as ground, so this will also be at ground only because these are the neutral region. Right? So here what you are getting? Here you are getting depletion region. This is your X depletion, or XD I will write down. XD depletion region I am getting. Now in this depletion region negative charge is there, but here what will be the permittivity? Sir, here the permittivity will be epsilon OX, and here what will be the permittivity? Sir, here the permittivity will be epsilon SI. So what will be the equivalent? Equivalent will be two capacitors like in series. Two capacitors in series. This is your gate, this is your body. So I am calling this as C, capacitance between gate and body. Is that fine for you? Okay. So this capacitance I am calling as oxide capacitance, COX. What is the value of this one? Sir, epsilon OX divided by TOX. Multiply with the area. And this I am calling as depletion capacitance. What is the value of this one? Epsilon SI divided by XD multiply with the area. So what will be the capacitance between gate and body? Sir, that would be COX into C depletion divided by COX plus C depletion. And now you know one thing. What do you know? That sir, if Vg increases, then depletion width increases. That means if Vg changes, forget about increasing or decreasing. I am just saying that if Vg changes, or let's write down if Vg increases, then what will happen? Sir, XD will increase. If XD increases, then what will happen? C depletion will decrease. And if C depletion decreases, then what will happen? This guy will also decrease. That means your capacitance is depending on the applied voltage, and this is what we wanted. As I am increasing the applied voltage, it would require more and more negative charge, because here positive charge is being compiled up. If positive charge is being piled up, then it will require more and more negative charge. Here electrons and holes are not enough to provide positive or negative charge because they are very minute. They are in a very less numbers. That means who will provide the negative charge? Sir, these ions will provide the negative charge. This negative ion, they are providing the negative charge. So if they say that we need more positive charge, that means more negative charge will be required here. That means the depletion width has to be more. So as you increase this positive voltage, depletion width is increasing. Because of that, your C depletion is changing and your capacitance between gate and body is also changing, and this is our required task. Here I said that it should be lesser than V1. What is the meaning of this lesser than V1? The meaning is hole concentration should not get lesser than the electron concentration. Here in this depletion region, here what is the hole concentration? So 10 to the power 16. What is the electron concentration? 10 to the power 4. Surely it is p-type. This will remain p-type only. But in the depletion region, it should not happen that, sir, hole concentration has gone to 10 to the power 9 and electron concentration has gone to 10 to the power 11. This is not happening. That means still your hole concentration is higher than the electron concentration. So if I draw the concentration plot, so in the bulk, in this particular region, you know that, sir, my hole concentration is 10 to the power 16 and my electron concentration is, let's make it a bit more nearer. Okay, electron concentration is 10 to the power 4. right? And let's just say somewhere in between 10 to the power 10 is there. This is your Ni. Somewhere in between, this is your Ni. Ni is, this is showing 10 to the power 10. Fine. So this is on the log scale. We are showing it on the log scale. Okay. This would be shown on the log scale. So what is happening here? Concentration is going down, but it did not touch 10 to the power 10. Concentration is going down, but it did not touch 10 to the power 10. That means best case it could be, let's just say it is 10 to the power 11 at the surface, or it could be 10 to the power 9. But still holes are more than the electron. Still your holes are more than the electron. So here whatever the condition that we are studying as of now, the V1 is applied in a manner that P is always greater than N, even in the depletion region. Even in the depletion region. What is the depletion region? Sir, this is the depletion region. This is the depletion region. So just here, just before the depletion region, holes are greater than the electrons. But after that, holes are becoming lesser and electrons are increasing, but they did not increase in a manner that they are suppressing each other. P is still greater than N. So this is the condition. Is that understandable to you? All good? All fine? And it also explains that why it is not working as a metal, because carrier concentration are actually very, very, very low. So these guys are very low, 10 to the power 11, 10 to the power 9. I will neglect these guys. Why I am neglecting these guys? Because they are very low, no? Very low compared to these guys. So they will always be neglected. That's why we say it is depletion layer. People don't even talk about these holes and electrons, but they are present. They are present in a very lesser manner. So what is the meaning of depletion layer? Completely depleted of charge carriers? No. Charge carriers are there, but they are much lesser than the equilibrium condition. Okay. So can you try drawing the Venn diagram? I think you should be able to draw the Venn diagram. Electric field direction, you know. Along with that, you know that, sir, electron concentration is increasing, hole concentration is going down. So based on that, you can draw the Venn diagram, or you can draw the Venn diagram with respect to electric field as well. So let's draw it with respect to electric field. So last time as well, we have drawn the Venn diagram, no? Or I forgot it. Okay, yeah, did not forget it. So this was our accumulation mode, and this is known as depletion mode. What it is known as? This is known as depletion mode. Depletion mode. Depletion mode of operation. Okay. So whatever that is necessary, everything has been written on the screen. Okay. This diagram has been made, and let's draw the Venn diagram now. So electric field direction, you know, this is the direction of electric field from the metal to oxide. From the metal to oxide. Just tell me one thing. What will you tell me? That you have applied positive voltage at the metal, then what will happen? The Fermi level will come down, right? The Fermi level here, metal Fermi level will come down. Let's just say, or if we are not making it in the same way, like previously if it was here, then it will come down. It will come down a bit, right? It will come down a bit. So this will become your EFM. Okay. And EFP remains as it is. EFP remains as it is at its own place. There is no current, so there will be no slope. Slope will be there in the conduction band, valence band, and intrinsic Fermi level. So with respect to electric field direction, you can tell the slope. What will be the slope? Sir, this will be the slope, because in the direction of electric field, the slope has to be positive. What is the direction of electric field? Sir, this is the direction of oxide electric field, and sir, this is the direction of electric field in the silicon, right? So in the direction of electric field, slope will be positive, like this, right? So what we do? We will draw the diagram. Here nothing interesting is happening. This remains as it is, but this is how I will draw it. Let's not show the depletion width so much, because furthermore bias also we will increase. So let's show the depletion width this much only. Same goes for valence band as well. And same goes for intrinsic Fermi level as well. right? Again, let's make it more clear. They are not touching each other like this. These slopes are same. The gap between EFI and EFP has decreased. The gap between EFI and EFP. This was the gap here, but now the gap has decreased. What does it tell you? That means the whole concentration has gone down. Or you can say from EV, this has gone away. Fermi level has gone away from EV. What does that mean? Whole concentration has gone down. But still, holes are majority. Why you can say holes are majority? Because still your Fermi level is below the intrinsic Fermi level. If your Fermi level is below the intrinsic Fermi level, that means it is your P type only. So still here you are maintaining P type, but again the whole concentration has decreased, right? And this much I can say, this is my depletion width. This is my depletion width. I can show this is my depletion width. Again, can you let me know what will be this much of width? This is your applied bias. Can anyone tell what is this? This is your QVX. Since we are showing the energies, so we will show QVOX. And can anyone tell what is this? This is your surface potential. In the diagram, how will you show the surface potential? This is your surface potential. This is your surface potential, right? From now onwards, I will be calling this as x equals to 0. This is my x equals to 0, and this is my x equals to infinity. This point is x equals to infinity. So from x equals to 0 till x equals to infinity, whatever the potential, at x equals to infinity, what is the potential? 0. So if this point is x equals to infinity, this point is also like x equals to infinity only. Say yes or no? Because whatever the potential that you are getting here, the same potential you are getting here. So it is the potential between x equals to 0 and x equals to infinity. What is that? That is your surface potential psi s. If someone asks you, sir, what is the potential between these two guys? Then you don't know as of now. We will develop a formula, but as of now you don't know, sir, what is the potential between these two guys. But what is the potential between surface and the 0 potential, which is x equals to infinity? That potential is surface potential, phi s. So phi si and phi s both are the same, both are the different thing. Phi si is the work function potential, which is a complete different thing, right? But as of now, we are not caring about work function. Why we are not caring about work function? Because I have made sure one thing. What I have made sure? That sir, metal and my semiconductor work function are same. Okay, so all this diagram we have seen, and this is my Q phi s. And as always, you know that gate voltage will be distributed among two guys, oxide and surface potential. So this will always be maintained. Okay, let's see more diagram. We will draw the diagram of charge density, and then we will draw electric field, and then we will draw the potential plot. Try doing it on your own, because we have studied PN junction, then we studied accumulation mode. Here you should be able to draw these diagrams. So positive plate will come here, positive layer will come, but that will have a very minute width, very minute width. I just need to show it, otherwise, but the width is nearly 0 nanometer. Inside the oxide there is no charge, and here there is negative charge. Till what point? So till the depletion width. Till the depletion width. Till the depletion width there is a negative charge. This is plus plus plus. This is minus minus minus. Okay. Can anyone tell, sir, what I should write down here? Minus QNA, right? Charge density. Charge density means coulomb per centimeter cube. So how much? Let's not write down anything. I will tell you later on what you should write down. Let's not write down anything. We are not writing down the magnitude as of now. Let's see the waveform, then we will talk about the magnitude. So let's first see the waveform. Now what I need to do? Sir, I need to integrate this and then divide by epsilon. So sir, when I integrate this, sir, this will have nearly infinite slope. And then sir, I need to integrate 0, that means constant. One interesting thing will take place here. Sir, what will happen? Boundary condition. So let's apply the boundary condition here. So this is the oxide and this is the semiconductor. So although we have already seen it, but still I am going to show it. Epsilon OX, EOX, epsilon SI, ESI. But what we care about? I am caring about the surface electric field, the electric field at the surface. So if I am caring about the electric field at the surface, that means I am caring about the electric field at surface, means electric field at this particular point. I am only caring about electric field at this particular point. Here, do you need to care about that, sir, this point, that point, this point? No. Why so? Because inside the oxide, the electric field is same at all the points. But here, if you integrate, what you will get? You will get a linear curve. No, you will get a linear curve here if you integrate, right? So if you get a linear curve, then you need to define where you are interested in. I am interested in the electric field at the surface. Here also, what is the electric field at the surface? That is EOX. Here in semiconductor, what is the electric field at the surface? That is ES. So epsilon OX, EOX equals to epsilon SI, ES. Okay. So from here, what you will get? Sir, ES is nothing but epsilon OX, epsilon SI, EOX. And I told you, what did I tell you? That epsilon OX would be roughly around 3.9, or what value I told, I don't remember. And this would be 11.7. So if you divide them, it would come out to be 1.1 by 3. So electric field at the surface would be 1 by 3 times of electric field in the oxide. So if this is EOX, then this value would be bit lesser, and then it will go till xt. So this is how the waveform would go. Why it is ending at 0? Why it is ending at 0? Because you know that, sir, this positive charge would be equal to this negative charge. What I am saying, sir, if this is plus q1, then sir, this has to be minus q1. Why is it necessary? To maintain the charge neutrality. Because the whole device, whatever the device that you use in your whole industry, in your whole history, whichever the device you see, this bottle is also charge neutral, right? Charge neutrality has to be maintained. Positive charge will cancel out negative charge. So if someone asks you, sir, how much positive charge has been applied here? So you don't know how much positive charge has been applied, but you know how much negative charge have been created here. So based on this negative charge, you will be able to tell how much positive charge have been applied. Okay, so this thing we will be doing when we do the derivations. Okay, so there I will ask you how much positive charge have been applied. You will say, sir, positive charge I don't know, but negative charge I can tell. How can you tell negative charge? Negative charge per unit area I can tell you, sir. How can you tell? Negative charge per unit area. Think about it. This is my box. Here I am having a concentration of Na centimeter cube inverse. Right? Every Na can have 1 coulomb charge. Sorry, not 1 coulomb charge, 1.6 into 10 power minus 19 coulomb charge. So how much total charge is there? Qna. So Qna coulomb charge is there per centimeter cube. If I talk about till xd, till the depletion width, how much charge is there? Then multiply with xt. So what you will get? Coulomb per centimeter square. That means charge per unit area. How much is that? Qna xt. The same kind of thing we did in our PN junction as well. Say yes or no? So if I write down the electric field value, if I write down this electric field at the surface, if I write down the electric field value, can anyone help me writing down the equation of electric field? Note the equation, you can call it formula. Electric field at the surface, what that would be? What was the formula of electric field? This was the formula of electric field we used to write down. If I am talking about surface, that means I am inside the semiconductor, so I can write down epsilon Si dot dx minus infinity to x. Right? Just one thing I would like to tell you, that if you are integrating with respect to x, that means you will put the limit in terms of x, right? So here you should put alpha actually. Are you able to understand this point? Like basically, if I integrate x dot dx and I am putting the limit of x, does that make any sense? If I ask you what is the value of f of 1, what you will do? Sir, you will integrate from 0 to 1 x dot dx. So why you did not put 1 here? Why you did not put 1 here? Why you did not put 1 here? So better what should be written? That if I am integrating, if my limit is x, then here x cannot be there. So better what I should write down? Alpha dot dx. Alpha dot dx. Sorry, alpha dot d alpha, not alpha dot dx, alpha dot d alpha. So I will solve it. What answer I will be getting? Alpha square by 2, and then I will put the limit 0 to 1. Answer will come out to be 1 by 2. So this does not make any sense. If I put 0 to x, x dot dx. So I should put alpha dot d alpha. So similarly, here I should put this particular thing. Now, what will be the electric field here? This is our ES, no? So I'm writing down the value. Let me know, are you guys agreeing to this or not? The value is charge density per unit area divided by epsilon. What does this show? Rho dot dx divided by epsilon. This is your charge density per unit volume dot dx multiply with centimeter. So what you will get? Charge density per unit area. Here I should not put this negative sign. Charge density per unit area divided by epsilon. So how much charge is available here? QNA XD divided by epsilon. Epsilon of what? Semiconductor. So what answer you will be getting? QNA XD divided by epsilon SI. Is that clear to you? This point is at 0. Right? This point is at 0. Here the electric field is 0. I know that, sir. After the semiconductor, electric field is not being penetrated. So here electric field is 0. All the electric field is there between these points. Whatever the electric field is available, that is available between these guys. And in the diagram, this much is this portion. Right? If I call this point, this is your TOX and this is your XD. So your electric field is available between, this was your TOX plus XD. So electric field is available between TOX plus XD only. So that I have shown here. I need to find out this magnitude. I know that this total area would be this magnitude only. Basic mathematics. This total area would be this magnitude divided by epsilon. What we are doing, we are integrating. So let's just say I need to integrate this particular part. So what answer I will get? So this answer you will get. If I ask you what is the magnitude here, what you will say? So total area of this one. So that will be the magnitude. So similar thing I am doing. What will be the magnitude here? Total area of this guy. Mathematics, nothing else. Again mathematics. And here, what is the total area? Sir, XD multiply with this magnitude. What will be this magnitude? This was your semiconductor. Concentration is Na. Every atom will give you one charge, QNA. So QNA, Coulomb per centimeter cube. That is the concentration. That is something we were expecting. Charge density. So Coulomb per unit volume. So here what you will be getting? QNA. Okay. So QNA XD divided by epsilon, that will be your electric field at the surface. So electric field at the surface, I should show it in this manner. Electric field. Here you will be able to understand that I am not talking about energy. Okay, this is bad habit that I am having. That better I should show it with a different color, with a different notation, right? Because one notation we are using for electric field and one notation we are using for so this is the scenario we are doing. Okay, so that is coming out to be QNA XD divided by epsilon SI. This is the electric field at the surface we are getting. Direction and all we don't care. We already know what is the direction, right? This is the direction. Okay, so sometimes it is asked like what is the electric field. Now let's talk about the surface potential. Can anyone tell what will be the value of surface potential? I hope you will be able to tell. Basically, we need to go from here to here. What we need to do? Again, integrate. Integrate, but never forget, you need to take the mirror image as well. So what will be the integration? This will be the integration. Say yes or no. Here if I integrate, let's use the different color of pen. So this is how it will go, then this is how it will go, and again some area, and then this will be the waveform. But you need to take the mirror image. So if I take the mirror image, so you understood, sir, this kind of waveform I will get. If I take the mirror image, then this is how it will look like. From where should I start? Can anyone tell what is the voltage? What is the value of potential at the gate? What is the value of potential at the gate? So that is Vg. And what is the value of potential here in the semiconductor 0. That means, sir, this is Vg and here it will become 0. So what do you understand by this? This waveform I need to follow. This is just the mirror image, mirror image I have taken. This waveform I need to follow. So how will I follow the image? This is how I will follow the image. I hope you will be able to do the integration. Again, mathematical part. This is how I will do it. Sir, why it is becoming curvature? Why it is having curvature? Because this is function of x, right? This field here is function of x. If it is a function of x, if something is function of x and you integrate it, what you will get? X square. So this is your x square, right? So here what we have applied? Vg. What is this? This much potential? That is Vox. And what is this much potential? This much potential is phi s. Say yes or no. And from here as well you can say Vg equals to Vox plus phi s. Say yes or no. Do you agree to this point? Vox is the whole potential. I hope you are able to understand the meaning of Vox. Vox means this much potential. Like if someone asks you potential between two different points, that would be different. What that would be? So that potential would be, let's just say I ask you potential between these two guys. So that would simply be this much area. If I talk about Vox, what I am talking about? I am talking about the potential starting from here till here. That means inside the oxide, across the oxide, how much potential is being dropped? That is Vox, and that is simply equals to EOX into TOX. This I should show as EOX. So electric field multiply with this TOX. So this much potential is your Vox, and this much potential, this much area is your phi s. So can anyone tell what will be the magnitude here? So that would be half into XD into ES. That would be your phi s. Half into base into ES. Again, ES I am showing by this. Should have been shown by this. How we are showing here? This is how we are showing here. So electric field at the surface. Like if you are aware, then you are able to understand everything. Otherwise, you will not be able to understand. I cannot do anything. I hope you are aware. You are watching with the open eyes. Like what is the potential drop? Like otherwise, you will remember the formula. This is the surface potential, but you would never understand the meaning of surface potential. Surface potential means potential starting from x equals to 0 till this point. Vox means potential across the oxide. If someone asks you what is the potential from this particular point, from the metal to complete semiconductor, from metal to complete semiconductor till x equals to infinity, what will be the potential? So that would be Vg. Vg would be equal to, sir, Vox plus phi s. Is that clear? I hope it is clear. And all the formula and everything, like if these diagrams are there in your mind, then no formula you need to remember. Everything you will be able to derive. So if I talk about the surface potential, what is the formula we are getting? So that is, sir, half into base depletion width multiply with the surface electric field, right? And what is the formula of surface electric field? So formula of surface electric field that you have got is, sir, QNA XD divided by epsilon SI. So can I put that formula here? Absolutely, you can put. So first formula is this. I will keep that in a box. That this we need to keep in mind. After that, I am replacing the value of ES, which is QNA XD divided by epsilon SI. So here phi s would come. So what you will be getting from here, this XD square would, what you will get here is that QNA 2 epsilon SI XD square. So from here I can get the formula of depletion width, which is coming out to be 2 epsilon SI upon QNA phi s. This is the formula of depletion width. In PN junction, we have studied the formula of depletion width. What that was? In PN junction, you can simply relate it. PN junction under root 2 epsilon by Q. There would also be silicon only 1 upon Na plus 1 upon Nd into built-in potential. So in place of built-in potential, you are having built-in potential is equivalent to phi s. 1 upon Na plus 1 upon Nd is simply equivalent to, I am not saying equals to, equivalent to, that is equivalent to 1 upon Na. Is that clear to you? So what formula you will get? 2 epsilon Qna phi s. So this is like a built-in potential only. Like what was your built-in potential? In PN junction, whatever the potential that you got across depletion width, that was your built-in potential, right? This was your built-in potential in PN junction. So let's make this diagram here as well so that you guys would be able to relate in a better manner. So this was your built-in potential in PN junction. This was your built-in potential in PN junction, right? And in MOSCAP, what is the scenario? In MOSCAP, here you are getting a depletion width, right? So this is your surface potential. This was your depletion width here, and this is your depletion width here. This depletion width was XD. We used to call this depletion width as W depletion. So everything you will be able to relate now. All good? All fine? Okay. There also we find out electric field, all these things we find out there. There also electric field came out to be, there also built-in potential. What was the formula of built-in potential? Sir, half into depletion width into the maximum electric field. Half into depletion width into maximum electric field. You remember the diagram? You remember this diagram? So this was your depletion width. This was your Emax, right? So what will be the area? Half into depletion width multiply with Emax. That was your built-in potential. I told you built-in potential is important. We drew the diagram of built-in potential as well. In this manner, we drew the diagram of built-in potential as well. I told you built-in potential is important, but who knows, they ask the potential between 2 points. So they can ask the potential between 2 points. So what you should have? You should have the ability to compute the area. Say yes or no. Okay. So all these points we discussed in PN junction, similar thing is happening here as well. So this is how you can relate. Okay. So this formula we have got. This formula you will remember. This formula also you will remember. And surely this formula also you will remember. And no need to remember, by the diagram everything should be clear. My electric field. So you can call it surface electric field. Surface electric field. Or they can call it maximum electric field inside the semiconductor. Isn't it like a maximum electric field? Like inside the semiconductor, here you are having zero electric field, and this is the maximum electric field of the semiconductor, because this is the part of semiconductor. In semiconductor, what is the maximum electric field you are having? That is ES. So you can call it surface electric field, or better name is maximum E field inside semiconductor. Same formula we studied in our PN junction as well. Same formula. Say yes or no. Right? In PN junction, what we used to do? This diagram we used to make. Right? So this would be positive charge, this would be negative charge. Although opposite I have made. There what we used to do? PN junction we used to take, no? So this side would be negative. This is P side, this would be negative, this would be positive. Right? So in PN junction, what we used to say? So what is this? This would be equals to area of this one. QNA XD. So here magnitude would be QNA XD divided by epsilon SL. Right? Similar thing. QNA XD divided by epsilon SL. So similar thing is there, same formulas are there. Same, ditto same formulas are there. Okay. Just one more point here. We will talk about gate voltage now. Okay. What we will talk about? Gate voltage. So gate voltage is nothing but the oxide potential plus the surface potential. Okay, so how you can write down oxide potential? Just listen to me very carefully. I will write it down in this manner: Q depletion divided by COX. Do you agree to this point? So let's make the diagram again. Very, very important point it is. So you need to take full concentration. That's sir, how did you write down VOX equals to Q depletion COX? Okay, very important point it is. This is your oxide. I don't care about the oxide. This is your oxide. Okay, this is your metal. Here you are applying positive bias. So on the metal here, positive, 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 positive have come. Here depletion width has been framed. Here your this width is TUX and here your permittivity is epsilon OX. So what will be your capacitance per unit area? Capacitance per unit area. What will be your oxide capacitance, oxide cap per unit area? Sir, that would be epsilon OX divided by TOX. Say yes or no? Area I have divided, right? Now, how do you define the capacitance? Another way is there, no? What is the potential that has been developed here? Sir, VOX. So, VOX, Q equals to CV. Q equals to CV. So, it would be Q divided by V. So, charge divided by the potential. What is the potential? VOX. How much charge you will write down? So, sir, across the oxide, this is my oxide. Sir, across the oxide, here there is positive charge. And sir, here there is some negative charge. Right? So I need to put down the charge. Either I can write down this charge which is plus Q1 or I will write down here minus Q1. So my answer would be, sir, my oxide capacitance per unit area would be charge divided by voltage. This charge, since this is per unit area, this is your per unit area. So here also I will write down charge per unit area. This is your charge per unit area. So I need to write down the charge per unit area. Can you comment on this positive charge? No, sir. How much positive charge applied, that I don't know. It would depend on the Vg value. I don't know how much positive charge have come, but I know one thing. How much is this negative charge? If you know minus Q1, then you already know plus Q1, no? If you know minus Q1, then can you put the Q1 value here? That's it. So how much charge you are having per unit area? Charge per unit area. How much is this charge per unit area? That is Q Na xt, and that charge I am calling as Q depletion. Sir, if we are talking about negative positive charge, then sir, here there are some electrons as well, no? Right? These electrons are known as inversion charge. Which electrons are there? These electrons. Which electrons? These electrons. 10 to the power 9. These electrons are there. So this is your inversion charge. Sir, inversion charge is also there. But we will always ignore the inversion charge until a certain condition. Sir, what is that certain condition? I will tell you. Inversion charge will always be ignored. And I will verify it with respect to a numerical problem as well. Sir, whatever the charge that they give, that is much lesser than compared to this particular charge that we are getting. In XD width, in this XD width, whatever the charge that we are getting from these negative ions, that charge is, that means Q depletion is much larger than Q inversion until a certain point. What that point would be, we will talk about it. But until a certain point, your Q depletion would be much larger than Q inversion. That means your Q total, if I talk about Q total, which should be Q depletion plus Q inversion. So you will ignore the inversion charge. This charge will be ignored. We will verify it with respect to a numerical problem as well. that sir, this inversion charge was actually very, very less. We can ignore this inversion charge. Okay, so as of now you might not be able to understand theoretically, but with numerical problem you will be able to understand that sir, why we are ignoring it. But up to a certain point we will ignore. After that it will also start coming into action. So did you understand what we did here? So here what I need to put? I need to put this negative charge. What is that? Q Na XD. So instead of writing this particular thing, here I will only write down Q Na XD. But notice one thing, that this is your capacitance per unit area. Okay, COX dash, capacitance per unit area. Sir, where the inversion charge is gone? Sir, electrons were also there. No, sir, they will also give you negative charge. Why you are not considering that negative charge? They are very minute. We will ignore them. How much minute they are, we will see it with respect to a numerical example. Don't worry about it. So inversion charge was there and depletion charge was there. So I will call this as depletion charge. Depletion charge per unit area was also there. Inversion charge was also there. So we are ignoring the inversion charge. We are only taking that depletion charge into action. That would be QNAXT. So that I have put here, divided by VUX. That is my COX, but from here if I need VUX, what that would be? Sir, QNAXT divided by COX dash. So that I have put here. Okay, plus surface potential. So what do I do? QNA COX dash. Can you put the value of epsilon? Sorry, can you put the value of XD? Yes, sir. That would be 2 epsilon SI divided by QNA phi S. Not phi SI, phi S. Okay, what I am putting? Phi S here, not phi SI. Phi SI is the work function plus phi S. So what you are getting here? Sir, under root 2 epsilon SI under root QNA, pure QNA. So this will become under root QNA psi S divided by COX dash plus psi S. This is your VG. This is the VG that we are getting. So like a lot of student, even in the textbook this formula is written and people actually remember it. Okay, like if you are preparing for gate examination, a lot of people remember it. So if you can remember, try remembering it. 2 epsilon QNA psi SI, psi S, not psi SI, psi S. But in a longer run it would be tough to remember. What I would say, in longer run it would be tough to remember, but I will be using this formula directly. Somewhere this formula will be used. In our analysis, this formula will be used somewhere, but I will be using it directly from where it came. Very simple step. Within 15 seconds, you will be able to derive it in the examination. What you would think, sir, Vg equals to Vux plus pi S. Okay, Vux. So that would be QNA XD divided by COX dash. XD, that is coming from under root 2 epsilon by QNA psi S. So under root QNA, this will get cancelled out. So under root 2 epsilon QNA psi S divided by COX dash plus psi S. So within one step, I guess without even doing the calculation, you will be able to write down this particular thing. So even if you feel like that, sir, I don't want to remember the final result, remember this particular thing. From here you can derive it. At least XD formula you will be remembering, no? XD formula you will be remembering. I hope this formula at least you will remember. This formula you will remember. That is very simple. W depletion formula, same formula. So this you will not be forgetting, right? And let's remove this one. This you will not be forgetting, sir. Surface potential. This diagram will be there in your mind. Which diagram? So this diagram will be there in my mind. Half into base into height. ES. What will be ES? Sir, whatever the negative charge we are getting divided by epsilon. That will be my ES. So QNA XD divided by epsilon. So derivation is there in your mind, then all these formulas are simple. Otherwise, they will become very difficult. In EDC, people feel like that, sir, there are a lot of formula. But starting from the basic semiconductor physics, I made sure that you will never have the pressure of formula. In whole gate preparation, studying from this platform, you will never have the pressure of formula. No matter whichever the subject you are studying. It's just that your eyes should be open, your mind should be open. And proper reasoning would be given. For each and every step, proper reasoning would be there. As of now, one reasoning I am missing out, that sir, why you ignore this inversion charge. This reasoning also I will give you. And this charge will be ignored until a certain point only. And that point is known as threshold voltage. After threshold voltage, this guy will come into action and depletion charge will be ignored. Okay, so they go one by one. That sometimes for some time only depletion charge will be into action, and after some time only inversion charge will be into action. We will draw the waveform as well. It will be clear to you. But as of now, you will remember one thing, that sir, in the depletion region, what we are talking about? We are talking about, sir, depletion mode of operation. Depletion mode of operation. In depletion mode of operation, I am not applying very high gate voltage. Very high gate voltage I am not applying, sir. Decent gate voltage I have applied. Because of that, band bending and all these things have taken place. Depletion width we are getting, that is changing with respect to the applied voltage. Okay, well and good. It's just that we can see the formula of potential as well. So what was your potential curve? What kind of potential curve you got? So this kind of potential curve we got. So this kind of potential curve we got. This was the scenario here. This was the scenario here. And this was the scenario. So sir, I know this is Vux. This is Vux. If someone talks about Vux, sir, I can directly say it is Ux dot Tux. This width is Tux. And sir, this value is phi s. This value is phi s. Now what I am saying, here in this region, whatever the potential you are getting, that I am showing by phi x. So what is phi x? This point was our x equals to 0. This was your semiconductor, right? So this point was x equals to 0, and here you are having x equals to infinity point, right? After that you are having x equals to infinity point, and this point is x equals to 0. So what is your phi x? Phi x is the potential between x equals to x and potential difference between x equals to x and x equals to infinity. What is the potential at infinity? That is 0, right? So your phi x would be given by, so direct formula I am writing down, and here this diagram is also not correct. Why it is not correct? Because after xd only it is gone, right? That is not exponential. After xd only it is gone. After xd, potential is 0. Right? So this much distance was your xd. So which relation it is following? Sir, square relation it is following. Which relation, sir? Square relation. So this phi x is given by, so direct formula I am writing down, that is phi s into 1 minus x by xd whole square. And you will be able to relate to this formula as well. How you will be able to relate? Sir, at x equals to 0, that means at the starting of the semiconductor, sir, what is the potential? X equals to 0, sir, what is the potential? Phi s is the potential. Sir, at x equals to xd, what is the potential? At x equals to xd, sir, what is the potential? At x equals to xd, come to this diagram. At x equals to xd, this is your x equals to xd, no? You can call it x equals to infinity, or better we can call it x equals to xd, because this is your x equals to 0, this is my depletion with xd, so this point would be x equals to xd. So whatever the potential at x equals to xd you are getting, the same potential at x equals to infinity you are getting, 0 potential. So potential at x equals to xd, what that would be? Sir, that would be nothing but at x equals to xd, so what that would be? 1 minus 1, that would be 0. What will be your potential at, let's just say someone asked at xd by 2. So what you will put? Sir, I will put, in place of x I will put xd by 2, so this would be 1 by 2, 1 by 4, so that would become phi s by 4. Okay, so phi s 0, phi s by 4. So here this was your phi s, at xd by 2, in between it would become phi s by 4, and here it would become 0. At other points as well you can find out the potentials. Is that clear? So sir, how this formula came? Derivation not important, very simple derivation it is. Basically what we are doing, you write down this waveform in terms of x, you write down the electric field here in terms of x, then you integrate it, you will get this answer. But that derivation we are not going deeper into that. It's just that, sir, this particular expression, this particular waveform I am representing by phi x. Okay, in Niemann questions are given. Okay, in Niemann questions are given from here. So this particular waveform is given by phi x, sir. So for this phi x, what I will do, I will put it as, I know that at x equals to 0 I am having phi s potential, and at x equals to xd I am having 0 potential. So this is the relation that I am getting. Formula is also, we are able to verify the formula as well. Well and good. Let's talk about the carrier concentration. What we will talk about? carrier concentration. Which carrier concentration? Electron and hole concentration at surface. That we need to talk about. So this is my Q phi f. What is this? Q surface potential, right? What this was? This was your Q Vux. This is your Q phi s. So what will be this point? These two guys would be Q phi f minus phi s. So yes or no? So can anyone tell that, sir, what you are writing down here, that Q phi f minus Q phi s equals to kT ln hole concentration at the surface divided by Ni square. And what will be your Q phi f? Q phi f would be kT ln hole concentration here. What is the electron concentration here? Hole concentration is Na, and what is the electron concentration? So that is Ni square by Na. So Q phi f could be written as Na divided by Na by Ni, not Ni square. KT ln Na by Ni. Why Ni square I am putting? Ni. Okay. So from here what you will see, that, sir, minus Q phi s, this goes here. So kT ln Na by Ni. If this goes here, then what will happen? Ps by Na. This is your Q phi f. If this goes here, this would become Ps by Na. So from here, what is the value of Ps you are getting? Na e to the power minus Q phi s by kT. And it is pretty obvious as well. The same formula we are getting. Whatever the formula that we got previously, it is the same formula, nothing else. And what will be your Ns? What is the meaning of Ns and Ps? I hope you know what is Ns and Ps. This is your Ps is your hole concentration at surface. Right? So Ni square by Ps, because you know that at any point Ps into Ns would be equals to Ni square. Right? Electron and hole concentration, multiplication of electron and hole concentration would be equals to Ni square. So Ni square by Ps. So what you will be getting? Let's keep it as it is. I don't need to write down the formula. Right? So let's keep it as it is. Or you can simply put it would be Ni square by Ps is Na e to the power. So this e to the power, this guy is go upward, Q phi s by kT. Right? Ps value I am putting Na e to the power minus Q phi s by kT. This goes upward. So what is your Ni square by Na? Ni square by Na was the previous hole concentration. So in the bulk, whatever the hole concentration you are getting, not hole concentration, electron concentration. So in the bulk, whatever the electron concentration you are getting, that is multiplied with exponential of Q phi s by kT. And it is pretty obvious as well. Why is that so? Because you know that, sir, hole concentration is going down and electron concentration is increasing. So sir, this guy is increasing actually and this guy is going down. So phi s surely I will take positive, because I know that, sir, hole concentration is actually decreasing and electron concentration is actually increasing. But phi s value will be maintained in a manner that Ps is still greater than Ns. Okay, very simple thing. All fine about it. I don't think anything tough about it. Same formula we are getting, ditto same formula. In the accumulation mode, this was positive. So your mind should be clear that whether the concentration will increase or decrease. Based on that, you will be able to write down the formula. In the examination, you will not think, sir, what is the formula? No. I know that my hole concentration is Na, my electron concentration is N. Now it will increase or decrease. Let's just say I get to know that my holes are increasing. That means surface potential divided by kT. I get to know that my electron concentration is decreasing, divided by kT. So whatever that you get to know that this is increasing or decreasing, based on that you will be able to write down the formula. Are you able to understand this point? Yes, sir. Now here at the surface I am asking, if I ask you at any point, let's just say at this particular point I ask you, what is the electron and hole concentration? Will you be able to tell? At any random point, at some x equals to x. Say yes or no. Will you be able to tell? So can I write it down in this manner? at x equals to x. This is your x equals to x. My whole concentration would be Na. Do I have the next page? No. So where should I write down? Not having enough space. Although in one numerical I have already asked it, but yeah, still, like, are you guys able to relate that, sir, it would be equals to e to the power minus q phi x by kt. What is the value of phi x at surface? So that is phi s. Phi x at the surface is phi s. So this phi x you put here, same value you will get. What is the value of phi x at in the bulk? In the bulk, basically here. If I ask you what is the value of for x greater than 4x greater than xd, what will be your phi x? So that would be 0. Yeah, one more thing you will take care that this formula is applicable between 0 to xd only, right? Because you know that for x greater than equals to xd, the potential is 0 only. So curve is there in your mind, the potential will be 0 only. So potential is 0 only, right? So this potential will be 0. Where? At x equals to xd. At x equals to xd, this potential will be 0. So e to the power 0, what that will be 1. That means my whole concentration at x equals to xd should come out to be phi x is 0 at x equals to xd. That is 0, so that should come out to be Na. Are we getting it? Yes. Here the concentration is Na only. In this particular region, from here to here, the concentration of hole is Na and concentration of electron is Na square by Na. And at the surface, if I ask you, then what will be the value? In place of phi x, what you will put? Phi s. At the surface, in place of phi x, what you will put? Phi s. So very simple formula these are, and these are important because questions have not been asked on these formulas and they are mentioned in Niemann. Whatever that is mentioned in Niemann and questions have not been asked, that means they are important for you because questions are going to come from these particular topics. Is that clear? So this you will not mug up. Most of the chances are there that they will ask at the surface only. But even if they ask at a random point, still you will be able to tell, say yes or no. If they ask me what will be my whole concentration at x equals to xd by 2, I will be able to tell that, sir, it would be minus q at xd by 2. What is the potential? At xd by 2, the potential is phi s by 4. Q phi s by 4 kt. This is the whole concentration at x equals to xd by 2. At x equals to xd, this is the whole concentration. At x equals to what this is? This is your x equals to 0. At x equals to 0, this is the whole concentration. If you know the whole concentration, you will be able to tell the electron concentration as well. Right? Well and good. Okay. Capacitance value. Do I need to explain it? No. Sir, positive charge we are applying, let's just say some positive charge 0.3 volt. So with respect to this 0.3 volt, we are getting it. Now, with respect to this 0.3 volt, what we have built up? We have built up a depletion layer. Some minority carriers are also there, but they are not very important because they are in a very less amount. Now what I am doing? I am applying some small signal here, 0.1 sin omega t. So if I here 0.3 voltage was there, let's not take 0.3, let's take some larger value, let's take 2 volt. So here 2 volt was there. With respect to 2 volt, what we were having? Plus q1 charge. So with respect to 2.1 volt, what I will have? Plus q1 plus dq1 charge. So if more charge is there, what it will say? I require more negative charge. Then what will happen? Depletion width will increase by a minute amount. So there is a change in depletion width as because of this small signal voltage that we have applied. Why it is known as small signal? Because amplitude is small here, no? That's why it is known as small signal. So this small signal, because of this small signal, there is a change. There is a change in the depletion width. Oxide remains as it is, COX remains as it is. COX remains as it is, but this guy is changing. Right? So what is your equivalent capacitance? So that would be COX into C depletion divided by COX plus C depletion. Okay, this will be the equivalent capacitance. Now if I sweep the Vg value, that means if I increase the Vg value, what I am doing? I am drawing the graph now. So I am drawing the graph of Vg versus the capacitance. So for negative gate voltage, I have already drawn, right? How it came out to be? Sir, it was COX. It was your COX. That came out to be epsilon OX A divided by TOX. Now for the positive voltage, what will happen? This was nothing but COX, which was epsilon OX A divided by TOX. Now as the gate voltage increases, you are going from here to here, gate voltage increases. As the gate voltage increases, what will happen? It will ask more and more positive charge. That means here we will require more and more negative charge. That means depletion width will increase. If depletion width increases, then what is your C depletion? So that is nothing but epsilon Si multiply with the area divided by X depletion, right? So that would increase. If this increases, then what will happen? C depletion would decrease, and because of that, what will happen? CAB would also decrease. That means with respect to the increase in the gate voltage, the capacitance will decrease. This kind of graph you will be getting. Till what point this kind of graph you will be getting, we will see that. Now what we are going to do, we are going to increase the Vg value. So as of now, at a particular Vg value, at a very small value, which was lesser than V1, the value which was lesser than V1, we saw what was happening. Here, what was the important condition? The important condition was this, that hole concentration was still higher than the electron concentration. Now if you more increase the Vg value, if you increase the Vg value more, what will happen? More and more holes will be reflected. That means hole concentration will go down, electron concentration will increase. Are you able to understand this point? What I am saying, if I increase the more Vg voltage, what will happen? More holes will go down. If more holes goes down, then what will happen? Hole concentration will decrease and electron concentration will increase near the surface. I am talking about near the surface. So near the surface, hole concentration will go down and electron concentration will increase. If I increase the Vg value more, if I increase more positive bias, then this value will go down and this value will increase. So from 10 to the power 11, we can come to 10 to the power 10. If my hole concentration is 10 to the power 10, then what will be my electron concentration? That would also be 10 to the power 10. So if I further increase my voltage, if I further increase my gate voltage, then hole concentration is going down and electron concentration is increasing. That's our next point. But before that, there is a numerical. We will solve it. But this is what we are going to do. Depletion mode of operation we are having. Then what we are going to do? We are further going to increase the forward bias. Positive voltage we are going to increase more. That means now we are applying our positive voltage greater than V1 but less than V2. So now what will happen? Let's draw the carrier concentration plot. So this was our Ni. This was our Ni. In the bulk, what I was having? This was my, in the bulk, nothing interesting is happening. This guy remains as it is. Everything is same here, right? So in the bulk, everything is same. This was your electron concentration. This was your hole concentration. Electron concentration, which we called as 10 to the power 16. And this is your hole concentration, which is 10 to the power 4. But because of the positive voltage, what happened? Holes got reflected. Holes are getting reflected, not reflected. Holes are being repelled because of the because of that. Hole concentration is decreasing near the surface. Hole concentration is decreasing and electron concentration is going up. So he is decreasing and he is going up, and there would be a point where both of them would meet. And at this point, N would be equals to P would be equals to Ni. What kind of band diagram you will get? Sir, band bending would be there, and here the gap would become 0. The gap would become 0 here, right? Band bending would be there, the gap would become 0. Okay, so here this gap has become 0. What does that mean? That means this was your Q phi f, right? And this was your Q phi s. So your Q phi f has become equals to Q phi s this time. This is the condition that you have got. Yes, sir. Okay, and electron and hole concentration has become equals to 10 to the power 10. If you further increase the positive voltage, then what will happen? If you further increase the positive voltage, then more hole concentration will go down and electron concentration will increase. So now, after that, after I further increase the voltage, what will happen? Electron concentration will become 10 to the power 11 and hole concentration will become 10 to the power 9. Is that clear? So this particular region near the surface, the region has started being inverted. Electrons are becoming majority in a p-type semiconductor. Do you remember the diagram? The diagram is this. We are having a p-type semiconductor. If we are increasing the positive voltage more and more and more, holes are being repelled, holes are going down, electrons will increase because equilibrium has to be maintained, mass action law will be valid, n into p equals to ni square will always be valid. So electron concentration increasing, hole concentration going down. At some point electron concentration will become more than the hole concentration, and that mode of operation is known as inversion mode of operation. Surely we will see it, but before that we need to solve this numerical. Calculation and everything would remain the same. After that calculation part is gone, only the conceptual part would be there. So we need to see the conceptual part. We will surely see it, but before that you solve this numerical, you would be able to solve it in a very easy manner. So it's up to you. You try doing it on your own. I will take a break and then I will come back. Okay. So depletion mode of operation we have already seen. I will draw the diagram. This is already done. Furthermore increased, more V will increase now. Then what will happen? N will increase, P will go down. This is known as inversion mode. Then more V will increase. Let's see what happens. Okay then. Yeah. So let me take a break and then I will come back. And you solve this numerical for now. Solve this numerical. Yeah, welcome back. So we will solve this question and then we will end this video. And in the next video, because it's been roughly around 3 hours, and in the next video we will see, like, we will further increase the forward bias or further increase the positive bias. So when we further increase the positive bias, then this kind of scenario we get that we have already seen. So right. Okay. So let's solve this question now. So did you try this one? I hope you will be able to solve this one. Any value is given, Ni value is given, right? Epsilon Ox is given, epsilon Si is given. What this is? Maximum electric field at the semiconductor interface. What is this Emax? This Emax is given. Emax is nothing but electric field at the surface, right? Which is equals to 1.7 into 10 to the power 4 volt per centimeter. Right? You need to find out the applied gate voltage, surface potential, all these things you need to find out. So ES is given, electric field at the surface is given. So will you be able to find out electric field inside the oxide? Because TOX is given, no? If TOX is given, I will be able to find out VOX as well. So I need to find out electric field inside the oxide. So can I find it out? Yes, sir. Epsilon OX, EOX equals to epsilon SI, ESI, or ES, electric field at the surface. Right? Epsilon OX value I am having, yes, 3.9. Electric field inside the oxide I need to find out. 3.9 epsilon naught, but epsilon naught will get cancelled out, no? So basically, very simple scenario is there that electric field in the oxide would be 11.7 divided by 3.9 into electric field at the surface. So electric field would be simply the 3 times of this thing. 3 into 1.76. 5.28 into 10 to the power 4 volt per centimeter. This is the electric field in the oxide. So if you know the electric field in the oxide, you would know the oxide potential as well, right? Sir, what that would be? Sir, 5.28 into 10 to the power 4 volt per centimeter. And what is the width? TOX is given as 10 nanometer. 10 nanometer is nothing but 10 to the power minus 6 centimeter that we have already seen. So what answer we are getting? Sir, 0. Or 52.8 millivolt. Say yes or no? This is your VOX. 52.8 millivolt. 10 to the power minus 2. So to make 10 to the power minus 3, what I did, multiply with 10. So 52.8 millivolt. What I need to find out? I need to find out the gate potential. So I know that gate potential is equals to VOX plus surface potential. So now my next matter of concern is this surface potential. This is find out. So surface potential I need to find out. What is given? Emax is given. Some relation is there. I know that, sir, some relation is there. Something I can do. So this, because of this surface electric field, I can try thinking of finding out surface potential. So what will be the first thing that will click to me? That's our surface potential. Like sometimes I will write down as this sign, or sometimes I can write down as this sign. Okay, don't get confused. Okay, I have the habit of writing down in this manner, but in the textbook it is written like this. So don't get confused with the notation. This is nothing but a surface potential only. So surface potential would be the first thing that would click to me. What that would be? Sir, half into base into height. Half into base xd into height es. That would be my phi s. This is the first thing as a student that would click to me. Right? Here we saw it. Half into base into height. Now the problem is I don't have xd. I don't have the depletion width. I remember the formula of depletion width, under root 2 epsilon by QNA surface potential. If I find out xd, for finding out xd, what do I need? I need surface potential. So surface potential I am not having, but I have done one thing here. What I have done? I can simply replace xd here. So what I will get? Phi s equals to 1 by 2 under root phi si upon QNA phi s es. Right? Okay. So if we see closely, then what I can see is that this will go inside. That would become epsilon si 2QNA es square. Say yes or no? Yes. So this formula we are getting. So do I need to remember it? No. Do you remember the formula of breakdown voltage? It came out to be somewhat like this only. Epsilon E critical square divided by 2QNA. So no need to remember, but from here, like how I will be thinking in the examination. This is how I will be thinking in the examination. That's why I need phi s. First I will be thinking about, sir, I need gate voltage. So VOX phi x. VOX I have find out. Phi s I need. Phi s, what first thing would click to me? Sir, half into xd into es. That is the first thing that would click to me. Now xd formula I can replace. This is how I can replace it. Now I am having all the values. Es value I am having, epsilon I am having, 2QNA I am having. So I will get the value of phi s. Right? So what I will get? Epsilon si 11.7 into 10 to the power minus 14. Yes, surface electric field 1.7 into 1.7 into 10 to the power 8 divided by 2QNA. Na, what is the value of Na? Na is 10 to the power 16. So you solve it, you will get the surface potential. So what I can see, so 10 to the power minus 3, 10 to the power minus 11. So this would become 10 to the power minus 3, and this is something that I needed. So only I need to do 11.7 into 8.85 into 1.76 into 1.76 divided by 2 divided by 1.6. So 100.23 millivolt we are getting.
And let me see the 10 to the power minus 3. This will become 10 to the power, yeah, 100.23 millivolt. So what will be the gate potential we are getting? So 52.8 millivolt plus 100.23 millivolt. So answer is 153.03 millivolt. Or answer would be given as 0.153. Let me check the answer if we are getting the same answer only. They are giving a different answer. 1.76 into 10 power 4 multiply with 3. Okay, here there is a mistake, I guess. 1.76 into 6 into 3, 5.28. 5.28 electric field inside the oxide we have got 10 nanometer would be 10 to the power minus 6. 10 to the power minus 6 we have done here, so it would become 10 to the power minus 2. So 52.8, everything is fine. Let me check why they are giving different answer here. QNAXD. Creation width. To QNA. Yes. I guess there is something wrong in the formation of the question. Because if I talk about the charge upon CUX, epsilon OX value is given, TUX value is given, I can surely find out the charge as well. QNAXD also I can find out. So it should come out to be same only. Let me check back the calculation. Okay, some calculation I need to check. Yeah, look, I just checked it. Nothing wrong here. What they have done, that is incorrect. Okay, we have done, that is correct. What they have done, they have subtracted it. Okay, this is the mistake they are doing. But both will be added, no? That's pretty obvious. We are not getting confused with the sign, right? Surface potential, whatever the answer you get, and oxide potential, whatever the answer you get, both will be surely added. That's it. Because gate voltage is VOX plus psi S, right? That's the scenario. So let me, yeah. So 0.153 I could have written volt. So that is the gate potential we are getting. Along with that, I will put a surface potential as well in the box, which is nearly around 0.1 volt. So this is your surface potential. Now what they are asking? Depletion width. Depletion width I can calculate. XD. Either you apply the formula. Which formula? You apply this formula. 2 epsilon QNA psi S. All the values you are having, you will be able to solve it. Or what I have? ES equals to half, sorry, phi S equals to surface potential equals to half XD ES. So XD would nothing be 2 phi S divided by ES. So 2 phi S, which is 0.1 volt, divided by ES. What is ES? 1.76 into 10 to the power 4. 4. Answer will be coming in centimeter. Okay. So 0.2 divided by 1.76. 0.113 micrometer. This is your xt. Okay, you can find out from this formula as well, and this is also you can find out. Okay, here we have reduced the calculation because we were having ES already. All these kind of things we were already having. These electron and hole concentration we can find out, but another thing, let's try out another thing. What is that? Let's take electric field expression. So this is also electric field expression only, Q Na xd epsilon Si, right? So from here as well I could have done the calculation, no? Or again I would have to do the same thing. Q Na epsilon Si, then xd value you put 2 epsilon Si divided by Q Na, then surface potential. So from here as well I would have got the same formula. If you solve it, what you will be getting? 2Q Na epsilon Si phi s divided by, that's it. This is what you will be getting, right? Q Na under root 2 epsilon Si. So this is your electric field, and if you solve it, surface potential is coming out to be epsilon Si is downward actually. Under root epsilon Si. Okay. So from here what you are getting? Epsilon Si Es square divided by 2Q Na. So again, not putting in this box to get the like, you don't need to remember it, but again, whatever the formula that you got here, the same formula you could have got otherwise as well. Like different things are there, all are interrelated only. One is derived from the other, right? But what you need to remember, everything has been kept in the box. Which formula you need to remember? XD formula you need to remember. This phi s you need to remember. Electric field, how to find out this relation you need to remember. These things you need to remember. Es equals to Q Na xd divided by epsilon I you need to remember. If you remember these things, then any way by hook or crook you will be able to solve the question. So this was just a way to tell you that everything is related, everything is interrelated. What they are asking now? Depletion width we have calculated. We need to find out the electron and hole concentration at the surface, and the electron and hole concentration at a surface we need to find out. So hole concentration at the surface. What I am doing? I am applying the positive bias. What we are doing? We are applying the positive bias. Is it mentioned? No. Should have been mentioned. Okay. It should have been mentioned that positive bias has been applied. So we are applying the positive bias. What will happen? Holes will be reflected. Holes will be going down. Holes will be going down. What does that mean? That means, sir, Na e to the power minus Q phi s by Kt. What is the value of Na? Sir, value of Na is 10 to the power 16. E to the power phi s. What is the surface potential, sir? Surface potential is 0.1 volt divided by 0.0259. So that is the answer we will be getting. So let's do the calculation. (0.1) divided by 0.259 plus minus e to the power. So 0.02. That means 2 into 10 to 2.1 into 10 to the power 14. 2.1 into 10 to the power 14 centimeter cube inverse. So this is your hole concentration, which is coming out to be 2.1. Forget about it. This is your hole concentration we are getting. Okay. And what about the electron concentration now? Sir, I know that it would be Ni square by Ps. Okay. What is the value of Ni? Ni is 2.25 into 10 to the power 20. Divided by 2.1 into 10 to the power 14. So 2.1, take the reciprocal, multiply with 2.25. So 1.07 into 10 to the power 6 centimeter cube inverse. Right? This is the answer we are getting. Okay. So this is your electron concentration, and you can see that hole concentration is still above the electron concentration. This is your hole concentration, and this is your electron concentration at the surface. So your hole concentration is still above the electron concentration. What does that mean? This is your depletion mode of operation. Depletion mode of operation. So they can ask you which mode of operation it is. So it is your depletion mode of operation. Okay, depletion mode. What next they are asking? At x equals to wd by 2. That means at half of the depletion width, what is your surface potential? Along with that, what will be your carrier concentration? So I don't think I am having a page. I need to add a page. So after this, we will add a page. So what about the surface potential at xd by 2? Surface potential at x, that is given by this thing, right? The surface potential at xd by 2, that would be the surface by 4. Okay, so what is the surface potential? Surface potential was 0.1. So 0.1 divided by 4 volt. So that would be your surface potential at xd by 2, right? Now what will be your electron and hole concentration? So that you can find out. Just you need the potential, just you need the surface potential and your job is done. So what will be the value? So 10 to the power 16 e to the power, what is the surface potential? 0.1 divided by 4. 0.1 divided by 4 means 0.025 divided by 0.0259, right? 0.1 divided by 0.1 by 4, what that would be? 0.025. Say yes or no, right? This much calculation you can do. So what I will do, I will simply calculate the answer now. .38, that means 3.8 into 10 to the power 15. 3.8 into 10 to the power 15 centimeter cube inverse. So not at the surface, this is not at the surface, this is your whole concentration at xd by 2. Okay, so this is your whole concentration at xd by 2. If you need to find out the electron concentration at xd by 2, what that would be? That would be Ni square divided by whole concentration at xd by 2. That would be 2.25 into 10 to the power 20 divided by 3.8 into 10 to the power 15. 0.59 into 10 to the power 5. That means 5.9 into 10 to the power 4 centimeter cube inverse. So this was your whole concentration at xd by 2 and this was your electron concentration at xd by 2, and the whole question have been solved. Okay, the complete question have been solved. This is like a complete revision of everything that we have studied till now, right? So numerical problem can be framed from here only. Nothing new can be framed numerically. अरे यार क्या अटक रहा है भाई? So numerically only from here questions can be framed, and now I hope you are completely comfortable with it. Okay, so you guys can see it. So this was the numerical. I hope you guys were able to solve this question, although I have taken 21 minutes, but it will not take that much of time, although these are 5 questions. At least these are 5 questions. In the examination, they will ask you gate potential separately, they will ask you surface potential separately, electron hole concentration separately, depletion width separately, and electron hole concentration or surface potential at a particular point separately. So everything that we have studied, all the formulas, everything have been revised here, and we just saw that formulas are interrelated. Okay, this formula we used, right? This formula also we used. Yes or no? Okay, yeah. So let's end this lecture here. This depletion mode of operation we have already studied it. So let me quickly make the concentration plot. So in the bulk nothing was happening. In between I will make a intrinsic carrier concentration plot. You know that whole concentration is going down and electron concentration is increasing, but not in a higher amount. Okay, not in a very high amount. So what does that mean? Like here, if the value was 10 to the power 16, this was 10 to the power 4. So now here it has become, this is your semiconductor. So at the surface it has become 10 to the power 14 and this has become 10 to the power
6, right? But if you furthermore increase it, more holes will go down, electrons will increase, and there would be one point where electron and hole concentration has become equal. After this point, just after this point, what will happen? Inversion will start. What is the meaning of inversion? That now your hole concentration will go more down and electron concentration will go more up. So here what is the scenario? Here both guys are 10 to the power 10. Both guys are 10 to the power 10. Both electron and holes, both are 10 to the power 10. But after that, interesting thing will take place. Electron concentration will increase, hole concentration will decrease. But again, either you take this point or you take this point. The number of charge carriers are very less. If I talk about at the surface, number of charge carriers at the surface, they are already very less only. What is that? Sir, 10 to the power 14 plus 10 to the power 6 nearly equals to 10 to the power 14, which is nothing in compared to 10 to the power 16, right? So charge carriers are very less. Here also the same thing. If I do charge carriers at the surface, what that would be? So that would be 10 to the power 10 plus 10 to the power 10. So that would be 2 into 10 to the power 10, which is again very less than 10 to the power 16. Again they are negligible. So still depletion width is there. The role of depletion width is there, right? Again the number of charge carriers are very less. That means near the surface metallic plate is not there, metallic layer is not there. What we saw in the accumulation mode, do you remember the accumulation mode? In accumulation mode, what was happening? We were getting a metallic plate because charge carriers were a lot. So we got the capacitance of epsilon OX multiplied with the area divided by TOX. But here charge carriers are still very less. That means in all the condition, I am ignoring the inversion charge. So here Q inversion ignored. Here also Q inversion ignored, because charge carriers are near the surface are very less. We will see if we furthermore increase it, what will happen. In the next video, I will draw the diagram. From here only I will pick up the analysis. Just make sure that you already remember all these things. So from here I will pick up the analysis and I will say that more positive charge means more lesser holes. That means electron concentration will increase now, because N into P equals to Ni square will always be valid. Okay, so let's meet in the next lecture. Thank you very much. Yeah, welcome back. So we are picking up our discussion from the last lecture only. So what we have done, we have increased the positive bias in a manner that N equals to P equals to Ni equals to 10 to the power 10 centimeter cube inverse. This condition we have achieved. Now if we furthermore increase the positive bias, what will happen is that more and more electrons will be coming up and holes will be going down. So if I make the intrinsic carrier concentration plot, then this is how the intrinsic carrier concentration plot would look like. This is our Ni equals to 10 to the power 10. Now what has happened is that in the bulk I was having more number of holes, but now those holes have gone down, right? And what about the electrons now? So here I was having less number of electrons. The electrons have gone up now. Right? So here holes were 10 to the power 16. Electrons were 10 to the power 4. Now I can say that, sir, electrons at the surface have become, let's just say it has become 10 to the power 12. And holes have become 10 to the power 8. So it's like I was having MOSCAP, and in between I was having a oxide as well. So this was my p-type substrate, p substrate, right? Now in this p substrate, here I am having more number of electrons than the holes. That means near the surface, what I am getting, surely there will be depletion region, no doubt about it. Depletion region would be there, but near the surface I am having more electrons than the holes. So near the surface I am getting n-type semiconductor. In p-type semiconductor I have created n-type semiconductor. Okay, and what this is known as?
This is known as inversion condition. So this we have written here. So this is known as inversion mode of operation, and last line we will understand that here your surface potential is greater than Fermi potential. We can understand that. How we can understand? This particular line was going down. Now increased more forward, we have increased more gate voltage, then this will come more down. Or how you can think? Sir, more voltage you have done, you have applied more gate voltage here, you have applied more voltage here, that means electric field will be more. If electric field will be more, that means slope will be larger. Along with that, depletion width will also be increasing, because what is the formula of depletion width? Depletion width is under root 2 epsilon by QNA into surface potential, right? So surface potential will also increase. How it will increase? Basically, here near the surface, you let me know what kind of a semiconductor you are having, p type or n type. Sir, n type, because electron concentration is more than the hole concentration. In n type semiconductor, where will be your Fermi level? Fermi level will be above. Fermi level has to be above. So I will not write down EFP, I will write down only EF. So in n type semiconductor, EFI is below EFP. In n type semiconductor, EFI is below EF. I should not say EFP, I should say EF. That means intrinsic Fermi level is below the Fermi level. That means intrinsic Fermi level will become below the Fermi level. This is where it would become. Say yes or no. So this was your phi f, and this is your surface potential. So surface potential has become greater than the Fermi potential. Similar slope we will be having here as well. Similar slope we will be having here as well. So what is this? How much is this slope? This is your phi s, or q phi s I should write down. Q phi s I should write down. This is your q phi s. So this has become more than the Fermi potential. All the formula, all the calculation, everything remains the same. Depletion width, everything would remain the same. Okay, depletion width will keep on increasing. Why it will keep on increasing? Because sir, you are applying more and more positive bias. If you apply more and more positive bias, what will happen? More and more holes will be reflected. That means this negative layer, these negative ions will be created more and more, and depletion width will keep on increasing. So it will keep on increasing. But again, if I ask you number of charge carriers near the surface, how many number of charge carriers you are getting? So 10 to the power 12 plus 10 to the power 8, it will be nearly equals to 10 to the power 12 only. Sir, again very lesser than 10 to the power 16. So again it is like a depletion region only. Why I am focusing too much on the number of charge carriers? Why number of charge carriers are important for me? Because I know that if number of charge carriers have increased, then the surface can act as metal. And if surface start acting as metal, then what will happen? Then it will become metal-oxide-metal semiconductor. That means my capacitance can change. As of now, what is the capacitance you are getting? As of now, if someone asks me what is the capacitance I am getting, sir, again the same capacitance I am getting. This is the capacitance value I am getting. So surely we will discuss the capacitance value. Okay, again all these points we will discuss. Don't worry about it. Here as well, sir, I am getting the same thing. COX into C depletion upon COX plus C depletion. So don't worry about the capacitance value. Capacitance value is still the same. Why I am focusing too much on the charge carriers? Because if I see the number of charge carriers are increased, then the surface can act as a metal. This particular surface, let's just say here charge carriers are a lot, then this particular layer can work as a metal. And if it is working as a metal, what it will say? Don't go to depletion or don't go to semiconductor. I will talk. Then he will start talking. This layer will start talking. And when it will happen, if I furthermore increase the bias, then what will happen? More positive I have applied. More holes will go down. More holes is going down. More electrons is rising up. So there will be one point where this kind of scenario would take place. This was your bulk. This was your bulk. So there will be one point where what kind of scenario would take place? In between there was Ni. So what will happen is that hole concentration will decrease down to electron concentration, and electron concentration will increase to hole concentration. Do you understand what really happened? Here what was your number of holes? So 10 to the power 16. What was your number of electrons? 10 to the power 4. At the surface, the electrons have become 10 to the power 16 and holes have become 10 to the power 4 at the surface. And now what is happening in your metal oxide semiconductor? You can think a lot of electrons have been piled up here. 10 to the power 16 electrons have been piled up here. That means whatever the number of holes you are having in the bulk, whatever the number of holes I was having, that was 10 to the power 16. The same number of electrons I have generated here. That means now you are having good number of electrons. If I ask you what is the number of charge carriers now, you will say, sir, number of charge carriers are 10 to the power 16, which is comparable to 10 to the power 16. So now the number of charge carriers are good enough. That means this particular layer near the surface, you can see that, sir, near the surface I am having good enough electrons. Now if you apply positive bias, what this surface will say? That I will provide you negative charge. After this particular point, the surface will say that now I am having more than enough electrons. If you apply more further positive bias, I will provide you the negative charge. Don't go to depletion region. Don't go to P substrate. Don't go downward. Talk to me. That means electric field lines will not go downward. They will start from here and will end here. So effect of electric field will not go inside the depletion region, and the depletion width will stop. The depletion width will stop extending. Are you able to understand this point? Surely we will discuss all these points again, but in summary you are able to understand that, sir, furthermore we increased. One point we reached that at the surface electron concentration has become equal to the hole concentration in the bulk, and now this layer has become very much metallic. So electric field lines will start and will end at the metal only. They will not go inside. So just before this point, whatever the depletion width I was having, before this point what was happening? That, sir, positive charge was applied, depletion width was increasing. Why depletion width was increasing? Because charge carriers are less. That's why depletion width was increasing. But now, sir, if charge carriers have become good enough, now the depletion width will not increase. So depletion width will attain a certain value. And if depletion width is attaining a certain value, then this was constant to epsilon I is constant, Q and A is constant, Na is constant. This also has attained a certain value. That means the surface potential will also be a constant value. What that value will be? Let's check that out. So this is your phi f. Now you know that, sir, this will go down. Sir, this will go down. But just let me know one thing. How much it will go down? This is your phi f. No doubt about it. I know that, sir, this will go down. But how much it will go down? Can anyone tell? I am saying that this much it is going down. Better I should make with pen only. Can anyone tell how much will be this much? Or think about this particular width. How much will be this width? This is Q phi f. How much will be this width? This width will also be Q phi f, no? If I am saying that I am having a semiconductor which is having a donor atom of 10 to the power 16. So what kind of Venn diagram you will get? This kind of Venn diagram you will get. Now if I am having a semiconductor which is having an acceptor atom of 10 to the power 16. So what kind of Venn diagram I will get? This kind of Venn diagram I will get. So this gap and this gap will be same, right? KT-ln Na by Ni, KT-ln Nd by Ni. Doping is same, gap is same. So this was above, this will be below. Why it is below? Because this has become N type. Whatever the hole concentration you are having here, 10 to the power 16, the same number of electron concentration you are having now, 10 to the power 16. That means whatever the height you have achieved here, the same height I have achieved here. Say yes or no. That means what will be my surface potential now? So surface potential has become 2q phi f. Q phi f plus q phi f 2q phi f. Is that understandable to you? So let's remove all this part. Okay, so same slope we are getting. I want to make it look good, but how do I make it? I know it is not looking good, but bear with it. Okay, this is your 2q phi f. So here the same thing I have written. This is known as strong inversion mode of operation. Until just as you get this condition that your phi s is equals to 2 phi f. At this particular point, you will call that strong inversion have achieved. The inversion started here. The inversion started here, but we call it weak inversion. What we call it? We call it weak inversion. Why it is weak inversion? Sir, although number of electrons are more than the number of holes, that means, sir, the surface has become n-type. No doubt about it. But again, the concentration is very low. But now the concentration has become equals to the bulk hole concentration. That means a strong inversion have achieved. So what is the condition of strong inversion? That your surface potential has become equals to 2 times of Fermi potential. So two scenarios we have seen. Two scenarios we have seen: weak inversion and strong inversion. We will discuss that in detail again. But my target was just to tell you that if you keep on increasing the voltage, then what will happen? This is something that will happen. Okay, so again we will discuss it, no doubt about it. But all the formulas, everything would remain same. Try solving this question. Everything would remain same. Try solving this question. The ditto same kind of question I am asking. Emax is given. Just one point you can notice here. This time, this Emax has changed from the previous part. Here we solved this question, no? Here Emax was 1.76. Now that has changed. Rest all the things are same. Ditto same as it is. That means electric field at the surface has changed. Electric field at the surface has increased. That means surface potential would have increased. Surface potential is increased. If this electric field is increased, that means oxide electric field is also increased. That means VOX is also increased. VOX has increased. Surface potential has increased. That means gate bias would also have been increased. Let's try solving it. What we need to find out? We need to find out the surface potential and everything. First, we need to find out applied gate bias. That would be this particular thing. What is the surface potential? We need to find out. What is the oxide voltage? That also we need to find out. So first, let's try finding out oxide voltage. That I know that it would be equals to oxide electric field multiply with the oxide thickness. What will be my oxide electric field? So that would be epsilon OX, EOX, epsilon SI, ESI. Okay. So electric field inside the oxide would be 3 times of 3.51 into 10 to the power 4 volt per centimeter. 3.51 into 3. 10.53 10 to the power 4 volt per centimeter. So oxide potential will be 10.53 into 10 to the power 4. Oxide thickness is 10 nanometer. That would be 10 to the power minus 6 centimeter. So answer would be 10 to the power minus 2, you can say, or 0.1053 volt. So this is your oxide thickness. Next, what I need to find out? I need to find out the surface potential. What I need to find out? Surface potential I need to find out. So what will be the first thing that would click to me? Sir, half into this thing would click to me, right? So Emax is nothing but ES only, right? This we already know. and here ES I should write down. This I will write down as ES only. ES. ES. Okay, and then we do something with this formula, and eventually we get a formula as epsilon Si ES square upon 2QNA. Say yes or no? Say yes or no? This was the formula only, no? Like, I don't remember it, but calculation we have done, no? So why should we do it again? Epsilon Si ES square 2QNA. Can I do something? What answer I got? 0.1 here I got, no? So 1.76, 1.76 if I divide, and I will do the calculation, put down all the values, I will do the calculation, you can also do it. So previously I have already got 0.1 answer. Then if I divide it by 1.76, then again I divide it by 1.76, and then I multiply with 3.51, again I multiply with 3.51. So 0.397, that means 0. Here you will put the values and you will get the answer as 0.4 volt. Okay, 0.4 volt you will get. That is your surface potential. Arey wow. Okay, that's your surface potential. What we need to find out? We need to find out the applied gate voltage. Oxide plus surface potential. Oxide voltage came out to be 0. So everything has increased, no? This also has increased. Plus 0.4. 0.5 volt. This is the applied gate voltage you need to apply. So previously what was the applied voltage we could see in the last question? Same kind of question it is. Applied voltage was 0.513. But furthermore, if we increase the positive bias, then what has happened? Let's see what has happened. What we have got here, surface potential is 0.4 volt. Let's find out the Fermi potential as well. Why I am finding out Fermi potential? You will see. You will understand why I am finding out Fermi potential. Or let's not talk about Fermi potential first. Let's first find out the electron and hole concentration at the surface. So what I need to find out? Hole concentration at the surface. What that would be? Sir, hole concentration is going down. So e to the power minus. So Na value I already know. I will directly put the value. Na value I already know. Sir, hole concentration is actually going down. So e to the power minus psi s divided by 0.0259. Say yes or no, right? Zero 0.4 upon 0.0259 plus minus e to the power. So you can see that, sir, it is coming out to be 1.96 into 10 to the power 9 centimeter cube inverse. This is the concentration of holes you are getting. So what will be the concentration of electrons? Ni square by Ps. What will be your Ni square? 2.25 into 10 to the power 20. What is the value of Ni? Ni is this much, 2.25 into 10 to the power 20 divided by 1.96 into 10 to the power 9. So 2.25 divided by 1.96. So you are getting 1.147 into 10 to the power 11 centimeter cube inverse. So we can see that hole concentration is 1.96 into 10 power 9 and electron concentration is 1.147 into 10 to the power 11 centimeter cube inverse. This is the scenario we are getting. So is it strong inversion? It is inversion or depletion or accumulation? What do you think? What it is? It is your, what it is? Weak inversion, right? Why it is weak inversion? Because you can see that, sir, number of electrons are more than the number of holes. But it's not that number of electrons has become equals to 10 to the power 16. No. So your Ns is still less than Na. But it is surely greater than Ps.
Is that understandable to you? Electron concentration at the surface is more than the hole concentration at the surface, but it is lesser than the hole concentration in the bulk. Lesser than the hole concentration in the bulk. So this condition is not achieved, that sir NS has become equals to Na. This condition is not achieved. NS equals to Na, this condition is not achieved. Okay, well and good, all fine. Yeah. So along with that, you could have verified with the phi f as well. Like if I try to find out Fermi potential, or I can do it on the next page if I have some space. Yeah, here I can find out Fermi potential. So you would see that your surface potential is more than the Fermi potential. In the weak inversion, this was your weak inversion, right? So in weak inversion, this surface potential would become more than the Fermi potential. So let's try finding out the Fermi potential. What that would be? 0.0259 kT ln Na by Ni. So Na is 10 to the power 16 divided by Ni, 1.5 into 10 power 10. So that would become 0.0259, 0.347, 0.347 volt, right? So what you can see, that your surface potential is more than the Fermi potential, and surely it is lesser than, and surely your surface potential is less than twice of Fermi potential, because what is twice of Fermi potential? You can do the double, it will surely be lesser than that. That means this is the condition of weak inversion. So from here you can verify weak inversion, from here also you can verify weak inversion. Say yes or no. Okay. Well and good. Yeah, so this question have been solved. Now again we can discuss weak inversion and strong inversion in more detail. So weak inversion and strong inversion in more detail we are discussing. Same points, what we are doing, positive bias we are applying, but this time your surface potential would be more than the Fermi potential but lesser than twice of Fermi potential, right? So this is the condition of weak inversion. What will happen? Holes go away, depletion width has extended. So I will make the depletion width more this time. So this much of depletion width I will make. Let's take one more. So this much of depletion width I will make. So this depletion width we have got. Okay. So this is the depletion width we have got. Along with that, surely there are some electrons as well, but those electrons are not that high. These are 10 to the power 12, 10 to the power 13, 10 to the power 14, but again not 10 to the power 16. So not that high. Again it is very much less compared to this guy. Again he is winning. He is saying that I am 10 to the power 16, I am winning. Whatever you are, I don't care. You might be, or better I should write down at the surface only. At the surface you might be having, let's just say 10 to the power 14, but still you are very much lesser than me. I am still winning. So if I apply a bit more voltage here, then what will happen? The positive charge will say I need negative charge. If I need negative charge, then depletion width will be extended. So whole electric field will go like this. This will be our electric field. This will be our electric field. Okay. So there will be a drop across oxide as well, and there will be this surface potential as well. All the formula, everything would remain same, ditto same. No need to worry about anything. Everything would remain same. All the formulas, everything. Okay. If you are moving from depletion to inversion, nothing is changing. If I ask you capacitance, same. Depletion width, same. Surface potential, same. Surface electric field, same. Everything is same. All the formulas are same. Right. So what will be your capacitance? Capacitance, for capacitance we have made different slide. Yeah. So what else we can see here? Yeah, that's it. Formula I don't need to write down again and again because you already know about it, or it would be kind of summary if we write down, right? If we write down, it would be kind of summary. So shall we write down? Vg equals to Vox plus psi s, right? Electric field, yeah, electric field also I can write down. So that would be q na xd divided by epsilon si. Psi s is half xd es. Xd is under root 2 epsilon si qna psi si, right? All good? Anything else we have left? Es phi s, this formula we have written. Phi s formula we have written. Vox would eventually come. Like if someone want to write down the formula for Vox as well, then it would be Eox into Tox. Along with that, Q depletion divided by Cox. Q inversion still ignored. Okay, Q inversion still ignored. Still it is nearly 0 only. Why it is 0? This point is remaining. We will solve a numerical. Q inversion is still ignored. Okay. Even at the strong inversion as well, when phi s is just equals to 2 phi f, at that time as well we will ignore it, but after that we will not ignore it. That's the point. After that we will not ignore it. But even at the strong inversion as well we will ignore it. We will solve the numerical, have some patience. Okay. How will I measure the capacitance? I know that. Sir, positive, positive, positive. Depletion layer, depletion layer, depletion layer. As you increase the voltage, sir, depletion layer will increase. Why so? Because, sir, we are not having more than enough electrons here, right? So what will be your capacitance? Capacitance will be same, Cox C depletion divided by Cox plus C depletion. This will be your capacitance. Okay, then if I draw the plot, the same plot we will be getting. Same things are continuing. Capacitance versus Vg plot if I draw. So till this point we have already drawn that at the negative we were getting the same, and then it started decreasing and it will keep on decreasing in this manner. So same plot, like when you move from depletion to weak inversion, nothing interesting is happening. Same thing is there. It's just that inversion we have achieved. That means in P type we have got N type. So that is the interesting part. Rest nothing is changing. Okay, so this kind of a curve we will get. Here this was our Cox, right? And this is our Cox C depletion upon Cox plus C depletion. Okay. Now strong inversion. This is an interesting point. So here plus 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 plus. Depletion width has also been framed, no doubt about it. So depletion width is also there. But along with the depletion width, electron layer has also been made up. Depletion width is there. Along with that, there is a layer of electrons as well. There is a layer of electrons as well. Let's use a different color of pen. Right. So if I am saying that, sir, here number of holes were 10 to the power 16. So here number of electrons has become 10 to the power 16 centimeter cube inverse. Now let's just say from Vg I increase it a bit. Let's just say this Vg was 3 volt. At 3 volt this condition we have achieved. Now from 3 to if I go to 3.1 volt, what this guy will say? Initially I am having plus Q charge. With respect to 3 volt I am having plus Q charge. But with respect to 3.1 volt I need plus Q1 charge. So previously what was happening? When he needed plus Q1 charge, what he did? He went to the depletion layer. That depletion width should increase. That means these negative ions was providing negative charge. But now what this layer will say? This layer will say that I am highly metallic. If you increase it, if you increase positive voltage, you require plus q1, you require minus q1 charge, I will give you. I have the ability of generating the electrons because I am n type. N type will say that I am having more than enough electrons. I have the ability of generating the electrons. So whatever the electrons you require, let me know. I will give you those electrons. So he will give you those electrons. He will say, don't go into depletion. Don't go into depletion. The electric field will just be at this point only. Surface electric field will be there. Surely it will be there. Surface potential will be there. It will be there. But it will, like, what will be the surface potential? Sir, this will be the surface potential. Oxide potential, sir, this will be the oxide potential. Oxide potential. But now your surface potential will be fixed at 2 phi f. It will not increase further. Why it is not increasing further? Because electric field is becoming 0. If electric field is 0, what is the potential? Potential is electric field dot dx. If electric field is 0, then that means 0 dot dx. It has become constant. That means at the surface, whatever the potential you are having, that becomes constant only. Basically, there is no increase in this depletion width. No increase in the depletion width. Because electric field is now positive charge is being supplied by these electrons only. By these electrons only. Positive charge, whatever the positive charge is there, it would require some negative charge, and this negative charge condition is being fulfilled by these layers of electrons. So electric field is not proceeding inside. Previously electric field was going inside. Because of that, depletion width was increasing. Why depletion width was increasing? Because if he said that I need more negative charge, because with respect to more positive charge I would require more negative charge, then your semiconductor will say that take from the depletion width. Depletion width will extend and electric field will go inside the depletion width. But here electric field will not go inside. Is that clear to you? Again, here formula and everything remains same, but surface potential will be fixed to 2 phi f. Surface potential here will be fixed to 2 phi f. So this is the maximum surface potential you can have. This is the maximum depletion width you can have. People will get confused, sir. Here you have made 4. Here also you have made 4. So what we can do? Can we reduce it? Like basically, can we reduce till this point? Don't get confused. Basically, this XD I have made. This XD max is more than XD. In the weak inversion, whatever the depletion width you are having, here you will be having more depletion width. Because till you reach 2 phi f, till that point depletion width will increase. But after that it will stop. So if someone asks you what is the formula of XD max, what will be the maximum depletion width you can have? So sir, maximum depletion width that I can have, that would be under root 2 epsilon Si divided by Qna. Sir, here I used to write down surface potential, right? So that surface potential will be fixed to 2 phi f. Now the surface potential will not increase. So the potential across the depletion width will not increase. Now can I ask you a very interesting doubt? Like this particular doubt is written in the, it is written wrong in the books as well. So what doubt I will ask you? Sir, with respect to 3 volt, this is the condition I am having, right? That electron concentration is 10 to the power 16. Now sir, from 3 volt to if I go to 4 volt, so here the charge will increase. That means it will require more negative charge. That means this guy will also increase. So this will become 10 to the power, from 10 to the power 16 to 10 to the power 18. Have you seen the formula of electron and hole concentration at the surface? This was your hole concentration at the surface, e to the power minus q phi s by kt. Now you are saying that sir, this guy is fixed. That means this should not change. If this is not changing, that means this should also not change, because you know that sir, ns into ps equals to ni square. Sir, you are saying that phi s is fixed to 2 phi f. It will not increase further. This is what you are saying, right? If phi s is fixed, Na is already fixed, Kt is already fixed. That means the whole concentration at the surface should not be changing. If it is not changing, that means electron should not be changing. So if you are saying that
from 3 volt to I am going 4 volt. At 3 volt, I am getting my hole concentration of 10 to the power 16. Now from 3 volt, if I am going to 4 volt, what this 4 volt will say? That I am having plus Q2 charge. With respect to plus Q2 charge, I require minus Q2 charge. So here electron concentration has to increase because electron will provide the negative charge. So electron concentration is actually increasing. That means hole concentration is actually decreasing. That means this guy has to change. So the point is the potential here it is changing. Like across the layer, whatever the potential is there, no, that potential is changing. But the potential across the depletion region is not changing. I don't know why in the books it is written that surface potential is not changing. But actually, the potential across the depletion region is not changing. The surface potential is changing. Are you able to understand this point? Because surface potential has to change, no? If surface potential is not changing, then how the electron hole concentration will change? If they are not changing, then how will you provide minus Q2 charge, minus Q3 charge, minus Q4 charge? That means they are surely changing. So this surface potential, the potential that you are having across this very thin layer, this layer will be very thin, 1 nanometer or 2 nanometer. So there the potential is changing. But the potential across the oxide remains same because electric field is not coming inside. Here no electric field is coming. So whatever that was made, that is made already. That's it. No electric field is coming. This is at the equilibrium now. He will say I will not change. So this phi s will remain equal to 2 phi f. But here the potential will change. But I don't know why in every textbook it is written that surface potential does not change. But actually surface potential changes. The potential across the depletion width does not change. We will not write down in the statement. Why is that so? Because even the NPTEL professor also teach in this manner only that surface potential does not change. They ignore this much of width. But practically if you see that this potential has to change here. This potential has to change. Are you able to understand this point? But very thin width is there, no? So that would be ignored. Okay? Is that clear? So even in the textbook, if you find out that after strong inversion, once you achieve this condition that phi s equals to 2 phi f, after that your surface potential will not change. So you should not be questioning that, because as a student this doubt should come that sir, if I am increasing more potential, here, that means this will require more charge. If this is requiring more charge, that means here more charge should be there. That means more electrons should be there. If more electrons are there, so this was the formula. Then this surface potential has to change, So the potential across that thin layer it is changing, not across the depletion region. So this XD max formula that will be applicable, because XD max is the width of a depletion region, and across the depletion region this guy remains constant. Phi s equals to 2 phi f. Is that clear? Okay. So all these points we will not write down in theory, but still let me ask you one more interesting doubt. Okay, like all these doubts will come if you think deeply. So we have drawn these kind of plots. Here we have drawn this kind of plot. Here also we draw the plot. Here also we have drawn the plot. In the depletion region also we have drawn the plot. In the accumulation region we draw this kind of plot. Right? What does this show? That sir, here hole concentration has gone down. Let us say here there are 2 holes. So sir, here there will be 4 holes. Or let's not show the holes here. Let's show the holes here. Or let's show the holes here. Sir, here there will be 2 holes and here there will be 4 holes. Right? Do you agree to this point? Sir, here my hole concentration was 10 to the power 16. And sir, now the concentration has become dropped down to 10 to the power 14. Concentration gradient is there. More holes, less holes. And because of the concentration gradient, these guys should diffuse. There you go. And if they are diffusing, there should be a diffusion current. That means in MOSCAP, current is flowing. Does that happen? If current is flowing, that means there should be a slope here. Where that current is going? Answer is not t equals to 0. Okay, answer is not t equals to 0. This is not coming because of the t equals to 0. T equals to 0 was associated with the battery. The battery we applied, current was flowing. It's not that sir, at t equals to 0 this current is there. No.
What is my doubt? Did you understand? What is my question? More holes here, less holes here. Diffusion would be there, no? Diffusion current should come into action. So where that diffusion current is going? Sir, you missed one point. What point you missed? There is an electric field as well, no? Electric field in this direction. So what this electric field will say? What this electric field will say? Whatever the holes that are diffusing here, electric field will say, go back, drift. So holes, because of this electric field, will feel the drift. And drift and diffusion will cancel out each other. So these kind of things can be asked in interviews. I don't know how MCQ can be framed from here. I don't think MCQ can be framed here. But here also drift, diffusion, current components are there. Is that clear to you? So this is the beauty of EDC. The more you study, the more you think, the more you will feel enjoyment. Okay. So I don't know how they will frame the question in the theory part, right? But surely in the in the interviews, if someone is taking good interview, what he will say that explain this mode of operation, and then he will say more concentration, less concentration, diffusion current. In the MOSCAP, you say zero current is there, you have made it flat, it should not be flat, current is there, that means it should have a slope. Explain it, why it is not having any slope. You will say, sir, you missed the electric field, because of that drift would also be there, both will be cancelling out each other. So just a small point, just keep it as it is. Okay. Yeah, so where we were, yeah, so this is where we were considering. Okay, so in this condition, what do you think, what will be the capacitance? Sir, here your capacitance is looking like COX only. Why it is looking like COX only? Because, sir, this guy is blocking, right? It is working as a metal oxide metal semiconductor, which is metal oxide metal, which is equals to COX. Because this has become a conductive layer, he is saying that whatever the change in charge you are applying, the same amount of change in charge I can give you. Don't go inside. Depletion width fixed, right? Surface potential fixed at 2 phi f only. No matter how much you increase it, no matter how much you increase it, phi s would be equals to 2 phi f. Depletion width fixed. Okay, well and good. Yeah, so let's remove this part, rest all are fine. Okay then. So all this formula we will again write down, don't worry about it. But yeah, this point that inversion charge, यहाँ क्या लिखा है भाई? The point is inversion charge is always neglected compared to their compared word is written. Okay, so inversion charge is always neglected, or it is considered very less compared to depletion charge, but until the strong inversion condition. So even at the strong inversion, this charge is very less. Sir, you are saying higher number of electrons are there, no? Yes, number of electrons are more. It doesn't mean charge will be more. These are the number of electrons. What I am talking about? I am talking about the charge. Q is the charge, right? So I need to talk about the number of charge, right? So number of charge here and number of charge in the depletion region. So what we need to do, number of charge, not number of charge, total charge in the depletion region versus total inversion charge. This is something we are doing. Is that clear? So here I know the number of electrons. If I multiply with the volume, what I will get? Total number of electrons. This is your number of electrons per unit volume. If I multiply with the volume, what I will get? Total number of electrons. And if I multiply with the Q, what I will get? Total charge in the inversion layer, right? Total charge in the inversion layer that I will get. So Q inversion I need to calculate. Q depletion I already know. What is Q depletion? Q depletion is nothing but Q Na XD, right? Which condition they have given? Strong inversion. That means XD max I can write down. So this is your charge per unit area. If I multiply with the area, what I will get? Coulomb.
So Q Na XD max into area. XD max I will calculate. Okay. Inversion layer thickness is given as 3 nanometer. So this thickness is given as 3 nanometer. This thickness is given as 3 nanometer. So what will be your Q inversion? What do you think? The Q inversion will be number of electrons at the surface, right? Thickness is given. Thickness is given. Multiply with the area. So what you will get? Total number of electrons. Then multiply with the charge. What you will get? Total charge. Ns per centimeter cube. Thickness into area. Total number of electrons you are getting. Multiply with the charge. Total charge you are getting. This is total charge. This is total charge. Find out Q depletion. Find out Q inversion and compare both of them. Do the calculation on your own. I will take a break and then come back. Very simple calculation. You can do it. Surely you can do it on your own. So do it and then we will talk about the capacitance as well. Along with that, we will discuss this point which we have already discussed actually. Why depletion width stop extending after achieving strong inversion. So this we can already discuss. This we have already discussed. So this theory has been written which you can read on your own. That why depletion width will stop extending after achieving strong inversion. Theory has been written. So I can read it out for you. Before strong inversion, if we increase the voltage, if we increase the gate voltage, then the semiconductor supplying the required negative charge by removing the holes from the surface and thereby the depletion width will get widened up, thereby widening the depletion width. In this region of operation, depletion is the only available mechanism to generate negative charge because surface electron concentration is very small. So depletion widths are saying that I will take everything on me, that I will provide you negative charge. But after achieving the strong inversion, what has happened? The surface electron concentration has become equal to the bulk hole concentration. This means that effective N layer has been framed in the semiconductor surface, and now once the inversion layer has been framed, and if you increase the further voltage at the gate, then what will happen? The required additional negative charge will be given by the electrons. So this has been written. Any further increase in gate voltage is balanced by generating additional electrons in thin N-type region. As a result, the electric field will no longer penetrate deeper into the deeper into the semiconductor. The electric field will be there, metal, oxide and that very thin layer, right? So the electric field no longer penetrates deeper into the semiconductor. The potential remain essentially uniform across the depletion region and the depletion width stop increasing after strong inversion is achieved. That's it. This is every single line you are able to understand. Every single line. Say yes or no. So theory has been written. We will solve this question. From this question as well, we will make a very good conclusion. And I can frame one numerical as well. From this conclusion, whatever the conclusion we get, we will get the conclusion that Q inversion is less than Q depletion. Okay, very less than Q depletion. But after that, after achieving strong inversion, then this Q inversion will come into action. So this, I guess we can frame a numerical here. Okay, so I will take a break. You try doing this value and then I will come back. Okay, you try solving this numerical and I will come back. Okay, yeah, welcome back. So did you try this question? So we need to find out depletion charge and inversion charge. Look, inversion charge looks simple. We have the value of Q, we have the value of inversion thickness as well, and we have the value of area as well. What will be the value of electron concentration at the surface? Can anyone tell what is the value of Ns? Do you need to calculate it? Do you need to apply any formula? No, sir. This is the case of strong inversion. Like you are at the edge of strong inversion. That means phi s equals to 2 phi f. What does that mean? That means your Ns would be the electron concentration at the surface would be equal to the hole concentration in the bulk. Hole concentration in the bulk is given. That is this much. So what will be the answer? 10 to the power 16. Right? So Q value I know, Ns value I know, inversion thickness I know, and area I know. So I will simply put the value and I will get the inversion charge equals to 4.8 into 10 power minus 14 coulomb. So this much inversion charge we are having. Now we need to calculate a depletion width charge. Depletion charge we need to calculate. So we are having the value of Q, we are having the value of Na, we are having the value of area, but we don't have the value of depletion width. So how much depletion width is there? Let's calculate that. Why I am putting XD max? Because I know that at the edge of strong inversion, the depletion width would be maximum. So what we need to do? We will simply apply the formula
in this formula what I would require, sir, I would require the value of 2 phi f. Why 2 phi f? Because the formula says 2 epsilon Si upon Qna multiply with surface potential, but here surface potential is equals to 2 phi f. That means I would require the value of phi f. What I need to find out? I need to find out the Fermi potential. So that would be 0.0259 ln Na by Ni 10 to the power 16 divided by 1.5 into 10 to the power 10. So from here I will get the value, although I have calculated this value a lot of time, but still I don't remember it. .347. So if you talk about your surface potential, that would be twice of that, 0.694. .7 into 8.85 into 10 power minus 14 divided by Qna. What is the value of Na? 10 to the power 16 into 2 phi f, that is, this is the scenario. So what we will be getting, 10 to the power minus 10 to the power minus 11, so 10 to the power minus 5 can come outside, and then 0.2 into 11.7 into 8.85 into 0.694 divided by 1.6. Take the under root, 10 to the power minus 5 is outside, 2.99 into 10 to the power minus 5 centimeter. This is the value of XD max we are getting. Okay, so what we need to calculate? Q depletion we need to calculate. So what will be your Q depletion? Q depletion will be Qna XD max, Q 1.6 into 10 power minus 90, Na XD max. XD max is 2.99 into 10 to the power minus 5 into area. So you would see that, sir, this term and this term, this term and this term all are same. The problem is with this thickness. So this particular thickness is very lesser, 3 nanometer, but our depletion width thickness is large. So from here only you can compare that, sir, this is 3 into 10 power minus 7, and let's just put it 3 into, let's put it 3 only, because 2.99 is nearly equal to 3 only, so let's put it 3 only. So this is coming out to be 3 into 10 power minus 7, this is coming out to be 3 into 10 power minus 5. That means here the answer would come out to be 4.8 into 10 power minus 12 coulomb. Say yes or no? Which is 100 times of Q inversion. So you can see that Q depletion is 100 times of Q inversion. That means Q inversion is nearly 0. Or if I say Q total, if I talk about total charge in the semiconductor, total charge in the semiconductor, which semiconductor? The semiconductor that we are using in this semiconductor here, total charge will be depletion charge plus this particular charge, which we are calling as inversion charge. So total charge is Q inversion plus Q depletion. So this is nearly equals to 0. So total charge in the semiconductor is equals to Q depletion only. So even at the strong inversion condition, look, number of electrons have increased. Number of electrons have increased for sure. Near the surface, number of electrons have increased, but electron density has increased. It doesn't mean charge is also very large. No, number of electrons are very much more. Electric field lines are not going inside the depletion region. Everything is understandable, but it does not mean that, sir, the charge is too much. No, inversion charge is still very less. So until the condition of strong inversion, that means until you get phi s equals to 2 phi f, until that condition you will always ignore the inversion charges. Inversion charges would be equals to 0. So charge in the semiconductor would be equals to the depletion charge only. Is that understandable? Because the problem is the thickness would be very less, and in that thickness how much charge can be contained? Very less charge can be contained. Okay. Even though this charge is very less, but after that if you increase charge here, if you increase the voltage, that means if you increase the charge on the semiconductor plate, this layer will say that I am conductive, I can give you increased charges. He will say I can give you increased charges. That means he has the capability of giving the increased charges, but as of now the charge is actually very less. But he has built up the category, he has built up the strength to give the increased charges. Is that understandable to you? Surely it is understandable. Okay. Now let's just write down the formulas. Metal oxide semiconductor. I have applied good enough Vg value such that here you are having inversion charges or your inversion layer, we call it inversion layer. Along with that we are having depletion width as well. We are just writing down those formula which we already know. So depletion width also we are having. You know that after a certain voltage, depletion width will stop extending. Now let's just say this is the maximum depletion width that we have got. So this would be our HD max. This layer is actually very thin. This is known as inversion charge. This is known as depletion charge. Okay. So what they are saying, maximum potential across the depletion region. What that is known as? Maximum potential across the depletion region, that is known as surface potential, which is equals to 2 phi f. So that would be equals to surface potential max, that would be equals to 2 phi f. Maximum depletion width, that is known as HD max. So formula of HD max would be, sir, formula I already remember, it would be there in my heart always, because again and again I apply this formula. 2 epsilon y QNA. Here I should have written phi s, but it would be 2 phi f. Why so? Because phi s will not increase after 2 phi f. This is the maximum depletion width I will get. Maximum depletion charge. Now if depletion width is not changing, what is your depletion charge? What is your depletion charge? What was the formula of depletion charge? Sir, this was the formula of depletion charge, QNA XD. Right? So Q is constant, NA is constant. If depletion width is also not extending, then depletion charge will also not extend. Right? Depletion charge will also be fixed. If depletion width is not changing, that means depletion charge is also fixed. So if I talk about maximum depletion charge. So what will be your maximum depletion charge? That would be, sir, QNA XD max. You know the formula of XD max, you know the formula of QNA. So surely you can write down here QNA XD max. If you write down this formula here, what you will get? Under root QNA, and this will be cancelled out, and here you will be getting under root 2 epsilon SI QNA 2 phi f. This will be the maximum depletion charge that you get. And all this is occurring at the edge of strong inversion. Edge of strong inversion means that just the strong inversion has started. That means your NS has become equals to NA. What is your NA? Here, whatever the NA we are having, that is my NA. Okay, and here we are having NS. So NS has just become equals to NA. At that time, these are the conditions that we are having. Okay, so we have written down the formula. Now there is another formula which is known as threshold voltage. Threshold voltage of MOSCAP. What is the meaning of threshold voltage? So it is the gate voltage at which this condition has started. This condition. What is this condition? At which strong inversion has started. That means this condition has taken place. What does that mean? That means your surface potential has become equals to 2 phi f. Or better, I should have said the potential across the depletion region has become 2 phi f, and it is fixed now. The surface potential will not increase. Although surface potential will increase, the potential across this very thin layer will increase, but the potential across depletion width will remain same. So at what gate voltage this will happen? We know that Vg is equals to oxide plus some potential will be dropped in the oxide. You know that, right? Some potential will be dropped in the oxide and some will be dropped across the surface, right? So phi s equals to 2 phi f, I already know, right? Now when your gate voltage, when Vg equals to Vt, at that time what will happen? What is the value of Vux? Do you remember? Yes sir. When we used to write down Vux, Vux means, sir, this charge divided by the capacitance. Charge divided by the capacitance. But sir, which charge? This particular charge, sir, I cannot comment. This particular charge I cannot comment. But here negative charge I know. What is the negative charge I am having? Sir, you are having inversion charge as well. Plus, you are having inversion charge as well. Along with that, you are having depletion charges as well. But you know that at the strong inversion condition, this will be ignored. Q inversion will be ignored. So Vux would be Q depletion, and you are at Vt. You are at the threshold. Threshold voltage is given by Vt. You are at the threshold. At threshold, depletion charge would be maximum divided by Cox plus phi s, and phi s equals to 2 phi f. Also, Q depletion is maximum, right? And let's put it aside. Let's put it here. So here I can put Q depletion maximum plus 2 phi f. So this is the formula of threshold voltage we get. Threshold voltage formula. Which formula we get? Sir, under root 2 epsilon Si. Look, this Q depletion max we have put here, no? This 2 can be multiplied here. This will become 4. So 4 epsilon Si Q Na phi f. 4 epsilon Si Q Na phi f. Divided by Cox plus 2 phi f. So this is the formula of threshold voltage we get, which people remember, but I don't think as a student for me it will be easy for me to remember. No, it will not be easy. It would be tough, right? So better what I would remember this thing only, Vux plus phi s. That's it. Then I know what is my Vux, Q depletion divided by Cox. Q depletion can I write down? Yes sir, Q Na XD. I won't even remember this formula. I will only remember this formula, Q Na XD. That's it. This is something that I would remember. Q depletion is Q Na XD. Sir, inversion charge I will ignore. Q Na XD I will write down. XD formula I remember, 2 epsilon Q Na, and I know that surface potential will be equal to 2 phi f. Within 10 seconds I will be able to derive this formula. Although I am keeping it in the box, still I would say do not remember it. Okay, not very tough to remember. Sorry, very tough to remember, but not very tough to derive. If you have confidence on yourself, you will be able to derive in the examination without a single doubt. Okay, so this is the formula of threshold voltage. Now after threshold, what will happen? After threshold, this depletion charge will not change. Then who will change? Look, if you increase your voltage above Vt, what I mean to say is that if Vg is greater than Vt, then he will say I need more positive, here more positive charge will be put, and he will say I need more negative charge. Depletion width will say I will not extend. That means depletion charge will say I am not able to provide more charge. Then who will provide more charge? This will provide more charge. Again, let me repeat. If you increase the voltage, now he will say I need more negative charge. This positive charge will say I need more negative charge. Depletion width will say I will not provide the charge. Then who will provide the charge? Inversion layer will provide the charge, right? So for Vg greater than Vt, can I write down my Vg as again the same thing, Vux plus Is? No one can change it, right? But what I will write down my Vux now? Now I will not ignore this Q inversion, because now whatever the change in charge I require, Q inversion is providing me. So I will put Q inversion plus Q depletion divided by Cox plus psi s. That is equals to Vg. All this we are doing for Vg greater than Vt. So at Vg greater than Vt, our Q inversion will start coming into action. This guy will have some importance now. So if this guy is having some importance, I am giving him importance here. So can I put this formula in this manner? Q inversion Cox plus Q depletion by Cox, and here I should put a Q depletion max. Why max? Because maximum condition has achieved. Q depletion will not increase further than that. Cux plus phi s, right? Can anyone tell what this is? Q depletion max divided by Cux plus phi s, which phi s is also equals to 2 phi f. So here also you can put 2 phi f already, or let's put phi s here only. Let's put phi s. Let's put this as 2 phi f. Can anyone tell what it is? This is your threshold voltage, right? This is nothing but threshold voltage. So Vg is coming out to be Q inversion Cux plus Vt. So from here, your Q inversion is coming out to be Cux into Vg minus Vt. Or I can say that Q inversion is proportional to Vg minus Vt. Vg minus Vt when applied gate voltage is more than Vt. Is that clear to you? So can I draw the semiconductor charge? What is the semiconductor charge? Q semiconductor. Here I wrote no Q semiconductor, where Q inversion plus Q depletion. So can I draw the semiconductor charge versus voltage plot? How will I draw it? Till Vt. First I am talking about inversion charge. So till Vt, I will say that, sir, inversion charge is nearly zero. Inversion charge is nearly zero. But after that, it will rise up in linear fashion like this. So this is the plot of inversion charge I have made. Can I draw the plot of depletion charge as well? So how will the plot of depletion charge would go? Sir, it will increase until Vt, like for Vg less than Vt. For Vg less than Vt, if you increase Vg, then what will happen? Depletion width will increase. If depletion width increases, this is for less than threshold voltage. When we are less than threshold voltage, if depletion width increases, then what will happen? Then your Q depletion will also increase, right? So Q depletion keeps on increasing, but after Vt, it will saturate. Why saturating? Saturating means after Vt, it will not increase because depletion width has become fixed. If depletion width is fixed, that means depletion charge will not increase. So after Vt, it will not increase. So in that manner, the graph would go. In this manner, the graph would go. After Vt, it is not increasing. Is that understandable to you? So this is your depletion charge. So Q semiconductor charge is nothing but addition of both of them. So Q semiconductor is nothing but Q depletion plus Q inversion. Okay. All good. So after this, which condition I started? Strong inversion. So I am writing down strong inversion, SI, strong inversion. So after this strong inversion condition I started, where inversion charge is increasing, but depletion charge remains as it is. It remains constant. And at very high voltage, what you can see, sir, this inversion charge has increased very high, but depletion charge remains there as it is. So at very high voltage, you can ignore this depletion charge. At very high applied voltage. So this formula also, this relation also you will remember that Q inversion is proportional to Vg minus Vt. One gate question have been asked upon this particular formula. So can you solve this question? What they are asking inversion charge density at 1.8 volt, at applied voltage of 0.8 they have mentioned the value, at applied voltage of 0.1 at applied voltage of 1.3 as well they have mentioned the value. They are asking at 1.8 volt. So I know one thing, that sir, my inversion charge is proportional to Vg minus Vt, right? So at 0.8 volt, 0.8 volt minus Vt. So what is the inversion charge? 2 into 10 to power 11. And then the inversion charge is 4 into 10 to power 11 when your applied voltage is 1.3 minus Vt. So from here what you will get? If you simply take the ratio, what you will be getting? Sir, 1 by 2 equals to 0.8 minus Vt divided by 1.3 minus Vt. Okay. And just mark one thing, that this is the inversion charge per unit area, not the total inversion charge. Okay. Inversion charge per unit area. Also it is the number of electrons. So basically let's just say I say area is 10 to the power minus 4. Okay. This is the area. And I ask you how much inversion charge we are having at this condition. How much inversion charge in Coulomb? So they are giving the number of electrons. This is the number of electrons. So if you multiply with the area, what you will get? 2 into 10 to the power 7. 2 into 10 to the power 11 multiply with 10 to the power minus 4. So 2 into 10 to the power 7 electrons you have got. Okay. And now you need to calculate the area in Coulomb. Sorry, now you need to calculate the charge in Coulomb. So you will multiply with 1.6 into 10 to the power 1.6 into 10 to the power minus 19. So this will be your answer of total charge. So what you will get? 3.2 into 10 to the power minus 12 Coulomb charge. So this much charge you are having. Is that clear to you? Like a lot of times I have mentioned, I have seen that in Niemann's book, what they have mentioned, they always talk about the number of charge. They always talk about the number of electrons or number of holes, number of positive charge, number of negative charge. They don't talk about the total charge. Is that clear to you what I am saying? Basically, they will not multiply with the 1.6 into 10 to the power minus 19. That you have to do on your own. Number of charge and total charge both are the different thing. So these many number of electrons you are having. Now how much charge you will have? Multiply with 1.6 into 10 to the power minus 19. Okay. So this is just one small point that I needed to tell. It might be helpful in your examination. So 1.3 minus Vt would be equals to this scenario, and Vt would come out to be 0.3, right? So your threshold voltage was 0.3, and it verifies the thing that Vg is more than Vt only. Now they are asking at 1.8 volt. At 1.8 volt, how much inversion charge you will get? So your inversion charge, how much inversion charge you will get at 1.8 volt? So what I can do is that, so inversion charge at 1.8 volt I need to find out. That would be equivalent to Vg minus Vt. Vg is 1.8 minus Vt is 0.3. But ratio I need to take, no? So ratio I am taking. So I can take the ratio of 0.8 minus 0.3, and here an inversion charge I will take, that is 2 into 10 to the power 11. I hope you are able to understand this calculation. Not very tough. So inversion charge would come out to be, basically ratio only I have taken, no? 0.8 minus Vt is proportional to 2 into 10 to the power 11. So that I have taken. Now 1.8 minus Vt would be proportional to Q inversion, that I need to find out. So this is my final answer that I need to find out, right? This is something that I need to find out at 1.8 volt. So here I am just putting that at 1.8 volt. What is the inversion charge you are getting at 1.8 volt? So that would be 1.5 divided by 0.5, that would be 3. Right? 1.5 divided by 0.5. So that would be 3. So 6 into 10 to the power 11 centimeter square. Inversion carrier density. So it is the carrier density, not the charge. Carrier density. So this will be the answer. So it is not the charge actually, it is the carrier density. Carrier density per unit area. Okay. Right? If we want to find out the charge, then what I will do, I will multiply with the area, and I will multiply with 1.6 into 10 to the power minus 19 as well. Then I will get the total charge in Coulomb. But what I need to find out, I only need to find out the carrier density proportional to Vg minus Vt again. Then just remove the proportionality sign, you get the answer. Threshold voltage was 0.3. Threshold voltage I put here, and then I get the value of inversion carrier density, not charge, inversion carrier density at 1.8 volt. Okay, so that would be 3 times of 2 into 10 to the power 11. Very simple thing, right? Okay, so the threshold voltage we have seen, charge float we have seen, all these things we have seen. Now what we need to do, we need to find out the capacitance value. Capacitance value, which mode is going on? Strong inversion mode is going on. Which mode is going on? Strong inversion. Strong inversion is going on. So in strong inversion, what did I say? That a thin layer will be made. And that thin layer of electrons will say that, here sir, a lot of positive charge, positive. This thin layer of electrons will say that we will provide you whatever that you require, whatever the negative charge you require, we will provide you. So this thin layer will be made, and he will be providing you everything that you need. That means you don't need to go to the depletion region, you don't need to go to the semiconductor, right? So he will say that we will provide you everything that you desire for. So electric field lines will not go inside. So what do you think? What will be the capacitance value you will be getting? So capacitance value we will get is, sorry,
total capacitance value between point A and B. CAB, which we are denoting as C only, that would come out to be COX, epsilon OX, TOX into area, because semiconductor is playing no role. Sir, what is the meaning of omega low frequency? So we will talk about it, have some patience. Okay, so can we draw the plot? Yes, sir. Surely you can draw the plot, sir. Now we are able to understand. This was our accumulation mode. Then, sir, inversion was there. Sorry, depletion was there, weak inversion was there. But after that, at VT, this kind of plot we have got. At threshold voltage, this kind of plot we have got. This is our threshold voltage. So started with COX, ended with COX. Some part was of depletion, some part was of a weak inversion, and then, sir, this part will be of a strong inversion. And sir, this part was a accumulation. Here, what was the capacitance value? Sir, here the capacitance value was COX into C depletion divided by COX plus C depletion. Let's not write it down here. Let's not write it down. Okay. But I know that this value was COX and this value is something else. Okay. So can I say this is my minimum capacitance? This is my minimum capacitance. C minimum. Right? And this was my COX, which is my maximum capacitance. So if I say what is the maximum capacitance you will get, so that would be COX. What is the minimum capacitance you get? So that would be COX into C depletion minimum. Look, COX is not changeable, but C depletion is changeable, no? Because what is C depletion? So C depletion is nothing but epsilon SI multiply with the area W depletion. This is your C depletion, right? Or W depletion we are representing by XD. This is our XD, right? So here I will put XD. But here in this condition, at VT, XD has become XD max. That means C depletion minimum would be epsilon SI into A, and XD has become XD max, right? In the strong inversion, at this particular condition, XD has become XD max. So C minimum would be COX multiplied with C depletion divided by COX plus C depletion minimum. Okay. So this is the scenario. And some people can talk about the ratios as well. So whatever the ratio and everything you get, that is not a matter of concern for me. Like C max by C minimum, that kind of ratio you can calculate, all these kind of things you can do, but let's not focus on that particular part. Mathematical part we don't need to focus. We just know that C max will be COX, C minimum would be, so it is like a parallel combination of a COX plus C depletion. Sorry, series combination of COX and C depletion. So series combination of COX and C depletion would be COX into C depletion divided by COX plus C depletion. C depletion is epsilon SI divided by X depletion, right? And if you need to find out the minimum value of C depletion, that means XD max you need to take. If XD is maximum, that means C depletion is minimum. So if this is minimum, then total capacitance will also be minimum. So this is the scenario you are getting, but you are getting it at low frequency. What is the meaning of low frequency? The meaning of low frequency is that, sir, this omega is low. So what we were actually doing, let's just say this VG was 5 volt. So at the 5 volt, we know that we have got an inversion layer. At 5 volt, we know that, sir, we have got an inversion layer. Good enough inversion layer is there. Now we were superimposing a small signal. That means now our signal can go from 5 to 5.1 and it can go to 4.9 as well. That means this kind of input we are having now. What is our input? Our input is total input across the capacitor. So I can say capacitor voltage. What is my capacitor voltage? So that is Vg plus 0.1 sin omega t. So Vg plus 0.1 sin omega t, this point is 5, this point is 5.1 and this point is 4.9. So now my input can go from 5 to 5.1 and 5.1 to 4.9 as well. But it is going slowly. So here with respect to 5 volt, I am having Q1 charge. So this Q1 will say that I need minus Q1 charge, you are fine. Then slowly from 5 to you are going to 5.1.
Slowly you are going, no? Then 5.1 will say that I need Q2 charge. With respect to Q2, I require minus Q2 charge. So this inversion layer will say that I will provide you that minus Q2 charge. Then from 5.1 to 4.9 you are going. He requires Q3 charge. With respect to Q3 charge, he will say I need minus Q3 charge. Inversion layer will say that I will provide you that. Why inversion layer is able to provide that negative charge? Why inversion layer is able to provide these charges? Because the process is slow, no? But what if the process was very fast? What if the frequency was very fast? From 5 to 5.1, 4.9, 5.1, 4.9. So the charge on this metallic plate will change very fastly. So metal will say I need minus Q1. Okay. The very next second it will say that I need minus Q2. But inversion layer will say, sir, I have been made in P type. Sir, my surface is P type. In P type, I have made my home that is N type. So sir, I need some time to generate these electrons. What I am saying is that, let's just say frequency is very fast. So this metal is saying that I need charge corresponding to 5.1. That means inversion layer needs to generate more electrons. This particular inversion layer needs to generate more electrons. Initially, they were having electrons corresponding to 5 volt. But now with respect to 5.1, they need to generate more electrons. So there will be some generation, generation time as well, no? Generation lifetime would be there, no? Are you able to understand this point? To generate these electrons, it will take some time, no? But if the frequency is low, it will get enough time. But if the frequency is fast, that means 5.1, 4.9, 5.1, 4.9, very, very fastly it is going on. Then this inversion layer will say that, sir, I am not able to provide you the negative charge that you require. You go into the depletion width. Then this positive charge will have to take help of the depletion width. That means electric field lines will go inside the depletion width if the frequency is high. Are you able to understand this point? The job is, whatever the positive charge at the metallic plate you are having, semiconductor needs to provide the negative charge corresponding to that. Whatever the positive charge you are having on the metal, semiconductor needs to provide negative charge corresponding to that particular positive charge. If positive charge increases, inversion layer was saying that I will take the responsibility because we are in the strong inversion mode. So I will take the responsibility, but the charge change is happening fastly because omega is fast. Omega is more, that means charge change is happening very fastly. So 5.1, 5.1, 4.9, 5.1, 4.9, in this manner it is changing very fastly. Then this inversion layer will say that, sir, I am N type which has made his home in P type. This N type has made his home in P type. So sir, very fastly I will not be able to provide you this much of charge. Like the change in charge, I will not be able to provide you very fastly because I need to generate these electrons. Positive charge means holes will go down. That means holes are going down. That means electrons should be generated. So electron generation will take some time. But immediately he will say that I need positive charge, I need more negative charge, I need more negative charge. Then what inversion layer will say? Sir, I am not able to provide you. Go take the help of depletion layer. That means electric field lines will go inside the depletion layer like this. But that will happen in higher frequency, not in the lower frequency. Are you able to understand this point? So what kind of graph you will get, that we will see. Okay, so that's why it was mentioned omega is low. But if your omega is high, then what kind of graph we will get? So here, this was the scenario for, this is the scenario I am making for omega low frequency. Low frequency means slowly it is changing, I am able to provide the charge. But who knows, some depletion width we need to take at some other frequency, we need to take the help of depletion width. At some other frequency, we need to take the help of depletion width. That means this much of capacitance we will get. So here the capacitance I was getting was COX, but now I am getting the capacitance as COX C depletion divided by COX plus C depletion. Now it depends how much help of depletion width you require. How much charge from the depletion width you require. If you require more charge, that means more depletion width help you will take. More depletion width help you will take. That means more C depletion will come into action. more C depletion will come into action. That means charge will be, sorry, capacitance would be lesser, and lesser, and it might happen that your capacitance can become equals to this particular thing as well. That means this positive charge can take help of complete depletion width as well. So this is the lowest frequency and this is the highest frequency. And this is your threshold voltage. This is your COX. Is that clear to you? And all this is happening in strong inversion mode. Can anyone think that, sir, why this problem was not there in the accumulation mode? Because in the accumulation mode, here what we were having, holes, and holes are being generated here. So this whole region is of holes only. In the whole area, holes are dominating, and you are providing negative charge here. Negative charge you are providing in, I'm talking about accumulation mode. What I'm talking about? I'm talking about accumulation mode. So like problem is that, sir, in accumulation mode, if the frequency was high, then why I was not encountering this problem? Because in the accumulation mode, everything was of holes only. He says I need more holes. Without any doubt, he will say I can provide you more holes. Because here holes are not being generated. They are just being pulled. Are you able to understand this point? A lot of holes I am already having. He says I need more holes. He will say I will provide you. More holes, I will provide you. I will provide you. I will provide you. But if I have applied positive charge, then here what we have generated? We have generated electrons. This is the condition we are having, and this is the inversion charge we are having. Now if we increase this charge, that means if the frequency is high, very fastly we are saying that provide me more negative charge. Very fastly we are saying that provide me more negative charge. Then he will say, sir, I am not able to provide you more negative charge. You go into the depletion width, you take help of the depletion width to get the negative charge. I am not able to provide you. Why so? Because here the condition is that this inversion layer needs to generate the electrons. So your frequency of generation is less than your frequency of applied small signal, applied AC signal I am putting. Okay. So this is your frequency of generation of electrons. So your F generation is less than the frequency of AC signal. This is the scenario. The number of electrons that are being generated with some frequency, like it will take some time for the electrons to be generated, right? Now that time is larger than the, like if frequency is lesser, that means time is larger, or I can say that tau generation is more than the tau of, is more than, here this is your frequency omega, right? So omega is nothing but 2 pi f AC signal. So if you are representing in time, then what I am saying is that f AC signal is nothing but 1 by t AC. So here I can put t AC. Fine. So now these electrons need some time to be generated. Since electrons are saying that, sir, we will take some time to be generated, then what they will say, positive charge will say that I will take the help of depletion width. I will take the help of depletion width. I will take the help of depletion width. So now your electric field lines are going inside the depletion width. So if they are going inside the depletion width, that means for the total capacitance, depletion width will also come into action. So again your capacitance would become COX multiply with C depletion divided by COX plus C depletion. Now it depends how much help of depletion width you are taking. Maximum help you can take, that would be XD max, like complete depletion width help you have taken. That is the maximum help you can take. Is that clear to you or not? So this will be the plot for higher frequencies and this is the plot of lower frequencies. Is that clear or not? Important point, usually people remember it that, sir, at a lower frequency I will get this much of capacitance, at higher frequencies I will get a lower capacitance. But no need to remember, you have the pure concept with you. Higher frequency means lesser time you are getting, inversion layer will not be able to provide the number of electrons, then the negative charge will be taken from the depletion width. That's why depletion width will also come into action and total capacitance would become COX into C depletion divided by COX plus C depletion. Is that clear? Absolutely everything is clear.
So these kind of diagrams we are getting. So these are the ideal plots we are having. These are the ideal plots. So actual non-ideal plot you will get somewhat like this. Like what was the ideal plot we were having? This kind of plot. But actually what we are getting? This kind of plot. Nature is same only. It's just that this point is a bit lower. At 0 voltage, you are having the capacitance. What will be this capacitance? So this capacitance is CUX. What is this capacitance? So this capacitance is also CUX. Can I call this capacitance as C flat band capacitance? Why is that so? Because this particular graph we have made considering flat band voltage is 0. So can I call it flat band capacitance? Yes sir. At 0 voltage. 0 voltage means flat band voltage we have considered 0. All the analysis that we have done considering 0 flat band voltage. So considering 0 flat band voltage, can I call it flat band capacitance? Yes sir. Flat band capacitance is a bit lesser than CUX. Why it is bit lesser? We will talk about it. Now C minimum you will get at VT. This point is your VT. And if I need to show the region, then sir, this kind of region we will be getting. Sir, this will be your depletion region and this will be your weak inversion. And this will be your strong inversion. And sir, this was your, what this was, this is your accumulation. And this point is known as flat band. So I am removing this. This point is known as flat band. Okay. So now the point is that sir, why at the flat band I am having lesser capacitance, a bit lesser capacitance I am having than the CUX capacitance. Here this value was epsilon OX multiply with the area divided by TUX. So at the flat band, why the capacitance is a bit lesser? That is the matter of concern now. Sir, here why there is not a sudden increase? It is pretty obvious, no? Like you will be able to understand that it might happen that these many electrons were not enough. So it might happen that some help of depletion region it was taking. Are you able to understand this point? Like here you are saying that sir 10 to the power 16 centimeter cube inverse, this much number of electrons we are having, but still the charge is very low, no? So it might happen that this particular charge was not enough to compensate to this positive charge. Then it will take help of some depletion region. So VT is like a threshold point that we say that after this your capacitance will start increasing. Basically after this the inversion layer will start taking some responsibility. So it's not necessary that sir at this point only inversion layer will say that I will take the whole responsibility. It will take some time, right? Slowly it will start taking the whole responsibility, but the threshold point is that after this particular point the inversion layer will be activated that yes, now I will provide the negative charge. But this negative charge, like basically you can understand here, no? Like sir, just here you are saying that sir inversion charge is ignored, and after that you are saying that sir I will take inversion charge into action. So till this particular point, just imagine this particular point. So till this particular point, still your depletion charge is more than the inversion charge. That means still in depletion charge will play some role. And if depletion charge is playing some role, that means depletion width is coming into action. If depletion width is coming into action, that means your capacitance would be at this point. If I ask you to calculate the capacitance, then what it would be? Sir, COX into C depletion divided by COX plus C depletion. It might happen that we are taking some help of depletion layer or some more help of depletion layer. Here we are taking less help of depletion layer. At this point we are taking zero help of depletion layer. Okay, so threshold point is defined as one particular point where your inversion layer is activated. After that inversion layer will say that I can give you negative charge, but ideally you should say that sir whole charge will be provided by the inversion charge, but practically inversion layer will say that yes, some help of depletion layer also you take, but if you keep on increasing the voltage, then I will keep on increasing my charge, and after some time the whole responsibility will be taken by me. You don't need to go to the depletion region. So here whole responsibility will be taken by the inversion charge only. But after this point depletion charge is also into the action and inversion charge is also into the action, but after a certain voltage inversion layer will say whole responsibility will be on me. So this should not be a matter of concern for you. Sudden increase will not be there. Sudden increase will not be there that suddenly depletion layer is saying that I will provide you the whole charge. No.
Suddenly the inversion layer will say that I will provide you the whole charge. That will not happen. Inversion layer will be activated, but some help of depletion layer will surely be taken. Understandable, right? But this is a good point, that why at 0 voltage you are having a bit lesser capacitance, but here the capacitance was COX. So C flat band is a bit lesser than COX. Why is that so? This is the matter of concern. So let's try calculating the capacitance at 0 voltage. That means my applied voltage is 0. I am trying to calculate the capacitance at 0 applied voltage. How do you measure the capacitance? Sir, first this signal will not be there. This particular signal will not be there. Initially this particular signal will not be there. Sir, I will provide a particular voltage. Because of that some positive charge would come here, some positive charge or negative charge here. In the accumulation mode, what I provide? In accumulation mode, sir, I provide the negative charge. So sir, first I will provide some negative charge here. Because of that, holes and holes will come here. And now sir, I will provide this small signal. So this is how you calculate the capacitance value. That first I will give you Vg. First I will give you Vg, and after that I will provide some small signal input value. And based on that I will see what is the change in charge I am getting with respect to the change in voltage. And then I will get my capacitance value. So that was the COX I was getting when this Vg was, let's just say, some minus 4 volt. But if I have applied 0 volt initially, that means no charge was there, no holes were accumulated here. Are you able to understand what I am saying? If I have provided 0 volt, what does that mean? 0 volt I have provided, that means no negative charge was there, no holes have been accumulated. That means this is the condition, sir. This is the condition. This is the condition. Right? Now what you do? You superimpose a small signal, which is like this. It can give you the value of 0.1. It can also give you the value of minus 0.1. So let's just say minus 0.1 came here. Now this minus 0.1 will say that I need some minus Q1 charge. So minus Q1 charge, then holes will say that yes, we will give you. But again, holes are not very strong here, no? In accumulation mode, the holes concentration became 10 to the power 18. In the bulk, it was 10 to the power 16, but near the surface, it became 10 to the power 18. Holes were very strong, and they were saying that you cannot get into the semiconductor. You will stay on the surface only. But because of the 0 voltage, there is no accumulation layer. Holes are not being accumulated. Are you able to understand this point? What I am saying? Because of this applied 0 voltage, holes are not accumulated near the surface. That means the electric field will come. Semiconductor will say that I can provide you holes, but electric field will say, now you are not that much strong. Since you are not that much strong, so I will penetrate a bit inside your semiconductor. So your electric field is penetrating inside the semiconductor for a very minute length, and that length is known as dBi length. Okay, what it is known as? dBi length. Electric field is penetrating inside the semiconductor for a very minute dBi length. Why is that so? Because sir, when you applied 0 voltage, when I was applying sir minus 4 voltage, when minus 4 voltage was applied, sir, a lot of holes were there. Then this change in voltage was not troubling me much. When minus 4 was applied, then no matter whatever the voltage change you do, this particular layer, this very strong accumulation layer was saying that I will provide you all the charges, don't get inside the semiconductor. But sir, because of this 0 voltage, I am not having any layer here. So electric field will come and he will say that, okay, you are providing me holes, but not that much strong. That means I will penetrate a bit inside the semiconductor till that dBi length. Till that dBi length. Till that dBi length. So effectively what we are having another capacitance, that is our dBi capacitance, I can say, that is epsilon Si multiply with area divided by dBi length. So your total capacitance at flat band would become COX into CD upon COX plus CD. There you go. And which will be a bit lesser than COX. Okay. So C flat band would be a bit lesser than COX. So these kind of questions in interview can be asked, that at flat band or at 0 voltage, why a bit less capacitance you are having. Because sir, in accumulation I was having a good enough layer. In the accumulation mode I was having a good enough layer of holes, and that layer was enough to provide any positive charge that was required. But sir, because of the zero voltage, no accumulation layer has been framed. No accumulation layer is there. That means the negative charge from the direction, again I have made opposite. Again and again I mess it up. The direction will be opposite, no? The electric field will be going from the positive to negative. So for a very minute dBi length, this will be the electric field. Again and again opposite direction I take. From positive to negative it will go, no? So sir, electric field lines will penetrate a bit more inside the semiconductor. Why is that so? Because sir, there is no accumulation layer. If accumulation layer was there, then he was very strong. Accumulation layer was very strong. He was saying that I will not let you penetrate through my semiconductor. But even though holes are more than enough, they are providing them negative charges. So they are providing them positive charges, whatever the positive charge you require. But still, a bit length in the semiconductor, it will penetrate. That's why the capacitance is becoming a bit lesser than COX. A bit lesser than COX. So at the flat band, you will still get a bit lesser than COX capacitance. So this theory has also been written here. This theory has been written here. Why flat band capacitance is less than the oxide or accumulation capacitance. At flat band, the semiconductor is not perfectly conducting. Even though the band bending is zero, the semiconductor still responds to small AC signal by disturbing charge over a finite dBi length inside the semiconductor or silicon rather than strictly at the surface. That means electric field lines are penetrating through the semiconductor for a very minute dBi length. This finite charge spreading makes the semiconductor behave like a large but not infinite capacitance. This capacitance will be very large. This will be very large but not infinite. If it was infinite, then C flat band would have been equal to COX. If it was infinite, if CD is infinity, then you can calculate this particular thing. What will happen is that C flat band would become equal to COX. But still, it is not infinity but very large. Since this semiconductor capacitance appear in series with the oxide capacitance, then the total MOS capacitance at flat band becomes slightly lesser than the pure oxide capacitance measured in accumulation mode, where the semiconductor surface behaves like a metal and contributes to effectively infinite capacitance in the semiconductor. But here, the capacitance inside the semiconductor is also good enough. That means this was your oxide capacitance. Along with that, inside the semiconductor as well, some capacitance you are getting, which is CD. So this is your total capacitance. This is your gate and this is your body. So total capacitance is COX multiplied with CD upon COX plus CD, which is a bit lesser than the flat band capacitance. Okay, so these are good interview questions. I need to change the slide. We will just continue this discussion. We need to solve some questions and some more points are left. Okay, so hardly I guess 1 hour of discussion is left. We will do that discussion. Let me pause the video because I need to change the slide. Slides are completed. Okay, so I will change the slide and then I will come back. We will do the discussion. First we will solve some problem and then we will do whatever the discussion that is required. Okay, well and good. So let me change the slide and I will come back. Okay, then yeah, thank you very much. Yeah, welcome back guys. So let's solve a question. Okay, this question is given. What you need to find out? You need to find out the maximum depletion width. Ratio of permittivity of silicon to ratio of permittivity of oxide is given. Oxide thickness is also given. MOSCAP is there. What kind of substrate is there? Can you tell what kind of substrate we have used? P-type substrate. Because this particular curve we have already seen. For N-type substrate, the curve would be somewhat like this. Okay, so we will see this curve, don't worry. Basically, in N-type substrate, opposite process would happen. No? So we will talk about N-type substrate as well in this video only. So let's solve this question first. We know that it is P-type substrate, epsilon Si, epsilon Ox ratio is given, Tox value is given, and you know that what this value is? 10 picofarad. 10 picofarad is nothing but Cox only. Do you agree to this point? Yes, sir. Surely I agree to this point. What do you think? What is 2 picofarad? 2 picofarad is nothing but sir Cox C depletion upon Cox plus C depletion. But here depletion width would be C depletion would be minimum, right? Or you can say
depletion width would be maximum. So depletion capacitance would be minimum and depletion width would be maximum for 2 picofarad. Now this is 10 picofarad that is given. Can you find out C depletion minimum? What would be your C depletion minimum? Can you find it out? Sir, this is 2 picofarad, 10 picofarad I already know. So here you put 10 picofarad and you find out the C depletion value. Directly I can think of finding it out. Basically what I can do is that 1 by 10 would be equals to 1 by 2 plus 1 by C depletion. Oh, sorry. Basically what I am doing, 1 by C minimum would be equals to 1 by COX plus 1 by C depletion minimum. Do you agree to this point? Yes, sir. I agree to this point. From here, what you can find out, 1 by 2 would be equals to 1 by 10 plus 1 by C depletion minimum. Right? So this is 0.5, 0.4, 2.5. So C depletion minimum is coming out to be 2.5. And you can check as well, sir, parallel combination of 10 and 2.5. Or better, we should say series combination of 10 and 2.5. That would be this much. Answer is 2 only. Right? Did you understand this calculation? Series combination of capacitors, 2 picofarad. Very easily you can do the calculation. Minimum 1 by 10 would be, COX would be 1 by 10. C minimum is 1 by 2 picofarad plus 1 by C depletion minimum that I need to find out, that is coming out to be 2.5 picofarad. Right? So what is your COX? COX is epsilon OX multiplied with the area divided by TOX, that is 10 picofarad. What is C depletion minimum? Sir, that is epsilon SI multiplied with the area divided by XD maximum, and that's equals to 2.5 picofarad. Say yes or no? Right? Epsilon SI divided by XD maximum multiplied with the area. Just take the ratio of both of them. If you take the ratio, what you will get? Epsilon OX divided by TOX multiplied with XD max divided by epsilon SI ratio we are taking. So epsilon OX divided by epsilon XI TOX, yeah, that would be equivalent to 10 divided by 2.5, that would be 4. Now epsilon OX divided by epsilon SI, epsilon OX divided by epsilon SI, that would be 1 by 3. Epsilon OX divided by epsilon SI, that would be 1 by 3 into 1 by TOX. Epsilon OX divided by epsilon SI, I am putting 1 by 3. TOX is nothing but 1.8 micrometer. And XD max, that would be equivalent to 4. So your XD max would come out to be 4 into 3 into 1.8 micrometer. So 12 into 1.8. What that would be? 21.6 micrometer. Say yes or no? Okay, very simple thing. Like some people might be doing complex calculation, but here for this particular question the task was how simple you can make your calculation. I know this is my COX, I know this what is my 2 picofarad. From here I can find out the C depletion. For both of them I know the formula. Just simply take the ratio. Because why I took the ratio? Because I know the ratio of epsilon OX, epsilon SI, right? A and A will get cancelled out. TOX I already know. XD max I will be able to get. That's it. Okay. I hope I have taken the ratio in a correct manner. 1 by 3, then TOX, XD max. Yeah. Yeah, fine. Okay. Let's go to the next one. Now, what kind of known identities we saw in our MOSCAP? Sir, first one we saw that phi ms is not equals to 0. That means metal work function and the semiconductor work function are different. Phi msi, sorry, not phi ms, phi msi is not equals to 0. Metal work function and the silicon work function both are not equal. So this was the first known identity that we have understood. Because of the work function, what will happen? Electrons will travel. One side would become positive, one side would become negative, and to get the flat band, you need to apply a flat band voltage, and the flat band voltage here came out to be, it was equals to 5 MSI only. I told you this formula would always work, no matter whether metal work function is more or metal work function is lesser, silicon work function is more or silicon work function is lesser. This formula would always work. Along with that, there could be one more known ideality. That known ideality is your oxide can have some fixed charges. The charges could be positive or negative, and those charges would be near to the semiconductor. Sir, how these charges come? During the fabrication. Basically, you fabricated metal oxide semiconductor, no? So this will be silicon. The oxide that you use, that is SiO2, and the metal that you use, that would be polysilicon. In the end, we will talk about it when we complete our MOSFET chapter, no? So I will talk about the fabrication as well in brief. What is polysilicon, what is SiO2, what is Si. So regarding the fabrication, I will talk in brief. So metal oxide semiconductor we use, semiconductor would be silicon, oxide would be SiO2, and metal would be polysilicon. Okay, fine. Now because of the fabrication, what will happen is that some charges, some positive charges would come inside the oxide. Because of the fabrication, they have come. Somehow they have come. You did not apply any bias. You did not apply any bias at the gate. You did not apply any bias at the body as well. Or you can say body is simply grounded. But no bias has been applied. Just because of the fabrication, those positive charges have come. Since these positive charges have come in the oxide, so what these positive charges would do? They will say holes go away. Here, what is the scenario? This is our p-type substrate. We are taking the example of p-type substrate only. P-type. So what they will say? Holes go away. Holes go away means negative, 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 negative. So in the semiconductor, what you are having? You are already having some negative charges. So what kind of band bending you will have? Sir, this kind of band bending I will have. Sir, why this kind of band bending? Holes have gone away. Hole concentration has decreased. That means EFI and EFP gap would decrease. So this kind of band bending would be there. Even without applying any bias. We are not applying any bias. Without applying any bias, this kind of band bending we are getting because of the fixed positive charges in the oxide. If the charges were negative, then what would have happened? Negative charges, what they would have done? Holes come to me. So hole concentration would increase. Hole concentration would increase. That means this kind of band bending would have. This kind of band bending we would be having, and here more holes means more positive charge. So we would be having more positive charge here. So if oxide charge is negative, here I will get positive. If oxide charges are positive, I am getting negative. Understandable? Okay. Now you just let me know, take your time and think about it. What kind of bias I need to apply on gate? Body is grounded, okay? What kind of bias I need to apply on gate such that the effect of this negative charges are gone? You want to kill the effect of these negative charges. What kind of bias you need to apply? Positive bias or negative bias? Think about it and let me know. Someone said, sir, positive bias. If you apply positive bias, then what will happen? If I had applied positive bias, then what will happen? What this positive bias will do? It will say go back holes. This positive guy was also saying go back holes, and this positive guy is also saying go back holes. That means you are creating more negative here, no? But I don't want to create more negative. What I want to create? I want to create positive. I need to kill this negative. For killing this negative, here what I need to create? I need to create positive. So in the semiconductor, I need to create positive. That means at the gate, what I need to apply? At the gate, I need to apply negative only, no? Is that clear to you? Because at the gate, if I apply negative, what he will say? Holes come to me. What this positive charge is saying? Holes go back. So this negative charge is saying holes come to me. This positive charge is saying holes go back. That means holes will stay at their ore position only, and there will not be any negative charge that will be induced in the semiconductor. Basically, I want those bands to be flat. If I want those bands to be flat, that means I want to kill the effect of these negative charges. Now someone would have a doubt that, sir, before applying this particular thing, before applying these negative charges, because of these positive charges, there would be some depletion width, no? There would be some depletion width. Now let's just say these positive charges were very high, so it might happen that some charge carriers can also be there, right? Positive charge is very high such that some charge carriers are also there. And depletion width would also be there. Now I am saying that I need to apply the same amount of negative charge on the metal. Whatever, let's just say here I was having QX charge. So if I apply minus QX charge here, then my job would be done. I would be getting the flat bands. Now my question is, QX would be equals to what? Capacitance multiply with voltage. Voltage, VOX voltage I will put. So here what capacitance should come? Someone would say that, sir, oxide capacitance is also there and depletion width is also there. So COX, C depletion upon COX plus C depletion. This capacitance should come. Here, what is the scenario that, sir, plus QX charge is there. To kill the effect of this plus QX charge, I need to apply minus QX charge here. Because if I apply minus QX charge here, then because of this plus QX charge, what has happened? Here plus QX charge has come. Say yes or no? Because of this plus QX charge, here in the semiconductor, minus QX charge has come. Now on the metal plate, if I have applied minus QX charge, then because of that what will happen? Plus QX charge would come and total charge would become 0. Say yes or no? Fine, understandable. Now the problem is, sir, what will be your minus QX or plus QX? I am interested in the value of QX. So that would be, sir, capacitance multiply with the voltage. What kind of capacitance? COX multiply with C depletion upon COX plus C depletion, or only COX or only C depletion. As of now, looking at this diagram, it feels like that, sir, it would be a series combination of COX and C depletion because, sir, depletion layer will be made. But why you are applying this negative charge? To kill the depletion layer, no? That means eventually your depletion layer should be 0. You are applying this negative charge to kill the depletion layer. That means this depletion width has to be 0 eventually. So that means eventually this guy has to be 0 or infinity. Sorry guys, this should be infinity, because if this is infinity, C depletion is infinity, then it will not come into action. Total capacitance would become COX only. So eventually we are applying this negative charge to kill the depletion region. So the depletion capacitance I will not take into action. My capacitance here would be simply COX only. A very important doubt we are discussing, which can be asked in the interviews. In the interviews, they will say that we are having some fixed positive charge in the oxide. Positive charge will not induce. Because of the positive charge, here you will get a depletion width, a depletion layer you will get where negative charges are piled up. Now, to kill that negative charges, what you will do? You will apply negative charges on the metal plate so that positive charges are induced in the depletion layer. So positive and negative will cancel out each other and total charge would be 0. So sir, my job is done. That means on the metal plate, I need to apply minus QX charge. If I was having plus QX charge in the oxide, then on the metal plate, I need to apply minus QX charge. Now, if you need to write down the expression of QX, what that would be? Capacitance into the voltage. Voltage is VOX, oxide voltage. What capacitance you will take? Sir, I will take only the oxide capacitance. I will take only the oxide voltage as well, because eventually this voltage and this capacitance, so eventually this voltage and this capacitance are being nullified. Eventually your depletion width would be 0. Eventually your depletion capacitance would be infinity. We are applying this negative charge to nullify the effect of this depletion layer only. So when I write down QX, I will simply write down COX multiply with VOX. Is that clear to you or not? Okay, so that's it. This is the complete discussion. Usually how it is taught that positive charge would be there, negative charge would be there, and then you need to apply, and negative charge is there. I have seen some notes, what they would say then, because of this negative charge, here positive charge is induced. And to kill this positive charge, you need to apply negative charge. Absolutely baseless explanation. Okay. What will be the wrong explanation? Because of this positive charge in the oxide, we are getting negative charge in the semiconductor. This negative charge in the semiconductor, it inducing positive charge in the metal. To kill this positive charge in the metal, we need to apply negative charge. That is absolutely baseless explanation. Positive charge in the oxide, because of that holes are being repelled, you are getting a depletion region. We need to kill this depletion region. For killing this particular depletion region, what we need to apply? We need to apply negative charge so that it will attract the holes. And once it has attracted the holes, depletion region is gone. That means these bands will be flat. Okay, so explanation and all we are not writing, but I hope you have understood the point here. Well and good. Okay,
So in the oxide, if I am having plus QX charge, then I need to apply minus QX. In the oxide, if I was having minus QX, then I need to apply plus QX, right? So what I have written, to get the flat bands, we need to apply minus QX charge on the metal, then our gate voltage, or you can say our flat band voltage, would be nothing but that would be Q equals to CV. So voltage would be Q by C. So that would be minus QX upon COX. Minus QX upon COX. There you go. Say yes or no. This would be our flat band voltage. So positive charge means you will apply negative charge. Negative charge means negative voltage I need to apply, right? Negative charge means negative voltage, right? That is understandable. Negative voltage I need to apply. So how much negative voltage I need to apply? Minus QX upon COX. Say yes or no. This is our flat band voltage. Okay. Try solving this question. Important part is just read this particular statement. Charges per centimeter cube. Sorry, charges per centimeter square. Charges. What does that mean? One charge would be equals to 1.6 into 10 power minus 19 coulomb. So here you need to multiply with 1.6 into 10 power minus 19. A lot of people will forget that. So let's find out the flat band voltage. What they are saying. A semiconductor uses a p-type silicon substrate and a silicon dioxide insulator of thickness 20 nanometer. Oxide thickness is given, which is 20 nanometer. 20 nanometer can be written as 2 into 10 power minus 8. That would be 2 into 10 to the power minus 6 centimeter. Oxide charges. Your oxide charges are 5 into 10 to the power 10 charges per centimeter square. That means 5 into 10 power 10 into 1.6 into 10 power minus 19 coulomb per centimeter square. So 8 into 10 to the power minus 9 coulomb per centimeter square. These many oxide charges you are having. 8 into 10 to the power minus 9 coulomb per centimeter square. Okay. Charges per centimeter square. Like the language could have been better, but this is taken from a Niemann only. So in Niemann, this kind of language is written. Charges per centimeter square. But I hope now you understand the meaning of charges per centimeter. What is the meaning of charges? Total number of charges. That means total number of electrons. Here not electrons, I cannot say electrons. Here I would say total number of positive ions. So these are the total number of positive ions. On these positive ion, how much charge would be there? So 1.6 into 10 to the power minus 19, this much charge would be there. So this is our total charge. Okay. So how much flat band voltage I need to apply? Sir, my flat band voltage would be nothing but, sir, positive charge is there, no? Here sign is not given. By default positive sign I will take. If negative charge was there, they would have taken the negative sign. But by default I will take the positive sign here. So minus QX upon COX. Just notice one thing, coulomb per centimeter square. Coulomb per centimeter square. So what will be the value of COX I will be taking? COX dash I will be taking. That would be epsilon OX into TOX, right? Capacitance per unit area. Capacitance per unit area, right? That would be this divided by capacitance epsilon OX divided by TOX. What is epsilon OX? Epsilon OX would be 3.9 into 8.85 into 10 to the power minus 14 divided by TOX. TOX is 2 into 10 to the power minus 6. So 10 to the power minus 15, 1.6 divided by 3.9 divided by 8.85. So 0.046. So our flat band voltage is coming out to be minus 0.046 volt. So because of the fixed oxide charges, this much flat band voltage you need to apply. So two phenomena we have discussed: work function difference. Another one is fixed oxide charges. Fixed oxide charges. Say yes or no. So can you write down the complete formula of flat band voltage? Sir, first one was this one, and other one is fixed oxide charges divided by COX. Now this formula would work in all the conditions, whether it is of p-type substrate, n-type substrate, whether your metal work function is more or silicon work function is more. This formula would always work. Like you should not be having the doubt that, sir, if I am using n-type substrate, then sir, metal work function is more, silicon work function is lesser, then sir, where positive charge would come, where negative charge would come. Ideally, in the examination hole, you should be checking that on metal plate positive charge would come, on silicon negative charge would come. So all these things you should be checking. But after checking everything, we have made a conclusion that this formula would always work. That first you write down the metal work function, then you write down the silicon work function, and then you do. If positive charge is there, then you will put negative sign here. If negative charge is there, then negative it would become positive. Is that understandable what I'm saying? Like if my fixed oxide charges were negative, here they have put positive, no? Because in 99% cases, positive charge only would come. In 99% cases. Okay? But if they were negative, then here what you will put? QX value negative you will put. So by default it would become positive. In the oxide, if I am having negative, then in the semiconductor positive would come. In semiconductor positive would come. Then on the oxide what you need to, on the metal what you need to apply? You need to apply negative. Sorry, on the metal what you need to apply? On the metal you need to apply positive to kill the effect of this positive charge, because this positive will induce negative, and positive will get cancelled out and your job would be done. So in the oxide, if I am having negative, on the semiconductor I need to apply positive. In the oxide, if I am having positive, then on the semiconductor I need to apply negative. So that's why a negative sign I have put here. So here QX is having positive polarity only, but what if it was having negative polarity? So negative will become positive only. Is that understandable? But during the fabrication, in 99.99% cases, positive charge would come, not the negative charge. That's why in the example as well, I am taking positive charge only. In the standard books as well, you will see only positive charge is given. Even in the gate examination as well, one question have come. In that question as well, positive charge was there. But hypothetically, they can introduce negative charge as well. So just remember one thing, negative charge means positive supply I need to pick. Positive charge means I need to apply negative supply. And this 5 MSI would also always work. So let's take the example of a N-type substrate. So what I am having, metal, oxide, semiconductor, N-type substrate is there. So will that make any impact? No impact would be made. No matter whatever the kind of semiconductor you are having, whether P-type or N-type. Our matter of concern is work function. Let's just say this guy was having more work function, metal is having more work function, and semiconductor is having lesser work function. This is the scenario. So this is having more electrons. So what will happen? Electrons will travel from semiconductor to metal. So this side will become positive and this side will become negative. Now on the gate, what you need to apply? To kill the effect of this negative, on the gate I will have to apply positive voltage. On the gate I will have to apply positive voltage. So how much positive voltage I need to apply? Phi m minus phi si. Why phi m minus phi si? Because sir, phi m is more and phi si is lesser. So if I need the positive answer, that means I need to subtract more minus lesser. So I will get the positive answer. Is that understandable to you what I am talking about? So this formula would always work. Blindly close your eyes, you can apply this formula. For the flat band, phi MSI minus QX upon COX, no matter whichever kind of substrate we are having, no matter whatever the kind of condition we are having. For your surety, you can check like this in the examination hall. That sir, yeah, electrons will be going from here to here. This would become positive, this would become negative. That means I need to apply positive charge. Sir, inside the oxide, sir, I am having positive charge. So it will induce negative charge here. To kill the effect of this negative, what I need to apply? Here also I need to apply negative only so that it becomes positive. So negative I need to apply, and here I need to apply. Again, here as well, here I need to apply positive. So once I need to apply positive, then I need to apply negative. So in that manner, you can check in the examination hall that what kind of charge you need to apply. Always this formula would be corrected. Okay. So let's solve this question now. What is given? What is the meaning of this xi? Chi xi. What is the meaning of chi xi? It is electron affinity. Okay. It is nothing but electron affinity. So Nd, Ni value is given, Eg value is given, phi m value is given, and oxide thickness is given. Fixed charges are there. Flat band voltage you need to find. So sir, I remember the formula for flat band voltage. Phi msi minus qx upon cox. Sir, cox can I find out? Yes sir. Epsilon ox upon tux. Sir, why you are not writing down the area? Because charges are also given in charges per centimeter square only. So qx value will also be in the coulomb per centimeter square only. So what will be the value of qx you will be getting? So 4 into 10 power 11 into 1.6 into 10 to power minus 19 coulomb per centimeter square. Coulomb per centimeter square. This is the value of qx you are having, right? Divided by cox, that is epsilon ox divided by tux. This is your cox. Okay.
So epsilon OX value we are having. Epsilon OX value not given. Should be given, right? Nowhere we have mentioned the epsilon values. So that should be given. Otherwise this question will not be solved, no? So epsilon OX, you know, it would be 3.9 epsilon naught, and epsilon SI would be 11.7 epsilon naught. So this value should be mentioned. So this job would be done. QX upon CX would be done. Now I need phi m SI. Metal work function I am having. I need to find out the silicon work function. So for that I can make the Venn diagram. Why I need to make the Venn diagram? Because apparently silicon work function is not given. So I need to find out the work function. So let's make the Venn diagram for N-type semiconductor. So 0.56. This much distance is 0.56, right? 0.56. Right? And here, what is this much distance? This much distance would be, this would be your phi f. So your phi f would be nothing but kt ln 0.0259 and dy ni, 5 into 10 power 16 divided by 1.5 into 10 power 10. 5 into 10 to the power 16 divided by 1.5 into 10 to the power 10. So let's pick the calculator. .259 0.389. So this is your 0.389 electron volt. Okay, and then there is a electron affinity as well. So here we are having electron affinity as well, which is 4.05 electron volt. So what do you think, what will be your work function? Your work function would be this much, right? This would be your work function. This would be your q phi si. Q phi si. So can you find out what will be your phi si? Yes sir. 4.05 4.05 plus 0.56 minus 0.389, right? 0.56 minus 0.389. .22. This is your phi si. What you are having, that is 4.22 electron volt. Very simple. If you solve the question with patience, you will be able to find out what will be your metal work function. Sir, metal work function is not work function. Why I am putting electron volt? I am dealing with the voltage now. So 4.22 volt. And what is your metal work function voltage? That is 4.90. So this time you can see that metal work function is more. That means scenario would be somewhat like this. This is your metal and this is your semiconductor, and this is your vacuum level. So this will be the scenario this time. So scenario would be somewhat like this, that sir, here I am having more and here I am having lesser gap. This gap is 4.90 and this gap is 4.22 electron volt. Right sir, this is my metal and this is my semiconductor, and you know that this is having more electrons. So electrons from here will come towards this side. That means this side will become positive, this side will become negative, and you need to apply positive voltage. And you can see that sir, here what will be the flat band we will be getting because of phi m si. So you can see that sir, by default it is coming out to be positive only, phi m minus phi si. So that would be minus 4.90, that would be 0.68. So 0.68 volt. So this is the flat band voltage we are having because of work function difference. And what will be the flat band voltage? Do I have the page? Yes. So what will be the flat band voltage because of the fixed oxide charges? So let's go to the next page. Flat band voltage because of the fixed oxide charges. So that would be minus qx upon cux. Sir, qx value do I know? Yes sir, minus 6.4 into 10 power minus 8. Minus 6.4 into 10 to the power minus 8 divided by cux epsilon ox, that would be multiply with tux. Tux would be 15 nanometer. So 15 nanometer. So 1.5 into 6.4 divided by 3.9 divided by 8.85, 0.278 volt. Okay, so this is the flat band voltage we are having. So what will be your threshold voltage now? Sorry, not threshold, sorry guys, what will be your flat band voltage now? Sir, your flat band voltage would be, sir, in this case I needed to apply the positive value, so 0.68 volt minus, in this case negative I need to apply 0.278. Don't get confused, like here you will not put another negative sign. What was the formula? If you just go by the formula, then also you will be able to solve it. What was the formula? The formula was phi msi minus qx upon cux. So basically, because of the fixed positive charge, what would happen in the semiconductor? Negative charge would come. To kill that negative charge, you need to apply negative charge only, so that negative positive will cancel out each other. Right? Very simple thing, very straightforward. So you know that phi msi is 0.68 volt minus 0.278 minus 0.68. So answer is 0.4 volt. So usually I am saying, usually for the n-type substrate, no, usually for n-type substrate, flat band voltage would be positive. Usually, no hard and fast rule. Usually for n-type substrate. Here what we are using n-type substrate this time. N-type silicon we are using. So usually for n-type substrate, flat band voltage would be positive. And for p-type substrate, it would be negative. Because what will be the scenario? In p-type substrate, this Fermi level will be downward, no? Fermi level will be downward. That means phi msi would become negative. So for p-type substrate, flat band voltage would be negative. More chances are there of a negative voltage. And for n-type substrate, flat band voltage would be positive. More chances are there. No hard and fast rule. But again, if we talk about in general, so in general, I will write down in general. In general, again very important, in general, V flat band is positive for n-type substrate. It is not a hard and fast rule. It is not certain. In general, I am putting for n-type substrate. And V flat band would be negative for p-type substrate. Well and good. Okay. This is in general, not an hard and fast rule. Yeah. So till now, whatever the mode of operation we studied, we have studied all mode of operation. Weak inversion, started with accumulation, then depletion, weak inversion and strong inversion. There we considered zero flat band voltage. But whenever you apply any bias, your first task would be that first I achieve the flat band, after that I apply any bias. Let's just say I am applying some 3 volt. So first I will achieve the flat band and then I will apply this 3 volt. So the formula of threshold voltage that we studied, what was the formula? Sir, on top level, this is something that I remember, that sir, my applied gate voltage is Vox plus surface potential. Along with that, you will always add up flat band voltage as well. So whenever you find out the gate bias, on the gate, how much bias I need to apply, always never ever forget to add up the flat band voltage as well. Till this point, whatever the numerical that we solved, there we consider that flat band voltage is 0. But always it is not necessary that flat band voltage would be 0. So you always need to consider the flat band voltage as well. So what will be the modified formula? So this I already know, sir. At the strong inversion, sir, I will ignore the inversion charges. Only I will take into action only my depletion charges. Sir, what is the formula of depletion charges? Sir, Q Na XD. Right? I am writing it down for P substrate. For P substrate, I am writing down the formula. If it was N substrate, then here Q Nd XD would become. Okay, for N substrate as well, we will write down all the formula. Don't worry about it. So Q Na XD. Now, sir, XD value I already know. What is XD? 2 epsilon Q Na. And sir, at the edge of strong inversion, it would be 2 phi f. Right? So under root 4 Q Na epsilon phi f. So Q depletion would become 4 epsilon Si Q Na phi f divided by COX plus 2 phi f plus what will be the flat band voltage? Flat band voltage would be phi m Si minus QOX upon COX. Looks like a very big formula, but don't worry about it. You will be able to remember it. So yes or no? No need to remember it. Basically, you will be able to derive it. I should have said, no need to worry about this particular formula. You will be able to derive it. Okay. No one actually, like a lot of people actually try to remember this one, that 4 epsilon Si Q Na phi f. But in a longer run, you would not be able to remember it. Okay. So I will recommend to derive it. How will you derive it? Sir, Q Na XD epsilon Si XD under root 2 epsilon Si Q Na 2 phi f. So from there, you will be able to derive it. Very simple. Well and good. So this is my threshold voltage, not VTH. Threshold voltage, I am representing my VT only. Right? Okay, well and good. Solve this question on your own. You should be able to solve. Na value is given, Ni value is given, epsilon Si is given, oxide thickness is given, fixed oxide charges are given, metal work function is given, Eg value is given. Along with that, this electron affinity is given. You need to find out the threshold voltage of the MOS capacitor. So, sir, threshold voltage formula, sir, I remember very easily, sir. First step, this is something that I will write down. Sir, phi s would be equals to 2 phi f. So, sir, here I will be writing down 2 phi f. Along with that, never ever forget flat band voltage as well. Sir, how flat band voltage would come into my mind? If your metal work function is given, that means surely silicon work function also would be given. From these values only, Eg value is given, psi si, like chi xi value is given. That means surely they are talking about silicon work function as well. So that would also be there. That means flat band voltage would come into action. Along with that, fixed oxide charges are also there. That means flat band voltage will surely come into action. It is not 0. So this value plus 2 phi f plus Vox, this is something you need to find out. Okay. And in place of Vox, what I will put? Under root 4 epsilon Si Q Na phi f divided by COX. Okay, again it is oxide per unit area. This is your capacitance per unit area. Capacitance per unit area. Why per unit area? Because here what did I apply? QNA XD. Your Q depletion was QNA XD, which was Coulomb per centimeter square. So here also COX dash we need to use. Capacitance per unit area. So what is COX dash? COX dash is having the unit of farad per centimeter square. Capacitance per unit area. Plus 2 phi f plus V flat band. This is the threshold voltage we are having. So all the values we need to find out. Again, there is a calculation only, nothing else. I guess flat band voltage like this phi SI value for the same data we have already calculated. So let's first try finding out silicon work function. This is what we are trying to find out. So EC, EV, draw the diagram. Sorry, intrinsic, and then the Fermi level here. Okay. So how much will be this gap? This gap would be 0.56, right? 0.56. 1.12 is given, so yeah, this gap would be 0.56. If this is your level, so here what you will put? This would be electron affinity is 4.05, right? 4.05, 0.56, and here how much value should come? Sir, it would be EFI minus EFP. EFI minus EFP. Sir, it would be KT ln Na by Ni. 0.347. And this is your 0.347. Like we can put electron volt here, we are not putting any value. So what will be your silicon work function? So 0.347 plus 0.56 plus 4.05. So 4.95. What we are getting? 4.95 volt. Right? So this value I already have now. Phi SI value I already have. Phi M value is already given, right? Phi M value is already given 4.40 electron volt. So phi M value is already given 4.40 electron volt. So phi MSI I will be able to calculate. Now QX upon CUX also I should be able to calculate. So let's first find out the flat band voltage only. So flat band voltage would nothing be phi MSI minus QX upon COX, that would be epsilon OX multiply with TOX, right? So phi M minus phi SI, so 4.40 minus 4.95 minus QOX. What is your QX? 5 into 10 power 10. 5 into 10 to the power 10 into 1.6 into 10 to the power minus 19 divided by epsilon OX. 3.9 into 8.85 into 10 to the power minus 14. 3.9 into 8.85 10 power minus 14 into TOX. TOX is 10 nanometer, that would be 10 to the power minus 6 centimeter. Okay, well and good. So now you will be able to find it out. Ten to the power minus 10 to the power minus 1, so 0.5, 0.8, yeah, 0.8 divided by 3.9 divided by 8.85. Oh, minus 4.40 minus 0.57. So flat band voltage is coming out to be minus 0.57 volt. This is the flat band voltage we are getting. So this was the first task that we have done. Now phi f value I already have. This was our phi f, right? This was our phi f. So what will be my surface potential? Surface potential is nothing but 2 phi f. So that would be simply the double of it. So 0.2 347 into 2, so 0.694 electron volt. So it will be simply the double of it. Okay. So what will be my threshold voltage? So my threshold voltage would be under root 2 epsilon Si. What is the value of epsilon? Epsilon Si is 11.7. Is it given? Yeah, it is given. 2 epsilon Si 11.7 into 8.85 into 10 to the power minus 14 QNA phi f, and here why I am putting 2? Here let's put okay, 2 also I can put 2 epsilon Si QNA phi f. What is the value of Q? Value of Q is 1.6 into 10 to the power minus 19. What is the value of Na? Na is 10 to the power 16, and your surface potential is 0.694. Okay, divided by epsilon Ox Tox. Again, very tough calculation. Epsilon Ox into Tox 10 to the power minus 6 plus 2 phi f. What that would be? 0.694 minus 0.57. This particular calculation we need to do would require a lot of patience. Why is that so? Because you can see here 10 to the power minus 14, 10 to the power minus 19. So it would become here 10 to the power minus 3, 10 to the power minus 17. I would take 10 to the power minus 8 outside. Yeah, so 0.2. Okay. So 0.2 into 11.7 into 8.85 into 1.6 into 0.694. Okay. Take the under root. Divided by 11.7 divided by 8.85. 0.046. 0.046 plus 0.694 minus 0.57. This is the scenario we are getting. Plus 0.694 minus 0.57. 0.17. Again, like very less value we are getting actually. Very less value of threshold voltage. It would be a bit larger, practically it would be a bit larger, but 0.17 is actually very low. Okay. And who is the major culprit? Like why we are getting very less voltage? Because of this flat band voltage. Flat band voltage is actually very high. This value is considered actually very high, right? Because metal work function difference, metal and semiconductor work function difference is actually very high. This work function difference is actually very high, and from here as well we are getting good enough value, right? So yeah, this is the answer we are getting. You can check back the calculation on your own, but I hope you have understood the whole point behind this question. Okay. Threshold voltage would surely come out to be positive only because you know that you need to apply positive voltage so that inversion layer will be framed. So it would come out to be positive since it is your p-type silicon. Okay. So like let me take a break and drink some water. I will come back. Also, I will check back the calculation as well. Okay, I will check the calculation again. Let's see, who knows, there was some different answer. So I will check the calculation and then I will come back. And after that, like some simple point like CV characteristics I need to draw with respect to taking the flat band voltage. Now I will consider the flat band voltage as well, and I will be considering for P substrate flat band voltage would be negative. So whatever the graph that I was getting at 0, like 0 I consider as flat band, but now the graph will be shifted by flat band. Like flat band voltage would be here,
Previously I was considering 0 volt here. Previously this was my flat band. Now this would become my flat band. So what do you think, what kind of graph you will be getting? Sir, directly this way, a bit downward, right? This is how. Okay, and the minimum capacitance you will get here. This kind of graph you will get. This would be your COX only. This is at a low frequency. At higher frequency, what kind of graphs you will be getting? This kind of graphs you will be getting at higher frequencies. Okay, so this kind of graph at higher frequency, this kind of graph at lower frequency, this would become your flat band voltage. This is my flat band. This is my V flat band. This is your accumulation. For some point you will get depletion. Then after some point you will get weak inversion. And once you have got a good enough inversion layer, inversion charges are coming into action. Now you will call it strong inversion. So just the point is that flat band voltage is added. Whatever that you are going to achieve at 0, now you are achieving that at flat band. And for P type, I have told you that flat band voltage would be negative. Okay. Right. So let me check back the calculation and I will come back. After that, what we need to see? We need to study MOSCAP with N-type substrate. Everything you already know. I will simply show it on the screen and you will be telling me everything. That if I apply positive bias, then what will happen? If I apply negative bias, what will happen? When I will get the inversion layer? Everything you will tell on your own. Okay. So let me take a break and then I will come back. Yeah, welcome back guys. So what was the error here? The error was here epsilon OX would come, no? So I have used 11.7. 11.7 will not come. What will come? 3.9 would come, right? So this would be 3.9. So answer that I got here, that would be 0.046 multiply with 11.7 divided by 3.9. So this would be 0.138. This value would be 0.138. Now 0.138 plus 0.694, right, minus 0.57. So it would come out to be 0.26 volt. So threshold voltage actually came out to be 0.26 volt. So there was an error here. What was the error? Error was here I should have used epsilon OX, not epsilon SI. I directly put 11.7 here as well and 11.7 here as well. That was the error, right? This slide we have already seen that this would be your flat band voltage. This is my flat band voltage. At flat band voltage I am getting some capacitance which we call CFB. CFB is lesser than COX. Why it is lesser? That also we have seen. Now we need to talk about MOSCAP but with N-type substrate. So again I will apply positive bias as well, negative bias as well. In that manner I will keep on applying. So if I apply positive bias, what will happen? Accumulation will take place, right? Just see it. If I apply positive, what this positive will say? Electrons, it will attract the electrons. It will tell to electrons to come to me. So electrons will come here. So electrons will be accumulated here. What will happen? Electrons will be accumulated. In N-type, electrons are being accumulated, right? This was already N-type. In N-type, more electrons you are getting. Electrons are being accumulated. So this will be known as accumulation mode. When you will get depletion, for getting the depletion mode, what you need to do? You need to apply the negative bias, right? What I will do? I will apply the negative bias. If I apply the negative bias, then what will happen? It will tell to electrons to go away. Electrons go away. So if electron concentration is going down, then what will happen? Hole concentration will increase. Along with that, you will get this kind of a depletion layer as well. So this depletion layer also you will get, right? You will keep on increasing this negative bias. More and more electrons will be repelled. Holes concentration will increase. At a point, we will reach a point. At that particular point, what will happen? Our hole concentration in the inversion layer would be equals to the electron concentration in bulk, right? Hole concentration near the surface would be equals to Nd, that is there in the bulk, and this point will be known as strong inversion, right? So everything you already know, everything you have already understood. Whatever that we studied in p-type substrate, the same analysis would go for n-type substrate. I have already drawn the energy band diagram, you can understand it. So energy band diagrams are drawn. This is for accumulation. In accumulation, what is happening? Electron concentration is increasing. If electron concentration is increasing near the surface, that means the gap between Fermi level and the intrinsic level will increase. Electron concentration increasing, so this gap will increase. In depletion mode, what will happen? In depletion mode, electron concentration is going down. That means the gap between Fermi level and intrinsic Fermi level will decrease because electron concentration is going down, right? What will be the surface potential? As much as it has gone down, as much as it has gone down, that will be the surface potential. This will be the surface potential. This will also be the surface potential, right? Okay. Then inversion and weak inversion, the same scenario, whatever the scenario that has happened. In the inversion, what will happen? This guy will go a bit upward. That means near the surface, we are starting to get p-type layer. And here we have got strong p-type layer. Here the holes concentration have become equals to the electron concentration in the bulk, right? So can you write down the expression of electron and hole concentration? Surely. What will be your electron concentration at the surface? That would be Nd e to the power. Here electron concentration will increase, so Q phi s by kT, right? Hole concentration you will be able to find out by Ni square by Ns. Here what will be the equation? Electron concentration is going down, so e to the power minus, not Ni square, what I am doing. Electron concentration is going down, so e to the power minus Q phi s by kT, and hole concentration would be Ni square by Ns. Okay, so similar scenario here as well, and here surface potential would become equals to 2 into Fermi potential. So everything we already know. Just answer me one thing. For getting the accumulation mode, what kind of bias you need to apply? Positive bias. Do you need to mug it up? No. Sir, n-type substrate. If I apply positive bias, electrons will be attracted. That means electrons will be accumulated. To get the depletion region, weak inversion or strong inversion, what you need to do? Sir, I need to apply negative bias, right? What will be the formula of flat band? Sir, formula of flat band will not change. Flat band voltage would again be the same thing. It will never ever change. Flat band voltage formula will never change. Phi MSI minus QSS not QOX. Sometimes in the books QSS word is written, but here we are using QOX. Whatever the charge that is there inside the oxide, if positive charge is there, then what I will do? Negative charge I will apply at the gate, right? Because positive charge will induce negative charge in the, because of the positive charge, what will happen? Electrons will be attracted, right? Because of that, what will happen? I need to kill those electrons. For that, what I need to do? I need to apply negative charge at the gate. So that's why minus QX would come. So this formula correspond irrespective of p-type or n-type, this formula will always work. Now threshold voltage. What is your threshold voltage? It is the applied gate voltage, right? It is the applied gate voltage where strong inversion is achieved. That means at this voltage, your surface potential would be equals to 2 phi f. Now just tell me one thing. Threshold voltage will be positive or negative? It will be negative, no? Right? So first task would be to get the flat bands. You achieve the flat bands, right? And now what I should write here? I will be writing minus Vox minus phi s. Are you able to understand this point? Forget about the flat band first. I know that, sir, I need to apply negative voltage. I know that my gate voltage is equals to Vox plus the surface potential, but it has to be negative plus flat band voltage. So always first task is get the flat band, whether it is positive or negative, you don't care. So first get the flat band voltage, and then I know that, sir, already that whatever that I am applying, that is negative only, no? So here I will put the negative sign. Vox formula, again I will put the same thing. What will be the Vox formula? Sir, Q and D XD divided by Q depletion divided by COX. plus phi s would be 2 phi f plus V flat band. But making sure one thing, that I will put the negative sign. I will put the negative sign outward. Say yes or no. And now if you solve it, what you will get? Under root 2 epsilon Si XD is under root 2 epsilon Q and D 2 phi f divided by COX minus 2 phi f plus V flat band. So this is the value of threshold voltage we are getting. This will be the formula of threshold voltage. Is it very confusing for you? I don't think it is confusing for you. Why negative sign we are using? It should be understandable. Flat band will always be added. No care about flat band. Flat band formula is also different. It doesn't care about anything. Flat band doesn't care about anything. It will always be added same formula. It's just that, sir, these guys will be negative here. Why these guys are negative? I hope you are able to understand why these guys are negative. Because the applied bias is negative. For getting the flat bands, what we will do? We will apply the bias. For getting the inversion layer, for getting the strong inversion layer, what we will do? We will apply the bias to be negative. Is that clear to you? Surely it is clear to you. Well and good. CV characteristics, can you draw? At positive voltage, what you will be getting? Accumulation. Then at negative voltage, till this point, what you will get? Depletion and inversion. And then you will get strong inversion. This kind of characteristics you will get, but actual characteristics would be somewhat like this. This is how the actual characteristics would look like. Okay. This is your threshold voltage, which will be surely negative only. This is your threshold voltage. Okay. So this much region is accumulation. Then for some time you will have depletion. Then for some time you will have weak inversion. And after the threshold voltage, this will be your strong inversion. Now capacitance and everything we already know. So this will be COX, this will also be COX, but this is happening at low frequency. At high frequencies, what kind of characteristics you will be getting? So these kind of characteristics I will be getting. Okay, so this is your high frequency. Well and good. All fine or understand? Everything is understandable. This diagram is completely understandable. What will be the characteristics here, sir? What kind of capacitance you are getting? Sir, here I am getting COX C depletion upon COX plus C depletion. Take this question, solve it. This is the end of our MOSCAP. So just you need to solve this question. Our MOSCAP will end. This time I am asking you to calculate everything with respect to n-type substrate. MOSCAP with n-type substrate. Everything we are going to do with respect to n-type substrate. Phi m is also mentioned. You can find out phi si, get the flat band. Substrate charge is also mentioned. This time the charge is negative as well, right? So negative charge means you need to apply the positive charge now. That means you need to give the positive supply. So everything is mentioned, like whatever the formula that is required, every formula you will have to use to get these answers. In the first question, what they are asking the maximum depletion charge per unit area in the semiconductor at threshold. Maximum depletion charge. What is the meaning of maximum depletion charge? So first thing, what is the depletion charge? What is the depletion charge? So depletion charge is
Q and D. This time I will be using Q and D. Q and D XD. But what they are asking maximum depletion charge. Now what is the formula of XD max? The formula of XD max would be under root 2 epsilon SI divided by Q and D 2 phi F. Right? All good? Here I would have written surface potential, but I know that when XD is maximum, then surface potential would be 2 phi F. And maximum surface potential I can get is, that is 2 phi F. Actually, it is not the surface potential, it is the potential across the depletion width. So depletion width will get maximum this much potential. Okay. So can I get the value of phi F as well? Yes, sir. Phi F value also we can get. So phi F value will be 0.0259 ln ND by NA, 5 into 10 power 16, 1.5 into 10 power 10. Zero 0.389. So what will be the surface potential? That is double of it, 0.778. Okay. So can you get XD max? Yes, sir. Under root 2 epsilon SI. What is the value of epsilon? Epsilon SI 11.7 is given, no? So 11.7 into 8.85 into 10 to the power minus 14 into 2 phi F 0.778 divided by Q and D. What is the value of Q? 1.6 into 10 to the power minus 19. What is the value of doping? 5 into 10 to the power 16. 5 into 10 to the power 16. So let's solve it. What we will get? 10 to the power minus 3, 10 to the power minus 11, 10 to the power minus 5. So 0.2 into 11.7 into 8.85 into 0.778 divided by 1.6 divided by 5, take the under root, 1.41. 1.41 into 10 to the power minus 5. 1.41 into 10 to the power minus 5 centimeter. This is your XD max we are getting. Okay. So what will be your Q depletion? So that would be, here I should have written Q and D, 1.6 into 10 to the power minus 19. What is the value of ND? ND is 5 into 10 to the power 16. Everything is going in centimeter into 1.41 into 10 to the power minus 5. So 10 to the power minus 8.41 into 5 into 1.6. So 11.35 into 10 to the power minus 8. So 1.13 into 10 to the power minus 7. This is what we are getting. Yeah, same answer we are getting. Coulomb per centimeter square. So this is the Q depletion we are having. Okay. This is the first thing we have calculated. And surely it will be a positive charge. So here I can put positive. So surely it will be a positive charge. Now, secondly, I need to calculate threshold voltage, but let's first calculate the flat band voltage, because flat band voltage would be required anyway, right? So ND is given, Ni is given, metal work function is given, electron affinity is given, everything is given. So now I can find out the semiconductor work function, phi SI I need to find out. So let's draw the diagram again. Conduction band, valence band, and this will be the Fermi level, and then I need to make intrinsic Fermi level, and I need to make this particular thing. Okay, 4.05, 0.56, electron volt, and 0.389 electron volt. Four point two two electron volt. Okay, so we are getting 4.22 electron volt. So this is the scenario that we are getting. So what will be my phi m SI? So your phi m SI would be nothing but phi m is given 4.70 minus 4.22. So it would be 0.48 volt. Okay, so this is your phi m SI. I need to find out the flat band voltage. So what will be my flat band voltage? Phi m SI minus Q oxide upon COX, that would be epsilon OX TOX, right? And everything I am going to mention in per unit area. So phi m SI already I know 0.48 volt. Now inside the oxide there is a negative charge, so it would become positive. Or directly if you write down this formula, you know that sir QX value is already negative. So this is charge density. Okay, take care, this is charge density. So charges per centimeter square they are saying. Charges per centimeter square means I need to multiply with 1.6 into 10 to the power minus 19 as well. So 4 into 10 to the power 11 into 1.6 into 10 to the power minus 19 divided by epsilon OX into 8.85 into 10 to the power minus 14 epsilon OX 11 point, where is epsilon OX? 11, epsilon OX is 3.9. Again I am doing the same blunder. It is 3.9. Okay, epsilon OX is 3.9 into TOX. What is the value of TOX? 15 nanometer. 15 nanometer. So 15 into 10 to the power minus 7 centimeter. Okay, so 15 nanometer would be 15 into 10 power minus 7, right? So this is the scenario. From here we will get the flat band voltage. 10 to the power minus 7, it would become 10 to the power minus 12. This and this will get cancelled out. 10 to the power minus 7, 10 to the power minus 12, it would become, and 10 to the power minus 1. So 0.4 into 1.6 into 15 divided by 3.9 divided by 8.85. So 0.278. 0.48 plus 0.278. So that would be plus 0.48. 0.578. That would be 0.76 volt. Okay, so flat band voltage is coming out to be 0.76 volt. Right, well and good. Now I need to find out the threshold voltage. So threshold voltage would be whatever the flat band voltage we are having, but now here I will put VOX plus 2 phi f. Say yes or no, right? Everything would become negative. 2 phi f also negative I will put, because I know that already negative bias I am applying. No, to get the threshold, like to get the inversion layer, I need to apply the negative bias. because I need to attract the holes. So I need to apply the negative bias. Flat band I am already having. I need to get the value of Vux. What will be your Vux? What do you think? Vux would be nothing but Q inversion plus Q depletion divided by Cux, right? So Q inversion is 0, Q depletion divided by Cux. Q depletion I already know. Q depletion I already know. 1.13 into 10 power minus 7 divided by Cux. What would be Cux? Cux would be epsilon Ox Tux. So epsilon Ox Tux. This thing I need to write down. 3.9 into 8.85 into 10 to the power minus 14 into Tux 15 into 10 to the power minus 7. So this and this will get cancelled out. So basically you are getting 1.13 into 15 divided by 3.9 divided by 8.85. Basically here you don't need to apply the longer formula. Sir, whatever the formula that you write down here, 4 epsilon Si Q and D phi f. This formula you don't need to apply. Even if you apply this formula, you will get the same answer. But what we need to do, we need to find out Vux. Keep your mind open. You know that what is Vux? Q depletion plus Q inversion divided by Cux. Q inversion is not coming into action. So simply it will be Q depletion by Cux. Okay. So this is the thing we are getting. So answer is coming out to be 0.49. So Vux is coming out to be 0.49. So let's find out the threshold voltage now. Flat band voltage is 0.76. This will come as it is. Vux is coming out to be 0.49 plus 2 phi f. 2 phi f. What is 2 phi f? 2 phi f, that is 0.778. Okay, plus 0.778 minus 0.76 minus 0.5. Yeah, minus 0.5. Roughly around threshold voltage is coming out to be minus 0.5 volt. This is the threshold voltage we are getting. Threshold voltage we have calculated, flat band also we have calculated, everything we have calculated, Q depletion also we have calculated. Now they are asking minimum capacitance value. Minimum capacitance also we can calculate. What will be your minimum capacitance value? So in C minimum, but C minimum would nothing be epsilon Ox C depletion minimum divided by Cox plus C depletion minimum. I should have already calculated the value of Cox because again and again it is being used. So again I have to do the same calculation, epsilon Ox divided by Tux, here whatever the calculation I was doing. So previously only I should have calculated it. Already you should always calculate epsilon Ox and capacitance per unit area. Okay, farad per centimeter square. So again per unit area they are asking. So every calculation we are doing in per unit area only. So epsilon Ox divided by Tux, 15 into 10 power minus 7. Okay, so what answer you are getting? 3.9 into 8.85 divided by 15. So 2.3 into 10 power minus 7. 2.3 into 10 to the power minus 7 farad per centimeter square. C depletion I need to calculate. That would be epsilon Si XD maximum, right? Epsilon Si upon XD maximum, right? So what will be your XD maximum? XD maximum we have calculated somewhere, I guess. Yes, 1.14 into 10 to the power minus 5 centimeter. Epsilon Si I already know, 11.7 into 8.85 into 10 to the power minus 14 divided by 1.41 into 10 to the power minus 5. 1.41 into 10 to the power minus 5. So let's do one thing, everything we will calculate in 10 to the power minus 7 only. So what we will get? This is your 10 to the power minus 9. So 11.7 into 8.85 divided by 1.41. divided by 100. 0.734 into 10 to the power minus 7 farad per centimeter square. So your C minimum would be 0.734 in parallel to 2.3. So 2.3 into 0.734 divided by 2.3 plus 0.734. 0.55. We are getting 0.55 into 10 to the power minus. You can put the values here now. This is not XD max, sorry, this is C depletion minimum. C depletion minimum. So your C depletion minimum we are getting as C depletion minimum already we are having, CVX also we are having, this also we are having, this also we are having. You can do this calculation. We are getting 0.556 into 10 to the power minus 7 farad per centimeter square. So answer would be 5.56 into 10 to the power minus 8 farad per centimeter square. That is your C minimum. Okay, that's it. This is the end. Are we getting the same answer? Yes, we are getting the same answer. Okay, so it's like a revision of all the numerical problems. Like from here only, whatever the numerical problems that can be framed, that would be framed. Okay, apart from this, no kind of numerical problem can be framed. They can ask electron and hole concentration at the surface. That formula we already know. So it's like a revision of everything that we have studied. Now one more concept I will tell in brief manner only. I will tell. If you want to write down, you can write down on your own. I will give you one free page. So there you can write down. But in brief, I am explaining that concept. What is that concept? Let's just say I am changing my gate voltage from, we are talking about P type substrate. Okay, MOSCAP we are having. MOSCAP we are having. I am having P type substrate. This is the gate voltage. So this is the graph of gate voltage I am having. So I am changing my gate voltage from -5 to +5, and threshold voltage, let's just say, is 3 volt. Threshold voltage is 3 volt. So this is the kind of graph you have got. This is the kind of graph you get, right? For low frequency, I consider the case of low frequency only. Okay. Now what you are doing, sir? Suddenly I am changing from -5 to +5. When it was -5, what was the scenario? Holes are being accumulated. Now suddenly what you have done, from -5 to suddenly you have made +5. What this +5 will say? At t equals to 0, this +5 will say that with respect to positive charge, I require very high negative charge. It is above than threshold voltage as well. That means it requires inversion layer as well. Along with that, it requires depletion layer as well. Right? But that will take some time. That particular scenario will take some time. You are directly going from -5 to +5. Directly you are taking here. In 0 time, you are changing this much. But semiconductor will say that, sir, you require electrons, you require depletion region. I need some time for that. I need some time for the electrons to be generated. What semiconductor will do now? With respect to +5 volt, what this semiconductor will do? Because here, what is the scenario? This is the scenario. This is the scenario. Although at +5 volt, you would say that, sir, inversion layer would be framed, and I will take the help of inversion layer. I will not go inside the semiconductor, and this will be the capacitance that I will be getting. That would be COX. Because, sir, threshold voltage is 3 volt. If we are at 5 volt, that means inversion layer have been framed. But what really happened? You went from -5 to +5 very immediately. So inversion layer will take some time to, it will take some time to be framed, right? Inversion layer will take some time to be framed. So in this particular time, what will happen is that this +5 will reflect the holes, and depletion layer will be made. And with respect to +5 volt, very big depletion layer will be made. Like this XD will even extend XD maximum. You would have got your XD maximum at 3 volt. But no, directly when -5 to +5 you have went, suddenly you have went to +5, holes were there. Now suddenly he is saying that I need a lot of electrons. So semiconductor will say, I cannot generate a lot of electrons. Because of this +5, you are repelling my holes. Because of that, you are getting some depletion region. And now my capacitance would be simply COX
C depletion upon COX plus C depletion. Now this C depletion would be very less. Why is that so? Because this guy has become very large. The depletion width has become actually very large. Is that clear? And if it is very less, then your CAB would also be very less. So this kind of graph you will be getting. Even lesser value. Basically, your capacitance value would even be lesser than C minimum. So the question can be asked, in the interviews it can be asked, that can your capacitance value be lesser than the C minimum value? Can it be lesser than this value? It will be lesser, sir, if you directly sweep from -5 to +5. That means this very high voltage, suddenly this very high voltage is demanding very high negative charge. And this very high negative charge will be given by the depletion layer only, because it would take a finite time for the electrons to come. So electrons have not come yet. Electrons will come, but it will take some time. So it will take a finite time for the electrons to come near to the surface. Because of that, whatever the charge it requires, whatever the negative charge this +5 requires, it will take that particular negative charge from the depletion layer. Okay, and with respect to +5 volt, very high depletion layer will be framed. That means C depletion would be very low. If C depletion is very low, that means my CAB or CGB, I can say this CGB would be less than C minimum. So I don't know how they can frame some question from here. In gate examination as well they can frame it, but it is possible to get capacitance lesser than C minimum as well if you sweep it very fastly. Sweep means from -5 to +5 you have swept it very fastly without even giving any time. -5 to +5, then you gave very low time, and then from +5 to you went to -5, then +5, -5, +5, -5. So the inversion layer will never be framed. Look, -5 is having no problem. Why -5 is having no problem? Because -5 will say that I need holes, and p-type semiconductor will say that holes I can provide. But +5 is saying that I need electrons. Now electrons in the p-type semiconductor will take some time to be generated. P-type semiconductor will say that I have a lot of holes. You tell me how many holes you require, I will give you. But if you want electrons, then I will take some time to be generated. If you cannot wait for it, then what you do? You take it from depletion region. You frame a depletion region and take it from there. Your +5 volt will repel the holes, and depletion layer will be framed. You take it from the depletion region. You are taking it from the depletion region. Depletion layer has been framed. That means my equivalent capacitance would be 1 by CGB would be equals to 1 by COX plus 1 by C depletion. Now, very large depletion layer, that means C depletion will be very less. That means your CGB would also be very less. So this kind of graph, in some books you would find that, sir, this kind of graph is also made. But you said that, sir, it cannot go below C minimum. It can go below C minimum as well if you are sweeping it very fast. Is that clear to you? So theory we are not writing down. In any manner, if you want to write down, I am giving you free space, you can write down there. Just that you can write down a conclusion in this manner, that your CGB can be lesser than C minimum as well if your toe generation is high. This is how I am telling. If this is high, if your generation lifetime is higher, then your CGB would be lesser than C minimum. So this line I will put here, and it would make you remember that something we have already studied about this particular scenario, that even lesser than C minimum capacitance I can get. In the gate examination till this date they never asked question from here. In theoretical problem they can frame one kind of question, that when your gate to body capacitance could be lesser than the minimum capacitance that you get. What do you mean by minimum capacitance? Sir, minimum capacitance we already know, that is COX C depletion minimum divided by COX plus C depletion minimum. Okay, so all these things, everything we have understood. Say yes or no, right? So here your MOSCAP will end. All the PYQs you will be able to solve. Now we need to start studying about MOSFET. Okay, yeah, thank you very much. Happy